In this next sequence of videos, we're going to revisit the single source shortest path problem. This is a problem that we already solved using Dijkstra's greedy algorithm. Now let's see what the dynamic programming paradigm can do for us for this same problem. Let me just quickly remind you the definition of the problem. What's the input? What's the output? We're given a graph, and when we talk about shortest path, we're going to be discussing only directed graphs. Each edge of the graph has a length, which we're going to denote by C sub e. And one vertex, which we'll denote by little s, is designated as the source vertex. We're going to assume that the graphs are simple, that is, there's no parallel edges. The reasoning is the same as in the minimum spanning tree problem. If you had a bunch of parallel edges, since we only care about the shortest path, you may as well throw away all of the copies of an edge except for the one that has the smallest length. The responsibility of an algorithm for this problem is to compute the length of a shortest path from this source vertex S to every other possible destination V. And always, when we talk about the length of a path, we mean the sum of the edge costs of all of the edges that are in that path. For example, if the cost of every edge was 1, then we'd just be talking about the hop count, and that's a problem that's solved using breadth first search. But in general, in the single source shortest path problem, we're interested in edges that have possibly wildly different lengths from each other. So let's now review our existing solution for the problem, Dijkstra's algorithm, review its pros and its cons. So Dijkstra's algorithm is a great algorithm. If you have a graph and it fits in your computer's main memory and all of the edge costs are non-negative, if you implement Dijkstra's algorithm using heaps, you will get a blazingly fast and always correct shortest path algorithm. In part 1 of this course, we explained an implementation using heaps that runs in big O of m times log n time, where as usual m is the number of edges and n is the number of vertices. And this implementation is almost identical to the one we discussed earlier in this course for Prim's algorithm for computing a minimum spanning tree. It turns out you can get an even better asymptotic running time, at least theoretically, a running time of m plus n log n if you use a more exotic type of heap data structure. But let's for now just think of this as the line in the sand. Big O of m log n using Dijkstra's algorithm on a graph with non-negative edge lengths. So given what a great algorithm Dijkstra's algorithm is, on what basis could we reject it and study any other shortest path algorithm? Well, there's two drawbacks we've mentioned before. Let me reiterate them now. So first of all, if you're working with a graph where some of the edge costs can be negative, then the output of Dijkstra's algorithm need not be correct. The correctness relies on the non-negative edge cost assumption. We saw concrete examples of this both back in part 1 of the course, but also in this course when we first started talking about greedy algorithms and we discussed their ubiquitous incorrectness. Now, frankly, for many of the applications of shortest path algorithms, you're never going to run into negative edge links. If you are implementing, for example, a program that computes driving directions, whether you're doing it in miles or in time, you're not going to have negative linked edges, at least until we finally get around to inventing those time travel machines. But not all applications of the shortest path problem are so literal and involve literally computing some path in space from some point A to some point B. More abstractly, the problem is just helping you find an optimal sequence of decisions. Imagine you were managing a bunch of financial assets, for example, and you were modeling a single transaction as an edge in a network that takes you from one particular inventory to another. When you sell stuff, that might generate positive revenue and correspond to a positive edge length. But when you buy stuff, then of course you have to spend money, and that can correspond to a negative edge length. So the second drawback, which we mentioned in the intro video for this course, is that Dijkstra's algorithm seems highly centralized. Now, that's not a problem if you just are storing the entire graph in the main memory of one machine, but if you're talking about routing in the internet, well, it's totally impractical for a router to have an up-to-date, complete map of the entire internet to compute routes locally. And so that motivates looking at a different shortest path algorithm, which is better suited for distributed routing. So we're going to be able to address both of these drawbacks in one fell swoop via the Bellman-Ford algorithm, which will be yet another instantiation of the dynamic programming algorithm design paradigm. This Bellman-Ford algorithm, despite predating the earliest version of the ARPANET by a good 10 years, nevertheless does form the basis for modern-day internet routing protocols. Of course, there's a lot of engineering steps that you need to go from the abstract Bellman-Ford algorithm to practical solution to internet routing. We'll discuss that a little bit in a separate video, but this really is where it all gets started. So before we start developing the Bellman-Ford algorithm, we need to take care of some subtle preliminaries. We need to be clear about how we're defining shortest paths in the presence of negative edge costs, and in particular, in the presence of negative cost cycles. That is, a directed cycle of edges where the sum of the edge costs is less than 0. You could think, for example, about this green cartoon I've drawn off on the right, where somewhere embedded in this graph is a directed cycle that has 4 edges. Some of the edges in the cycle have negative cost, some have positive, but on balance, the cycle has negative overall cost -2, if you traverse all 4 of the edges. So let's think about how we should define the shortest path from the source vertex S to some destination V in a graph like this. In particular, do we allow cycles in the path or not? So first, let's think through the ramifications of allowing paths to include cycles. So this proposal actually doesn't make sense, in that generally there will be no shortest path from S to V if you allow cycle traversals. The reason being that if you have a negative cycle, like this one of overall cost -2 in this green graph, and you can actually reach it from the source S, then for every path, you can actually find another path which is even shorter. You traverse the directed cycle one more time, the overall path length drops by another -2, and there's nothing from stopping you from just doing over and over and over again. So either the shortest path, you can think of it as being undefined, or you can think of it as being sort of -infinity in the limit. So if permitting our path to have cycles didn't work, why not we explore the option where we forbid cycles in our paths? So this version of the problem is perfectly well defined. It's a totally sensible computational problem, which you might well want to solve. The issue here is much more subtle. The issue is that this problem is what's called NP-complete. So that's something we'll discuss much more next week. But the bottom line is these are intractable problems. There are no known computationally efficient, no known polynomial time algorithms for NP-complete problems. And this, unfortunately, is one such problem, computing shortest cycle-free paths in the presence of negative cycles. So a bit more precisely, if you came up with a guaranteed correct and guaranteed polynomial time algorithm that always computed shortest paths in the presence of negative cycles, a consequence would be what's called P equals NP, and that's something we'll discuss a bit more formally in a later video. But certainly if you came up with such an algorithm, you should report immediately to the Clay Institute. They would have a $1 million prize awaiting you for such an algorithm. So for those of you that are already familiar with NP-completeness, it would be an easy exercise to prove that this problem is NP-hard. It would just be a reduction from the Hamiltonian path problem. So it seems that we're stuck between a rock and a hard place. If we allow cycles in our paths, we don't get a meaningful problem. We get something that doesn't make sense. If we exclude cycles, we get a perfectly meaningful but unfortunately computationally intractable problem. So here's how we're going to proceed. We're going to focus for now just on graphs that do not have negative cycles. We will, of course, allow individual edges to be negative, but we're going to insist for the moment that every single directed cycle of the input graph has overall non-negative length. So it can have some positive edge costs, some negative edge costs, but overall it has to be non-negative. Now, I don't blame you if this assumption bothers you, but the good news is, as we'll see, the Bellman-Ford algorithm effortlessly checks whether or not this condition holds. It effortlessly detects a negative cycle in the input graph if one exists. So the version of the shortest path problem that Bellman-Ford algorithm is going to solve will be the following. Given an input graph, which has negative edge costs, it may or may not have a negative cycle, the Bellman-Ford algorithm will either correctly compute shortest paths from the source to all the destinations, just like you wanted, or it will punt, but it will offer you a good excuse for why it punted. It will show you a negative cycle in the input graph, and of course computing shortest paths is intractable in the presence of a negative cycle, so Bellman-Ford, you have to sort of let it off the hook in that case. Okay, so it'll give it an input graph, either it'll show you a negative cycle, or it'll give you all of the desired shortest path distances. That's the guarantee we're going to strive for. So I'm going to end this video with a quiz helping you understand why this hypothesis of no negative cycles might be useful in an algorithm. So for now, I just want you to think about, suppose I promised you that an input graph had no negative cycles. And the question is, how many hops, how many edges are sufficient to guarantee that you found the shortest path between S and some given destination V? So the correct answer is A, and this is one of the main reasons the no negative cycle hypothesis is useful. It gives you control over how many edges are necessary to ensure that you've got a shortest path. So specifically, suppose you had a path between some s and some v that had at least n edges. Well, if you have at least n edges, it means the path visits at least n plus 1 vertices. There's only n vertices, so if you visit at least n plus 1, that means you visit one vertex twice, say x. So that means you have a cycle inside your path that goes from x back to x again. Now, if you rip out this cycle, if you just delete those edges, you get another path from s to v. And because this directed cycle, as they all are, must be non-negative, the total length, the sum of the edge costs, has only gone down by removing this cycle. So you show me a path from s to v with at least n edges. I'll show you a path with fewer edges and that's at least as short, could only be shorter. So that shows you that the shortest path, or a shortest path, has at most n minus 1 edges, which is the correct answer to the quiz. In this video, we'll start developing the Bellman-Ford algorithm. As an instantiation of the dynamic programming paradigm, we'll develop it in the usual way by understanding how optimal solutions must necessarily be composed of optimal solutions to smaller subproblems. So let me just quickly review what we learned from the subtleties of the previous video. In particular, let me be precise about what I mean by solving the single source shortest path problem when the input graph can have negative edge costs. So the input, as usual, is a directed graph. Every edge has an edge cost c sub e. We're allowing those edge costs to be negative, and we're given a source vertex s. So what do we want to compute? Well, ideally, we'd like to compute the shortest path distance from s to all other destinations v, where as usual, the length of a path is just the sum of the edge costs. Now, in the previous video, we discussed how this goal is problematic for input graphs that have a negative cycle. If you allow cycle paths to contain cycles, then this isn't even defined. The, in some sense, shortest path length is minus infinity. And if you don't allow cycles, then it's computationally intractable. It's an NP-hard problem. So if you fail to compute shortest paths, then at least tell us an excuse. Output a negative cycle in the input graph as the reason for your failure to compute shortest path distances. So for this video, I'm just going to develop the Bellman-Ford algorithm for input graphs that do not contain negative cycles. And of course, these are the cases in which we better actually output the correct shortest paths. Once we've got the Bellman-Ford algorithm up and running for input graphs that do not have negative cycles, we'll see that it's a fairly easy matter to extend it to the general case. And for input graphs that have negative cycles, we'll be able to output such a cycle without affecting the running time of the basic algorithm. So with an eye toward a dynamic programming algorithm for the shortest path problem, let's start thinking about optimal substructure, the way in which optimal solutions, that is shortest paths, must necessarily be composed of optimal solutions, that is shortest paths, to smaller subproblems. Now, the formal optimal substructure lemma is going to be a little bit cumbersome to state, so let me just spend a slide kind of telling you, what the deal is, how to think about it. It's often tricky to figure out how to apply the dynamic programming paradigm to graph problems. One of the reasons for that is that graphs aren't really naturally sequential objects. They're not ordered in any obvious way. We're just given some unordered set of vertices and some unordered set of edges. Now, one special case, of course, would be path graphs, our very first example of dynamic programming. There is an obvious ordering on the vertices of the graph. But unlike, say, alignments, sequences, where again there's an obvious ordering from left to right, in a graph problem it's not so clear how to order things. For this particular graph problem, however, it seems like we've got something going for us, which is the sequentiality of our output. Right? Paths are certainly sequential objects, so that gives us hope we can state and prove an optimal substructure lemma, talking about how optimal solutions, shortest paths, must be built up from, in some sense, smaller shortest paths. Unfortunately, it's still far from obvious how to really define smaller and larger subproblems. So for example, you'd love to have some intelligent ordering on which you process the possible destinations v, but it's not at all clear how to do that without knowing the shortest path distances in the first place. So this is a subtle issue that I encourage you to think hard about in the privacy of your own home so you can better appreciate what's non-trivial about the Bellman-Ford solution. So the key idea in the Bellman-Ford algorithm, and it's a good one, is to introduce an additional parameter that gives us an unambiguous definition of subproblem size. So what this parameter is going to do for a given destination v is it's going to control how many edges we allow in paths from the source s to this destination v that we're looking at. To explain this, let's look at the following green graph that has 5 vertices on the right-hand part of the slide. So in the Bellman-Ford algorithm, we're going to have one subproblem for each possible destination and each possible restriction on the number of edges in a path. So for example, suppose we're looking at S and we're looking at destination T, and we think about paths that only have 2 edges or less. Well, in that case, the shortest path length subject to that constraint from S to T in this graph has length 4. The bottom path, which has 3 edges, is not an option. We're only permitting 2 edges or less in this current subproblem. Now, if we bump up the edge budget to 3, then the corresponding shortest path distance drops from 4 to 3, because all of a sudden we can make use of this 3-hop path on the bottom. And again, the point here is that it gives us an unambiguous notion of subproblem size. The more edges you're allowed to use in your paths from a source to a given destination, the bigger that subproblem. All right, so that discussion was deliberately vague to give you some context for the following formal statement of the optimal substructure lemma. So we're going to go ahead and state and prove this optimal substructure lemma in full generality. We're going to be working with arbitrary input graphs. They might have a negative cycle, they might not. So like all of these optimal substructure lemmas, the statement's going to have the form that the optimal solution to a subproblem has to be one of a small number of candidates that are composed in simple ways from optimal solutions to smaller subproblems. So how do we index a given subproblem? Well, there's going to be a destination V that we care about, and as we said in the last slide, there's going to be a budget on how many edges you're allowed to use in a path from S to V, and we're going to use I to denote that budget. So for every possible destination V, and so for every possible edge budget, there's going to be a positive integer, 1 or bigger. Suppose that P is an optimal solution, meaning amongst all paths that start at S, that end at V, and that contain at most I edges, amongst all of those paths, P has the minimum sum of edge costs, the minimum length. So a subtle point, because we're proving this lemma in its full generality, that is also for input graphs that might have negative cycles, we need to go ahead and allow this path P to use cycles if it wants, including potentially to use a negative cycle multiple times. That is allowed. Notice we're not worried about this path using a cycle an infinite number of times because we have a finite budget I on how many edges it can contain. So with that set up, what are the possible candidates for what capital P could possibly be? Well, we're going to have our usual sort of trivial case 1, which is that if this path P doesn't bother to use up its full edge budget, that is if it has I-1 edges or less, well then, naturally, P better be the shortest SV path that has at most I-1 edges. So the non-trivial case is when the shortest path with the most I edges from S to V actually uses its full budget, uses all I of its edges. So now, by analogy with all of our previous dynamic programming algorithms where we think about plucking off the final part of an optimal solution, here we're going to pluck off the final edge from the path P. What do we get? Well, we get a path with 1 fewer edge, so that's good. It's going to correspond to some smaller subproblem because it has at most I-1 edges. On the other hand, notice that if we take a path from S to V and we pluck off the final edge, we get a path from S to somewhere else. So we're going to call that somewhere else W. So plucking off the final edge from capital P gives us a path P prime that starts at S, that ends at W, that has at most I-1 edges. And I hope you can guess that the claim is that it's not just any old path from S to W with at most I-1 edges. It is, in fact, a shortest such path. Now in this case too, notice that we of course know that P prime has exactly I-1 edges, not merely at most I-1 edges, but it's going to be useful to have the stronger assertion claimed here, that P prime is optimal amongst all paths that have I-1 edges or possibly fewer. Alright, so this is one of those lemmas that's actually harder to state than it is to prove. So let's just quickly sort of talk through the proof. It's the same as the previous optimal substructure lemmas that we've seen. Case 1 is totally trivial. It's the obvious contradiction that we've seen in many of our other case 1s. Case 2 is going to be one of our usual cut and paste contradictions. So suppose there was some path Q better than P prime. That is, Q starts at S, ends at W, contains I-1 edges or less, and the sum of its edge costs is even smaller than that of P prime. Well then if we just tack on the final hop of P, that is the edge WV, we get a path that starts at S, that goes to V that has at most I edges, and the total sum of edge costs in this path Q plus WV is strictly less than that in the original path P. But that contradicts the purported optimality of P amongst all paths starting at S, ending at V, and having at most I edges. So that's the proof of the optimal substructure lemma. It's simple enough. And as usual, the next step is going to be to compile this lemma into a recurrence, where informally what the recurrence is going to do is brute force search amongst the possible candidates for the optimal solution. So to make sure you understand what just happened, let's move on to a quiz. And the question is, for a given destination V of some input graph, how many candidates are there for the optimal solution of a subproblem that involves V? The correct answer is the second one. The answer depends on which destination V you're talking about, and what governs the number of subproblems is the integree of this vertex. That is the number of edges of the input graph that have V as their head. Why is this true? Well, case 1 contributes one possible candidate. It's possible that for a given I and a given V, all you do is inherit the optimal solution to destination V with a budget of one fewer edge. Case 2 may seem like only one other candidate, but actually case 2 comprises a number of them, one for each choice of that final hop, W, V. Specifically, for a given choice of W, that contributes a candidate optimal solution that's the shortest path from S to that choice of W that uses the most I-1 edges, plus that edge WV tacked on. Now that we understand the optimal substructure present in shortest paths, we can follow our usual dynamic programming recipe to arrive at the basic version of the Bellman-Ford algorithm. Let's compile our optimal substructure lemma into a recurrence, a formula that says how the optimal solution value of a given subproblem depends on that of smaller subproblems. I'll use the notation capital L sub IV to denote the optimal solution value of the corresponding subproblem. Subproblem is being indexed by two parameters. One, V, that's the destination we're interested in this subproblem. And the second one is the budget I on the number of edges that are permitted in paths from S to V in this subproblem. So a few details. First of all, remember that in the last video we proved the optimal substructure lemma in general for general graphs G, which may indeed have negative cycles. For that reason, we have to allow cycles in shortest paths from S to V. We're not concerned about the cycle being traversed an infinite number of times because we have this finite budget I on the number of edges that we permit. I also need to explain what I mean in the case that there are no paths from S to V with at most I edges. And indeed, when I is very small, that will in fact be the case for many destinations V. So if there's no way to get from S to V using only I hops, we just define LIV to be plus infinity. And as usual, in the recurrence, which is going to be defined for every positive integer I and every possible destination V, we're just going to state that the optimal solution value for this subproblem is the best of the possible candidates identified in the optimal substructure lemma. That is, capital L sub IV, the optimal solution value for the subproblem with parameters I and V, is the best of all of the possibilities. So let me start with a minimum to take the best of the case 1 candidate and the case 2 candidate. The case 1 candidate is simple enough. One option is always just to inherit the best path we found from S to V that uses only I-1 edges or less. And case 2, you'll recall from the quiz at the end of the last video, really comprises a number of subcases, one for each choice of the final hop. So here we're going to have another minimum ranging over all possible edges WV. For a given choice of that last hop, the shortest path length is going to be the shortest path from S to that choice of W that uses the most I-1 edges. And then, of course, we also incur the edge cost of the final hop, W, V. Correctness, as usual, follows immediately from the optimal substructure lemma. We know these are the only candidates, and by the definition of the recurrence, we pick the best one. Because our optimal substructure lemma has been proven, whether or not G has a negative cycle, this recurrence is correct for all positive values of I, whether or not G has a negative cycle. So now let's see how it's useful to assume that the input graph G does not have a negative cycle. So we had a quiz not too long ago that discussed the use of the no negative cycles hypothesis. In particular, we argued that n-1 edges are always enough to capture a shortest path between S and any possible destination. Why? Well, suppose there's no negative cycles, fix a destination V, show me a path that has at least n edges. If it has at least n edges, then it visits at least n plus 1 vertices. There's only n vertices, so the path must visit some vertex twice. And in between two consecutive visits of a given vertex, that's a directed cycle. By hypothesis, there are no negative directed cycles. They're all non-negative. So if I throw out this directed cycle from this path, I get a new path to the same destination V, and its overall length has only gone down. Discarding cycles only makes paths shorter. That's why there's a shortest path with no repeated vertices, that is, with at most n-1 edges. So what does this observation have to do with our recurrence? Well, it tells us we only need to compute the recurrence, evaluate subproblems for values of I up to n-1. There is no point in giving a subproblem a budget bigger than n-1 edges if there are no negative cycles. It's not going to be useful. You're guaranteed to have already found the shortest path by the time I has gone as large as n-1. So to make sure this point is clear, let me just formally write down the subproblems that we're going to solve in the Bellman-Ford algorithm and which are going to be sufficient to correctly compute shortest paths for input graphs G that do not have negative cycles. The subproblems are simply to compute the shortest path lengths capital L sub IV. Of course, for all destinations, we're responsible for ultimately computing shortest paths to every destination V, and for all relevant choices of the edge budget I. And so the base case is going to be when I equals 0, and we just said it has to go up as high as n-1 and no further. And this is actually a pleasingly parsimonious collection of subproblems. It may strike you actually kind of as a lot because there's a quadratic number, right? There's n choices for the destination V, and then I is taking on n different values. But remember, unlike all of the other problems we've been talking about, the output of this problem is linear size. We're supposed to output a number for each destination V. So we really only have a linear number of subproblems for each statistic we're responsible for computing. And that's as good as we've had in any of our other dynamic programming algorithms. So now it's a simple matter to write out the pseudocode of the justifiably famous Bellman-Ford algorithm. Because our subproblems are indexed by two parameters, the edge budget I and the destination V, we're going to have a two-dimensional array A. Remember that we're measuring subproblem size via the edge budget I. That's sort of the great idea in the Bellman-Ford algorithm to introduce this edge budget to control subproblem size. So the base case is when I equals 0, and then we're talking about getting from S to some vertex V using 0 edges. Okay, well, if V happens to equal S, then you can do it with the empty path, and the length of the empty path is 0. But if V is any vertex other than S, then of course you can't get from S to V using 0 edges. And remember, in that case, we define the optimal value solution to be plus infinity. So now we move on to our customary double for loop, one for loop for each of the indices that indexes our array A. And actually what's interesting is unlike most of the dynamic programming algorithms we're discussing, here the order of the for loop matters. You cannot pick arbitrarily. You really need to make sure that you have all the smaller subproblems solved by the time you need them. That means the outer for loop should be indexed by the subproblem size I. So as we discussed, we're not going to bother letting I range above n-1. That's going to be sufficient in the case where there are no negative cycles. And for each choice of I, we solve all of the corresponding subproblems, all destinations V. For each choice of I and V, of course, we just write down in code the formula that we stated in the recurrence. So as I'm sure you recall, case 1 furnishes one possible candidate. It's always an option just to inherit the shortest path from S to V that you computed using only I-1 edges. Alternatively, from case 2, there's also one candidate furnished for each choice of the final hop. So for each edge that ends at V, for each choice W, comma V, there's an option of taking a shortest path from S to W that uses only I-1 edges and tacking on that final edge WV. And as we've discussed, if it just so happens that the input graph G has no negative cycles, then this algorithm will indeed terminate with the correct shortest paths from S to all of the destinations. Those answers will be lying in wait for you in the biggest subproblems, the A n-1 V's. So that's correctness. As usual, it follows primarily from the optimal substructure lemma, but in this case also the hypothesis of no negative cycles guarantees that taking I equal n-1 is large enough to actually capture the final answers. So we'll talk about the running time of the Bellman-Ford algorithm in a sec, but first let's just go through a quick example to make sure all of this makes sense. Consider the following graph with 5 vertices. I'll label their edges with their costs in blue. So let's step through the values of I, and since there's 5 vertices, I is going to take on the values 0, 1, 2, 3, 4, and let's look at what the results of each round of subproblem computations is. So in the base case, when I equals 0, as always, the distance from S to itself is 0, and for all other vertices, the subproblem value is defined as plus infinity. Let me write down the recurrence again, just in case you've forgotten it. So now we enter the main for loops, and we start with I equal 1. So now we just go through the vertices in arbitrary order and evaluate the recurrence. So node S is going to just inherit the solution from the previous step. It's still happy with the empty path of total length 0. Now, node V is certainly hoping not to have to inherit its solution of plus infinity from the previous round when I equals 0. And indeed, when I equals 1, the subproblem solution for the vertex V is going to be 2. That's because we can choose the last hop to be the edge S, comma V. That has length 2, and S's subproblem value last iteration when I equals 0 was 0. By the same reasoning, X's new subproblem value is going to be 4, because we can choose the last hop to be S, comma X, and add the cost of that edge 4 to S's subproblem value last iteration when I equals 0. Now, the nodes W and T would love to throw out their plus infinity solutions and get something finite, and you might be thinking that because V and X now have finite distances, those would propagate to the nodes W and T. That will indeed happen, but we're going to have to wait till the next iteration. We're going to have to wait till I equals 2. The reason is, if you look at the code, if you look at the recurrence, when we compute the subproblem value at a given iteration I, we only make use of the subproblem solutions from the previous iteration I minus 1. We do not use any of the updates that have already happened in the current iteration I. So because when I equals 0, A of 0V and A of 0X were both plus infinity, we're going to be stuck with A1W and A1T both being plus infinity as well. So now let's move on to the next iteration of the outer for loop when I equals 2. The subproblem solution at S is not going to change. You're not going to do better than 0, so it's going to stay that way. Similarly, at the vertex V, you're not going to do better than 2, so that's going to stay the same at this iteration. Something interesting happens at the vertex X, however. Now, in the recurrence, you certainly have the option of inheriting the previous solution. So one option would be to set A of 2 comma X to be equal to 4, but there's actually a better choice. So the recurrence is going to come out to be even smaller. Specifically, if we choose that last hop to be the unit cost arc from Vx, we add that unit cost to V's subproblem value last iteration when I equals 1. That was 2. 2 plus 1 equals 3. So that's going to be the new subproblem value at X in this iteration where I equals 2. So as advertised, the updates to the vertices V and X in the iteration where I equals 1, now that I equals 2, get propagated on to the vertices W and T. So W and T shed their plus infinity values, and instead they pick up the values 4 and 8, respectively. Notice that I've labeled the vertex T with an 8, not with a 7. I've computed A of 2 comma T to be 8. And the reason is, again, the same. Updates from this iteration, in particular the fact that X has dropped from 4 to 3, do not get reflected at other nodes in this same iteration. We have to wait until the next iteration of the outer for loop before they happen. So we're using the stale information at X that when I equals 1, its solution value is 4. That's the information we're using to update T's solution value. So it's 4 plus 4, or 8. So in the penultimate iteration, when I equals 3, most things stay the same. At S and V, at X and W, we've actually computed the shortest paths, so they will all just inherit the solution from the previous iteration. But at vertex T, it will now make use of the improved solution value at the vertex X from the iteration where I equals 2. So its 8 gets updated to be a 7, reflecting the improvement at X, the previous iteration. And at this point, we're actually done. We've computed shortest paths to all destinations, but the algorithm doesn't know that we're done yet. So it still executes the final iteration of the outer for loop where I equals 4, but everybody just inherits their solutions from the previous round. At that point, the algorithm terminates. For most of the dynamic programming algorithms that we've discussed, the running time analysis has been trivial. The Bellman-Ford algorithm is a little more interesting from a running time analysis perspective. Please think about it in this quiz. So the correct answer is B. That is, of all these running time bounds, the smallest bound which is actually correct. So let me explain why it's the number of edges times the number of vertices, and also comment on some of the other options. So answer A, quadratic and squared, what this is the number of subproblems, right? So subproblems are indexed by a choice of I, which is somewhere between 0 and n minus 1, and a choice of a destination, V. There's n choices for each, so there's exactly n squared subproblems. If we only ever spent constant time evaluating a subproblem, then indeed the running time of Bellman-Ford would be big O of n squared. And in most dynamic programming algorithms we've discussed in this class, indeed you only spend constant time solving each subproblem. The one exception being the optimal binary search trees problem, where in general we spent linear time. Here again, like optimal binary search trees, we might spend more than constant time solving a subproblem. The reason being, we have to do brute force search through a list of candidates that might be super constant. The reason is that each arc that comes in to the destination V provides one candidate for what the correct solution to this subproblem might be. So remember, the number of candidates, we had a quiz on this, is proportional to the in degree of the vertex V. And that could be as large as n minus 1, linear in the number of vertices. So that's why the running time of the Bellman-Ford algorithm can, in general, be worse than n squared. Another interesting answer is C, that it's cubic in n. Indeed, big O of n cubed is a valid upper bound on the running time of the Bellman-Ford algorithm, but it's not the sharpest possible upper bound. So why is it a valid upper bound? As discussed just now, there's a quadratic n squared number of subproblems. How much work do you do per subproblem? Well, it's proportional to the in degree of a vertex. The biggest in degree of a vertex is n minus 1, big O of n. So linear work for each of the quadratic number of subproblems, resulting in cubic running time. There is, however, a better analysis of the Bellman-Ford algorithm. Now, why is O of mn bigger than n cubed? Well, what is m? In a sparse graph, m is going to be theta of n, and in a dense graph, m is going to be n squared. So if it's a dense graph, it's true, big O of mn is no smaller than n cubed, but if it's not a dense graph, then this really is an improved upper bound. So why does the bound hold? Well, think about the total amount of work done over all of the subproblems in the following way. So all we're going to do is take the amount of work done in a given iteration of the outer for loop and multiply it by n, the number of iterations of the outer for loop. So how much work do we do in a given iteration for a given choice of I? Well, it's just the sum of the in degrees. When we consider the vertex V, we do work proportional to its in degree, and we consider each vertex V once in a given iteration of the outer for loop. But we know a much simpler expression for the sum of the in degrees. This sum is simply equal to m, the number of edges. In any directed graph, the number of edges is exactly equal to the sum of the in degrees. One easy way to see that is take your favorite directed graph and imagine you plug the edges into the graph one at a time, starting from the empty set of edges. Well, each time you plug in a new edge, obviously the number of edges in the graph goes up by 1, and also the in degree of exactly one vertex goes up by 1, whichever vertex happens to be the head of the edge that you just stuck in. So therefore, the sum of the in degrees and the sum of the number of edges is always the same, no matter what the directed graph is. So that's why the total work is better than n cubed. It's actually big O of m times n. So a number of optimizations of the basic Bellman-Ford algorithm are possible. Let me wrap up this video just with a quick one about stopping early. See also a separate video about a less trivial space optimization of the algorithm. In the basic version of the algorithm, the outer for loop runs for n-1 iterations. Generally, you don't need all of them. We already saw that in our simple example where the final iteration did no useful work. It just inherited the solutions from the previous iteration. So in general, suppose it's some iteration earlier than the last one, so say with the current index value of j, it just so happens that nothing changes. That at every destination v, you just reuse the optimal solution that you recomputed in the previous iteration of the outer for loop. Well, then if you think about it, what's going to happen in the next iteration? You're going to do exactly the same set of computations with exactly the same set of inputs, so you're going to get exactly the same set of results. That is, it will be true again in the next iteration that you will just inherit the optimal solutions from the previous one. And that will keep happening over and over again until the rest of time. So in particular, by the time you get to the n-1th iteration of the outer for loop, you will have exactly the same set of solution values as you do right now. We've already proven that the results at the end of iteration n-1 are correct. Those are the real shortest path distances. If you already have them in your grubby little hands now, well, you may as well abort the algorithm and return those as the final, correct shortest path distances. Thus far, we've seen how in input graphs without negative cost cycles, the Bellman-Ford algorithm correctly computes shortest paths from the source vertex S to all destinations V. But what about input graphs that do have negative cost cycles? In this short video, we'll see how to extend the Bellman-Ford algorithm, leaving its running time essentially unchanged, so that it can easily check whether or not the input graph has a negative cost cycle. So the following claim is going to indicate the appropriate extension of the Bellman-Ford algorithm. In particular, this claim characterizes the presence or absence of a negative cost cycle in the input graph in terms of behavior of the Bellman-Ford algorithm. Okay, well actually the Bellman-Ford algorithm, if we ran it for one extra iteration. So currently we stop the Bellman-Ford algorithm when the outer index I is equal to n-1. For the claim, we're going to envision running that outer for loop for one extra iteration when I equals n, running the same old recurrence for all of the destinations v. So the assertion then is that G, the input graph, has no negative cycle if and only if we don't get any new information from this extra batch of subproblems. That is, if and only if ANV is exactly the same thing as AN-1V for every possible destination V. Equivalently, the input graph does have a negative cost cycle if and only if there exists some subproblem, there exists some destination V, where we see an improvement at V by running the Bellman-Ford algorithm for this extra iteration. So we're going to prove the claim in the next slide. It's not too hard, but I hope it's immediately clear what the implications of the claim are, how we check for a negative cost cycle. So now, given an arbitrary input graph with no promises, it might have a negative cost cycle, it might not. What do? You run Bellman-Ford, but you run it for one more iteration. You run it for the outer for loop index I going all the way up to n. And you check, does some subproblem value change in that final iteration or not? If not, if all of your AN-1Vs are the same as your ANVs, then by the claim, you know there's no negative cost cycle. By our previous work, we know the Bellman-Ford algorithm is correct. So we happily return the AN-1Vs as the correct shortest path distances as before. If, on the other hand, you notice that there's a vertex V so that ANV is different, is smaller than AN-1V, then you say, hey, there's a negative cycle by the claim, so I'm not going to compute shortest path distances for you. That wouldn't make sense. There is a negative cost cycle, and you punt. And of course, this one extra iteration in the Bellman-Ford algorithm has a negligible effect on its running time. It's still big O of m times n. So I'm lying a little bit in this claim. There's an edge case I'm not handling properly. When I wrote down the claim, I was thinking about arguably the common case of input graphs G, where there exists a path from S to every other destination V. That is, input graphs where all of the shortest path distances are finite. So if that's not the case, then the claim as stated is not correct. One way to see that would be just a degenerate instance where the source vertex S has no outgoing arcs at all, and maybe the rest of the vertices form a negative cost cycle. In that kind of graph, the left-hand side of this claim is false, but the right-hand side of this claim is satisfied. So to modify it for graphs that may have some infinite distances, I'm just going to modify the left-hand side to say G has a negative cost cycle that is reachable from the source vertex S. Now, if you actually wanted to detect in the input graph whether there was a negative cycle at all, reachable from S or otherwise, there are various tricks you can do to solve that problem, again, using the Bellman-Ford algorithm. So, for example, given an input graph, you can add a dummy sort of fictitious extra vertex and add arcs from that vertex to everybody else with length 0, run Bellman-Ford on that graph, and that will detect a negative cost cycle if one exists. So now that we know why we want the claim to be true, let's understand why it is true. Let's go to the proof. So the claim asserts something that's if and only if. On the left-hand side is the property of the input graph having no negative cost cycle. On the right-hand side is the property that the Bellman-Ford algorithm does not make any changes if you run one extra iteration. So proofs like this have two parts: assuming the left, prove the right; assuming the right, prove the left. One of these two parts, if you think about it, we already did when we proved that the Bellman-Ford algorithm is correct for graphs with no negative cost cycles. That is, if the left-hand side holds, if the input graph doesn't have a negative cost cycle, we already argued that you don't have to run the outer for loop beyond I equals n minus 1. That's sufficient to capture the shortest path. So in particular, take I as big as you like. For example, I equals n, you're not going to see even shorter paths. You're going to get exactly the same subproblem solutions. The content, then, is the reverse direction. So let's assume that we run Bellman-Ford, an extra iteration, and none of the subproblem solutions change. Now, I warned you there was this edge case when the input graph doesn't have a path from S to all other vertices and you have infinite distances. I'll leave those details to you. So let's just focus on the case when there is a path from S to everything else. And in particular, these subproblem values are going to be finite. So a little notation, I'm going to use lowercase d of a vertex v to denote the common value of its subproblems in the final two iterations, when I equals n minus 1 and when I equals n. So now the plan is we're just going to stare at the formula that we use to evaluate these subproblems. It's right there staring at us in the pseudocode for the Bellman-Ford algorithm. From that, we will get an inequality relating these d values to each other. And from that inequality, we will be easily able to deduce that every cycle of the input graph is indeed non-negative. That's the left-hand side of the statement. So what formula did we use to fill in this extra iteration of the table, the ANVs? Well, we just took the better of, on the one hand, AN minus 1V, the solution for the previous iteration, and then also the best of the candidates that use a last hop WV and concatenate a path with the most n minus 1 edges to W along with that edge WV. Let's also note that with our new notations, these little d values, the common value of a subproblem in the n minus 1 and nth iterations, we can write the left-hand side of this formula as d of v, and in the case 2 subproblems, we can write a n minus 1w as d of w. Now, because the left-hand side of this equation is a minimum over a bunch of candidates on the right-hand side, if we instantiate, if we zoom in on any one candidate on the right-hand side, so any choice of this last hop WV, we get something which is at least as big as the left-hand side. Again, the left-hand side is the smallest of all of the candidates. So in particular, for a given choice of the last hop W comma V, we get that d of V is at most d of W plus the length of the edge from W to V. Really, all this inequality is saying is that one way to get a path from S to V is to take a path from S to W and concatenate the final hop W comma V. The shortest path to V can only be better than this one particular candidate that goes via W. Now remember what it is we're trying to prove. We're trying to prove that the input graph has no negative cost cycles. So let's just pick our favorite cycle, capital C, and show that it has non-negative cost. This is going to be a sneaky application of the inequality that we just wrote down in pink. Specifically, we're going to sum that inequality over all of the edges in the cycle. It's going to be clear if I just rearrange that pink inequality a little bit. So now let's look at the sum of the edge lengths in the cycle capital C. Remember, this is what we want to prove is non-negative. So we sum over the edges W comma V in big C, and for each edge we look at its cost, little c of WV. By the pink inequality, we can lower bound this by a sum over the edges in the cycle capital C of the difference between the d values of that edge, the endpoints of the edge. Notice that for a given arc WV on the cycle, the tail of this arc W, its d value appears with a coefficient of +1, and the d value of the head of this arc v appears with a coefficient of -1. But cycles, of course, have the very special property that every vertex of the cycle appears exactly once as the tail of some arc and exactly once as the head of some arc. So each d value of a vertex on the cycle is going to appear once with +1 coefficient, once with -1 coefficient. So when we get massive cancellation, we're left with just 0. So the cycle capital C has non-negative cost. That was an arbitrary cycle, so it's true simultaneously of all of the cycles in the input graph. That's exactly what we were trying to prove. So again, the presence of negative cost cycles in an input graph is characterized by the behavior of Bellman-Ford in an extra iteration. That's why it's easy to extend the basic algorithm to check negative cycles without affecting the running time. So we've talked a bit about various running time optimizations of the basic Bellman-Ford algorithm. Now let's talk about optimizing the space required by the algorithm. To orient ourselves, let's just think about how much space is needed by the basic algorithm we've been studying thus far. All right, so the correct answer here is the first one, A. The space required by the basic Bellman-Ford algorithm is quadratic in the number of vertices. It's theta of n squared. Why? Well, the space is dominated by the 2D array that we fill in, and there's only a constant amount of space per subproblem, and there's n squared subproblems. Remember, one index is the budget on how many edges we're allowed to use. I ranges from 0 to n-1, and then the other index is just the destination, and there's n of those. So in this video, we will talk about how you can do better, how you can get away with only linear space, not quadratic space. The initial observation is a simple one. Let's just return to the formula that we used to populate all of the entries of the array. So we always take a whole bunch of candidates. What are the candidates? Well, either we can inherit the solution from last iteration, i-1v, or we can choose something to be the last top wv, and then we just paste together the best solution to w from last iteration, so ai-1w, plus we pay for the last top the length of the edge wv. But here's the point. Staring at this formula, which subproblem values do we care about? Well, not that many of them. And in particular, the trait shared by all of the interesting candidates are they're all from the last iteration. The first index in everything on the right-hand side is always i-1. As a consequence, as soon as we've finished one batch of subproblems for some value of I, we've computed AIV for all V, we can throw out the results of all of the previous rounds of subproblems, AI-1, AI-2, and so on. All we need is the freshest batch, the most recent iteration, to correctly proceed. If we do that, the only subproblems we're keeping track of are the ones that we're filling in the current round I, and we're remembering the solutions from the previous round I-1. That means at any given moment in time, we're only keeping track of big O of n different subproblems. And this linear spacebound is even more impressive than it might appear at first. And that's because if you think about the responsibility of our algorithm in this problem, we have to output a linear number of things, right? We're not just outputting one number, we're outputting n numbers. Shortest path distance from S to every possible destination. So the space is really constant per statistic that we have to compute. One thing I'm not going to discuss explicitly, but I think would be a good exercise for you, go back to all of the other dynamic programming algorithms we've discussed, and of course by now there are many, and see which ones you can do a comparable optimization. Which subproblems do you need to keep around to compute the new ones? And if you throw out all the ones that you're not going to need anymore, what does that reduce the space to? For many of the problems that we've studied, you're going to see a big improvement in the space required. So this would be a good time to pause and stop for a few seconds and think about possible negative consequences of this space optimization. So suppose we do this, either in the context of shortest paths, Bellman-Ford, or some other dynamic programming algorithm. We throw out the values of old subproblem solutions that we seemingly don't need anymore to push the recurrence further. Are there any drawbacks to this space optimization? So the answer depends. If all you care about is the value of an optimal solution and not the optimal solution itself, then you may as well just throw out all of these old subproblems that you don't need anymore to push the recurrence further. It's not going to hurt you at all. If, however, you want the optimal solution itself and not just its value, well, how did we actually accomplish that in the past? We had these reconstruction algorithms. How did the reconstruction algorithms work? You took the entire filled-in table and you traced backward through it. In each entry of the filled-in table, you looked at which of the candidates won, which comparison came out the winner when you filled in this entry. That told you a piece of what the optimal solution has to look like, and then you go backward through the table and repeat the process. If you've thrown out most of your filled-in table, how are you going to run this reconstruction algorithm? In the context of the Bellman-Ford algorithm, how are you going to reconstruct shortest paths if you haven't remembered all of the subproblems of all of the previous iterations? And you can certainly imagine in a routing application, for example, you don't just want to know that the shortest path has length 17, you want to know what route should we take to get from point A to point B. So in the rest of this video, I'm going to describe a solution for the Bellman-Ford algorithm. I'm going to show you how we can retain the constant space per vertex guarantee while recovering the ability to reconstruct shortest paths. So the idea is, for a given value of I and a given destination V, we're going to keep track of not just the one piece of information, the length of the shortest path from S to V that uses the most I edges, but also a second piece of information, which is the second to last vertex on such a path. So it's still going to be just constant space per subproblem. So we're going to call this second two-dimensional array B. We're going to call its entries predecessor pointers. Again, the semantics are this pointer points to the predecessor of this destination V on a shortest path from S to V that has the most I edges. Of course, if I is sufficiently small, there may be no such paths from S to V, and in that case, we just have a null predecessor pointer. So for a moment, let's just forget about the space optimization that we're trying to attain, and let's just observe that if we correctly computed these capital B's, then simply traversing predecessor pointers would reconstruct shortest paths. So why is this true? Well, two reasons that you've seen explain other things as well. So the first reason is, remember, we're assuming that the input graph has no negative cost cycle. Therefore, shortest paths have at most n-1 edges. Therefore, the b n-1 v's actually store in them the final hop of a shortest path period with no edge budget from S to V. So in the b n-1 v's, the final batch of predecessor pointers, if we correctly compute them, they are telling us the last hop on a shortest path to V. Now, the other part of the correctness comes from the optimal substructure lemma. So remember, way back when we started talking about shortest paths in their optimal substructure, we said, well, if only we had a little birdie which told us what the last hop of a shortest path was, then the shortest path would just be that last hop concatenated with the shortest path from S up to the penultimate vertex W. And these predecessor pointers are exactly this little birdie. We're storing at V what the last hop is, WV, and so we know that it's just that last hop with the shortest path back to S from W. And by traversing, that's exactly what you do. You just reconstruct the rest of the path apart from S to W. So if we correctly compute predecessor pointers, then they enable this simple reconstruction of shortest paths just by traversal after the fact. So that leaves us with the task of correctly computing these predecessor pointers. It's not hard. I think many of you could just fill in the details yourself, but let me just give a quick rundown. So remember, in general, we have this 2D array capital B. It's indexed by the edge budget I, and it's indexed by the destination V, and we're supposed to fill in BIV with the final hop on a shortest path from S to V that uses at most I edges. And if no such paths exist, then it's just null. For the base case, that's when I equals 0, and here everybody's predecessor pointer is null. So the way we're going to fill in the entry BIV is going to depend on which of the candidates won in the competition to be the shortest path for AIV. In essence, this predecessor pointer BIV is just caching the results of the competition we ran to find the shortest path for AIV. So to make this precise, let's just recall the formula that we used to compute AIV, given the solutions to the last batch of subproblems. Case 1 is when you inherit the solution from the last round, AI minus 1V. In addition, each possible choice for a last hop, w comma v, furnishes another candidate for the optimal solution of this round. What you're going to pay the optimal solution to the subproblem I-1w plus the length of the edge wv. So we're going to fill in the BIV array basically just to reflect what happens when we computed the solution to AIV. In essence, what we're doing in the 2D array B is remembering the most recent vertex W that's responsible for furnishing a new shortest path from S to V. So in case 1, the boring case, where at iteration I we just inherit the solution from the last round, of course in the B entry we just inherit the last hop of the previous round. That is, if we use case 1 to fill in AIV, then we just set BIV to be BI-1V. So the interesting case is when AIV is filled in using case 2 of the formula. That is, when the shortest path from S to V suddenly improves given a budget of I hops as opposed to just I-1 hops. In that case, we're just going to cache the results of the brute force search that we did to evaluate the formula. That is, we just remember the choice of the penultimate vertex W that achieved the minimum in this round. Now notice that just like the formula that we used to populate the capital A array, the original array, to compute these BIVs, all we need to know is information from the last round, information from round I-1. So just like with the A array, we can throw out all of the predecessor pointers that date back before yesterday, before the previous round. Therefore, we again need only constant space per destination V to maintain both the shortest path distance from S to V with the most I hops and the predecessor pointer. So this is great. For input graphs that don't have negative cost cycles, we can not merely compute the shortest paths in constant space per destination, we can also compute the predecessor pointers in that same space, which allows the reconstruction of shortest paths. The one other thing you might want is to handle graphs that do have negative cost cycles. Now, in a separate video, we showed that just checking whether an input graph has a negative cost cycle or not is easily addressed by a simple extension of the Bellman-Ford algorithm. You tack on one extra iteration of the outer for loop, you let I range not just up to n-1, but all the way up to n, and if you see, for some destination v, an improvement in the extra iteration when I equals n, then that guarantees that there is a negative cost cycle, and it's if and only if. But in the same way you might want to actually have the shortest paths, not merely their value, you might want to actually have a negative cost cycle and not merely know that one exists. It turns out you can solve the reconstruction problem for negative cost cycles as well using the Bellman-Ford algorithm and predecessor pointers in exactly the way we've been maintaining them here. I'm not going to talk through all of the details of this solution. I'll leave it to you as a somewhat non-trivial exercise to think through how this really works. But the gist is as follows. So you run the Bellman-Ford algorithm, you maintain predecessor pointers as on this slide. And if the input graph does have a negative cost cycle, then at some iteration you will see a cycle amongst the predecessor pointers. Furthermore, that cycle of predecessor pointers must be a negative cost cycle of the original input graph. This means that detecting a negative cost cycle, if one exists, reduces to checking for a cycle in the predecessor pointers, which of course you can solve using depth-first search at every iteration. At the beginning of the course, we mentioned that the Bellman-Ford algorithm provides the foundation for modern-day internet routing protocols. This video is going to supply a few of the details. So for starters, when you look at the code of the Bellman-Ford algorithm, I hope on an intuitive level it seems like a sort of distributed algorithm in some sense of the word. Right? Think about what you need to compute a given subproblem, A of I comma V. Well, the vertex V just needs to know from each of the possible previous hops, so from each of the vertices that can talk directly to V, what their subproblem solution was on the previous round. So in each round, each vertex in some sense only communicates with immediate neighbors, vertices to which it has a direct connection. Now, as you can imagine, there's a fairly long list of engineering challenges that have to be tackled to move from the basic Bellman-Ford algorithm to a routing protocol that you could conceivably use in practice. So what I'll do here is highlight some of the main issues and what's the high-level solution to those issues. And with those fixes to the basic Bellman-Ford algorithm, we'll actually have something that's surprisingly close to how modern-day internet protocols really work. That said, the discussion here will be necessarily brief and somewhat deliberately naive. So for those of you who want to understand this material at a really nitty-gritty level, I encourage you to buy a networking book, take a networking class, or read more about the topic on the web. So I want to talk about 3 modifications to the basic Bellman-Ford algorithm. I'll discuss them in order from the most trivial to the least trivial. The first and simplest modification to the algorithm is motivated by the fact that routing in the internet is destination driven. Given a piece of data floating around in the internet, you really don't care that much where it came from. What you really care about is where it needs to go. Right? It's exactly the same thing as with snail mail, the way it gets routed around the globe. If I'm on vacation in, say, Croatia, and I put a postcard in the mail, I don't even need to put a return address. I just say the address of my friend who might be back in the States. And then, just based on its destination, this postcard gets routed appropriately. First through local hops within Croatia, then on a plane over the Atlantic Ocean, and then again locally within the US network. Same thing in the internet, based on the destination IP address of a packet, that's how you know which intermediate sequence of routers it has to go through to get to its eventual destination. All you have to do to accommodate destination-driven routing is reverse all of the directions in the Bellman-Ford algorithm. So instead of having a source vertex S out of which you compute all shortest paths, you're going to have a destination vertex T into which you compute shortest paths from all possible origins. Each vertex, rather than storing a predecessor pointer, the final hop on a shortest path from S to that vertex, it's going to store the first hop on a shortest path to the destination T. Now, of course, if you're a router in the internet, you don't want to be optimized purely for a single destination T. You have to be ready to accommodate data bound for anywhere in the internet. So as a result, each vertex stores the shortest path distance and the first hop, not just to a single destination T, but to every relevant destination T, so that it's prepared for any data that it might acquire. So this should sound pretty intense. There's a lot of potential destinations T. There's a lot of IP addresses out there in the world. So a couple comments. So first of all, for most computers in the internet, they're not really responsible for knowing how to get to a lot of the destinations T in the internet. This is because of the hierarchical structure of the internet, right? So if it's just some computer inside the Stanford network, it really only needs to know how to get to other computers inside the Stanford network, of which there aren't that many. And it also has to know how to get to the Stanford gateway router. And if it's data bound for somewhere outside the Stanford network, you just sort of defer the responsibility to the Stanford gateway router and you let it handle it. You just get that far and then it'll take it from there. On the other hand, for the routers embedded in the core of the internet, they really are responsible for knowing how to get to all kinds of different places, basically the entire internet. And their routing tables, guess what? They're really quite big. So the number of entries might be, say, in the hundreds of thousands. So as you can imagine, routing table implementation is something that people who work in networking have thought about a ton. There's interesting hardware optimization, software optimizations, and then people also worry about how can you just make sure routing table size doesn't get too big. So for example, you want to avoid the fragmentation of IP addresses to make sure that you don't need that many distinct entries in the routing tables. Hundreds of thousands is plenty. Thank you very much. You will sometimes hear Bellman-Ford-based shortest path protocols like this one called distance vector protocols. The distance vector that this term refers to is at a given vertex, you have a vector indexed by possible destinations T, and you're keeping track of the shortest path distance in the first hop for all of those destinations. So the second issue we need to address is a little more serious, but it's still not too bad. This issue is asynchrony. And what I mean is, if you look back at our basic Bellman-Ford algorithm, it was synchronous in the following sense. We were careful to structure the outer iteration of the for loop so that all of the subproblems corresponding to value I-1 get solved before any of the subproblems with index I. Now, when you're talking about the internet and you have different routers, different computers running at different speeds, you have different physical connections with different bandwidth, there's no way you're going to keep people in sync. There's no way you can implement synchronized rounds at the internet scale. But what's cool is that the Bellman-Ford algorithm is surprisingly robust to the order in which you solve its subproblems. Really, if you solve them in any kind of reasonable order, you're still going to be computing correct shortest paths at the end of the day. So to explain what I mean, let's change the Bellman-Ford algorithm to be push-based rather than pull-based. So the basic Bellman-Ford algorithm is pull-based in the following sense. For each outer iteration I and each vertex v in this iteration, the vertex v in effect asks its neighbors for their most recent information. So for their subproblem solution values from the last iteration of the outer for loop. We're going to change it to be push-based, which is rather than asking your neighbors for the latest information, whenever you have something new to say, whenever your subproblem value changes, you're just going to go ahead and tell all of your neighbors. You're going to push that information onto your neighbors whether they want it or not. So I'm not going to define this especially formally. It's easy to do. Let me just show you a very quick example which hopefully gives you the gist of the idea. So consider this green network, and suppose we're trying to compute shortest paths from everywhere to T. Remember, we've switched from source-driven to destination-driven routing. So initially, T knows how to get to itself with length 0, and everyone else only has plus infinity. So to get started, the destination T is going to inform all of its neighbors that it can get to itself with a path of length 0. So who does it notify? It notifies V and W. Because U is not directly connected to T, U does not learn this information yet. So because the internet is asynchronous, even though T probably sends out messages at exactly the same time to V and W, telling it about its cool 0 path from it to itself, who knows which of V or W gets that information first. So maybe the line speed is faster to W, and W finds out first that T can get to itself with a path of length 0. At that point, W says, well, cool, I didn't have any path at all previously, but I can get to T with cost only 4, and once I'm at T, I'm done. T can get to itself with cost 0. So W updates its shortest path estimate to the destination T from plus infinity down to 4. So now remember, we're doing this push-based implementation, so W has new information, it has a better shortest path to T, so it needs to tell all of its neighbors. So in particular, it's going to tell the neighbor U that it has a path of length 4 to T. And now remember, still floating around on the internet is this message from T to V, advertising T's empty path from itself of length 0. But again, who knows what happens first? Maybe, in fact, W's message to U arrives before T's message to V arrives. So then U is going to say, oh, cool. Well, if from W to T has cost only 4, I can get to W with cost only 3. So that gives me a path of length 7 all the way to T. Now in this graph, there are no incoming arcs to U, so U doesn't have anybody to notify. And now at some point in the future, the message from T actually arrives at the node V. And so at that point, V says, oh, okay, cool. So I can get to T on an edge of cost 2. From T, I only have to pay 0 to get the rest of the way to T. So I'm going to update my estimate of my distance to T from plus infinity down to 2. V, now that it has a revised estimate, it's responsible for notifying all of its neighbors. So it tells U, it says, hey, U, I can get to T on a path of length only 2. And then U says, well, hey, great, that's actually an improvement. My old path had length 7. I can get to the node V with cost only 1, and V tells me you can get the rest of the way with cost only 2. So that gives me a path of length 3 all the way to T. So in this particular example, this asynchronous push-based implementation of Bellman-Ford did correctly compute shortest paths, and that is in fact true in general in any network. And of course, when I state this fact, I'm assuming that there's no negative cycles. In the context of internet routing, actually, negative cycles aren't a big deal. Usually, you think of all of the edges as having non-negative length in internet routing applications. Why does the algorithm converge eventually? Well, essentially, it's because every single update strictly decreases somebody's estimate of their shortest path distance to the destination T. And there's only a finite number of these configurations you can go through until you finally must be at the correct shortest path distances. So this very crude convergence argument only provides an exponential upper bound on the number of updates that you might need before you correctly compute shortest paths. And in fact, at least in the worst case theoretically, this asynchronous version of Bellman-Ford can require an exponential number of updates before it successfully finds all of the shortest paths. That's a non-trivial problem you might want to think about. So if you have the luxury of implementing the Bellman-Ford algorithm in a synchronous or a centralized setting, you do want to use the synchronous version that we discussed in the basic version. If you're in an asynchronous setting, you don't really have a choice other than to implement it asynchronously. And then, of course, you're hoping you're going to, in your particular network, have convergence time much better than the worst case exponential bound. So the original Bellman-Ford algorithm is from the 1950s, and with the modifications we've discussed to this point, we're up to routing protocols that were deployed as late as the 1970s. So if you want to read more, you can look at the RIP and RIP2 internet routing protocols. And if you really want to be nerdy about it, you can check out the request for comments related to these protocols, RFC number 1058. So what is an RFC? What's a request for comments? Well, this is the mechanism by which the community around the internet sort of vets proposed modifications, proposed protocols. So if you really want to see nitty-gritty details, that's a good place to look. So now let's talk about the final and most serious problem, which is that stuff in the internet, nodes, links, etc., is failing all the time. And while it's true that we just argued that the asynchronous Bellman-Ford shortest path routing protocol is guaranteed to converge to correct shortest paths, that was assuming that the network was static, that no links were coming up and down. So one particularly simple problem in the presence of failures is what's known as the counting to infinity problem. So I'm going to show you a particularly contrived version of this problem just to kind of illustrate the point in the simplest way, but it's quite easy to come up with more realistic examples. And this problem is not just some kind of theoretical flaw in the distributed Bellman-Ford algorithm. This problem really was observed in practice with those routing protocols from the 1970s. So imagine we just have a super simple network, vertices S, V, and T, bidirected arcs from S to V and an arc from V to T. Everything has unit cost, and we're doing routing to the destination T. You might, if you want a more realistic example, think about the arcs between S and V as standing in for longer paths that have multiple hops. In any case, let's imagine that we successfully computed shortest paths on this basic network. So the distance from T to itself is 0, from V to T is 1, and from S to T is 2. Now again, the issue is that links are failing all the time in the internet. So at some point, this link from V to T might go down. So at some point, V is going to notice that its link to T has failed, and it's going to have to reset its shortest path estimate to T to be plus infinity. And in an effort to recover connectivity to T, it makes sense for V to ask its neighbors, do they have paths to T? And if so, how long are they? So in particular, V will poll S, and S will say, oh yeah, I have a path to T of distance only 2. And V says, oh, well, that's great. Currently, my estimate to T is plus infinity. I can get to S with length 1. S says it can get back to T with length 2. So that gives me a path of length 3 to T. Now, of course, the flaw in this reasoning is that S was depending on V to get to T. And now all of a sudden, V circularly is going to use S in its mind to get all the way back to T. So this already illustrates the dangers of naively implementing the asynchronous Bellman-Ford algorithm in the presence of link failures. Where does the name counting to infinity come from? Well, you can imagine that for some implementations of this protocol, S would then say, oh boy, okay, V just revised its shortest path estimate to T to be 3. My next hop was to V, so if V takes 2 longer to get to T, then I'm going to take 2 longer to get to T as well. So at that point, S updates its shortest path distance to be 4. And now this keeps going on. At this point, V says, oh, well, if S is going to take 2 longer to get to T, I was depending on S, so I have to go up by 2, and then S goes up by 2, and V goes up by 2, and so on forevermore. So failures cause problems for the convergence of distributed shortest path routing protocols. Not just the counting to infinity problem, there are others as well. And this is a tough issue. Much blood and ink has been spilled over the relative merits of different possible solutions for dealing with failures. Back in the 1980s, people were largely proposing sort of hacks to the basic protocol. I will give them credit. They had some pretty ridiculous and fun names for their hacks, like Split Horizon with Poison Reverse. But what eventually people converged on is moving from these so-called distance vector protocols to what are called path vector protocols. And what happens in a path vector protocol is each vertex maintains not just the next hop to every possible destination, but they actually keep locally the entire path which is going to get used from V to each destination T. So there's definitely some irony here, because this is essentially the solution to reconstructing optimal solutions in dynamic programming that we've been studiously avoiding this whole time. You might recall when we first started discussing reconstruction algorithms, this was back independent sets of path graphs. We first said, well, you could, in the forward pass through the array, store not just the optimal solution value, but the optimal solution itself. But we argued, well, that's not really the best idea. It wastes time, it wastes space. Much smarter is to just reconstruct an optimal solution by a backward pass through the filled-in table. But what's happening here is this optimized version of the reconstruction algorithm that doesn't use extra time or space is just not robust enough to withstand the vagaries of internet routing. So we are going to the cruder solution where we literally just store optimal solutions, not just the solution value itself. So that explains why this is called a path vector protocol, right? Distance vector protocol, you store the distance for each possible destination. Here we're actually storing a path for each possible destination. So the drawback is exactly what we've been saying all along. If you store the optimal solutions and not just the optimal solution value, it's going to take quite a bit more space. And indeed, doing this blows up the routing tables in routers. That's just a fact. There are two quite important benefits. The first we've already discussed, you're more robust to failures. I'm not going to discuss the details about how you use this extra path information to handle failures better, but certainly in our contrived motivating example, you can see how if S and V actually knew the entire path they were storing to T, they could make sure that they didn't get into this counting to infinity problem. But moving to a path vector protocol doesn't just add robustness, it also enables new functionality. So in particular, passing around entire paths allows vertices to express more complicated preferences over routes than merely what their lengths are. Imagine, for example, you're a small internet service provider and you have a much more favorable contract with AT&T than you do with Sprint. So it costs you much less money to send traffic through AT&T as an intermediary than it does through Sprint. Well, now imagine you're running this distributed shortest path protocol and two of your neighbors offer you two paths to get to some destination T. The first path goes through AT&T, the second path goes through Sprint. And of course, the only reason you know this information is because it's a path vector protocol and you're passing around the actual path and you can see what the intermediate stops are. Well, then you're free to say, oh, well, I'm going to use as my path to T, and this is what I'm going to advertise to other people. I'm going to advertise and store the path that goes through AT&T. I'm going to ignore the one that goes through Sprint. So that is more or less how the Border Gateway Protocol, aka the BGP protocol, works, and that is the protocol which governs how traffic gets routed through the core of the internet. So that wraps up our discussion of how shortest path algorithms dating back to the 1950s has played a fundamental role in how shortest path routing has evolved in the internet over the past half century. So why should we be content computing shortest paths from merely one source vertex to all possible destinations? What if we want to know shortest path distances from every vertex to every other vertex? So the formal definition of the all-pair shortest paths, or APSP, problem is as follows. We are given, as usual, a directed graph G with edges that have lengths C sub E. You can think, if you want, about the special case when all edges are non-negative, but we're also going to be interested in the case where edges can have negative lengths as well. In contrast to the single source shortest path problem, there is no distinguished source vertex. And the goal of the problem is to compute for every pair of vertices U and V the length of a shortest path starting at U and ending at V. So just as with a single source version of the problem, this isn't quite the full story. If the input graph G has a negative edge cycle, then either, depending on how you define shortest paths, the problem doesn't make sense, or it's computationally intractable. So if there is a negative cost cycle, we're off the hook from having to compute shortest path distances, but we do need to correctly report in that case that the graph contains a negative cost cycle. That's our excuse for not computing the correct shortest path lengths. So you know what would make me really happy? If when you see this problem, you thought to yourself, don't we pretty much already have a rich enough toolbox to solve the all-pair shortest path problem? If that's what you thought, that's a great thought, and the answer in many senses is yes. So let's explore that idea, make it precise. In the following quiz, I'm going to ask you, suppose I gave you as a black box a subroutine that solves the single source shortest path problem correctly and quickly. How many times would you need to invoke that black box, that subroutine, to correctly solve the all pairs shortest path problem? So the correct answer is C. You need n invocations of the single source shortest path subroutine, where n is the number of vertices in the input graph. Why? Well, if you designate an arbitrary vertex as a source vertex S and then run the provided subroutine, it will compute for you shortest path distances from that choice of S to all of the destinations. So that computes for you n shortest path distances out of the n squared that you're responsible for. All of the shortest path distances that has this particular vertex S as the origin. So there's n different choices of the possible origin, so you just iterate over all of those choices, invoke the provided algorithm once for each, and boom, you've got the n squared shortest path distances that you're responsible for. So should we be happy with this reduction? Should we be happy with this algorithm that simply runs a single source shortest path algorithm n times, or do we expect to do better? Well, the answer is going to depend. It's going to depend on two factors. First of all, does the input graph have only non-negative edge costs, or does it more generally also have negative edge costs? The second thing we want to look at is whether the graph is sparse, meaning m, the number of edges, is relatively close to n, or is it dense, meaning m is relatively close to n squared. So let's start with a case of just non-negative edge costs. The reason it matters whether or not the edge costs are all non-negative or not is it governs which single source shortest path subroutine we get to use. So if the happy case, all edge costs are non-negative, then we get to use Dijkstra's algorithm as our workhorse. And remember, Dijkstra's algorithm is blazingly fast. Our heap-based implementation of it ran in time m log n. So if you run that n times, your running time is naturally n times m times log n. So in the sparse case, this is going to be n squared log n. In the dense case, this is going to be n cubed log n. So for sparse graphs, this frankly is pretty awesome. You're not going to really do much better than running Dijkstra n times once for each choice of source, of the source vertex. The reason is we're responsible for outputting n squared values, the shortest path distance for each pair u via vertices. And so here, the running time is just that n squared times an extra log factor. The situation for dense graphs, however, is much murkier, and it is an open question to this day whether there are algorithms fundamentally faster than cubic time for the all-pair shortest paths problem in dense graphs. If you wanted to try to convince somebody that maybe you couldn't do better than cubic time, you might argue as follows. There's a quadratic number of shortest path distances that have to be computed, and for a given pair u and v, the shortest path might well have a linear number of edges in it, so surely you can't compute the shortest path between one pair better than linear time, so to do a quadratic number, it's going to have to be cubic time. However, I want to be clear, this is not a proof. This is just a wishy-washy argument. Why is it not a proof? Well, for all we know, we can do some amount of work which is relevant simultaneously for lots of these shortest path problems, and you don't actually have to spend linear on average time for each. As a tale of inspiration, let me remind you about matrix multiplication. If you write down the definition of what it means to multiply two matrices, you look at the definition and it just seems like it's an obviously cubic problem. It just seems like by definition you have to do a cubic amount of work. Yet, that intuition is totally wrong. Beginning with Strassen and then many follow-on algorithms, we now know that there are algorithms for matrix multiplication fundamentally better than the naive cubic time algorithm. If you have a non-trivial approach to decomposing the problem, you can eliminate some of the redundant work and do better than the straightforward solution. Is a Strassen-like improvement possible for the all-pair shortest paths problem? Nobody knows. Now let's discuss the general case input graphs that are allowed to have negative edge lengths. So in this case, we cannot use Dijkstra's algorithm as our workhorse, as our single source shortest path subroutine. We have to resort to the Bellman-Ford algorithm instead, because that's the only one of the two that accommodates negative cost edges. Remember, the Bellman-Ford algorithm is slower than Dijkstra's algorithm. The running time bound that we proved was O of m times n. If we run that n times, we get a running time of m times n squared. How good is a running time of n squared m? Well, if the graph is sparse, if m is theta of n, then this is cubic in n. And if the graph is dense, m is theta of n squared, we're now seeing our first ever, for this course, quartic running time. And I hope you're not really especially happy with the cubic running time bound for the sparse graph case. But now when we're talking about quartic running time, now this really just seems exorbitant. And so hopefully you're thinking there's got to be a better approach to this problem than just running Bellman-Ford n times in the dense graph case. Indeed there is. The Floyd-Warshall algorithm. We'll start talking about it next video. In this video and the next, we're going to develop from scratch an algorithm for the all pairs shortest path problem, rather than by relying on the aforementioned reduction to the single source version of the problem. So in this video, we're going to develop the relevant optimal substructure lemma. In the next video, we'll culminate in a dynamic programming algorithm. It is a famous one, the Floyd-Warshall algorithm. Before developing the optimal substructure, let me just tell you a little bit about where we're going. The optimal substructure we're about to identify will lead to a dynamic programming solution via the usual recipe, which we've now seen over and over and over again. It's going to solve the all pairs shortest path problem in O of n cubed time, so we get a bound independent of the sparsity, n cubed even if the graph has negative edge lengths. This algorithm is known as the Floyd-Warshall algorithm. Last video, we discussed the performance that you get by just running a single source shortest path subroutine n times, and the Floyd-Warshall algorithm is a better solution in many situations. So first of all, for graphs that have general edge lengths, that is, edge lengths that are allowed to be negative, then Floyd-Warshall is looking pretty good. Remember, the previous solution was to run the Bellman-Ford algorithm n times. We can't use Dijkstra's algorithm because that's not generally correct with negative edge costs. And if you run the Bellman-Ford algorithm n times, you get a running time of n squared m. So even in the best case for Bellman-Ford sparse graphs, we're doing just as well with Floyd-Warshall. We've got a cubic running time. And we're doing quite a bit better for dense graphs. There, n times Bellman-Ford would give us n to the fourth, a quartic running time, whereas here we're getting cubic. Now, for graphs with non-negative edge costs, reducing to the single source problem is actually a pretty good solution because Dijkstra is so fast. So if you run Dijkstra n times, your running time is going to be n times m times log n. So for sparse graphs, you'd really want to use Dijkstra n times rather than Floyd-Warshall because you get a running time roughly quadratic in n as opposed to the cubic running time we're going to get here. For dense graphs, it's not so clear. If you run Dijkstra n times, you're going to get a running time which is ballpark cubic, so that's going to be roughly the same as Floyd-Warshall, and you'd expect them to be comparable. It's not clear which one would do better in practice. If you had to choose between those two solutions for dense graphs, you'd really want to code them both up and pick whichever one seemed to do better in your domain. One place you see the Floyd-Warshall algorithm used quite a bit is for computing the transitive closure of a binary relation. And in graph theoretic language, you can think of the transitive closure problem as computing all pairs reachability. So that's a special case of all pairs shortest paths where you just want to know whether the shortest path distance is finite or infinite. For each pair of vertices, you want to know, does there exist a path from the one vertex to the other or not? And if all you care about is the transitive closure problem, if all you care about is one bit of information for each pair of nodes, connected or not, as opposed to more generally what the shortest path length is, then you can do some optimizations in the Floyd-Warshall algorithm to speed up the constant factors. But I'll leave it to you to read up on the web about that if you're interested. Now, I realize that this cubic running time is maybe not super impressive. In general, as we've been talking about dynamic programming algorithms, we've been starting to see for the first time in these courses a proliferation of algorithms which, while polynomial time, while way better than exponential time, you wouldn't really call blazingly fast. We've seen a lot of quadratic running times. Now we're seeing some cubic running times. So that's kind of a bummer, but I am still teaching you the state of the art. As we mentioned this in the last video, it remains an open question to this day whether there are significantly subcubic algorithms that solve the all pairs shortest paths problem. So now let's formalize the optimal substructure in all pairs shortest path, which is exploited by the Floyd-Warshall algorithm. A quick digression first, though. At the beginning of the class, I hope that, if I had shown you this Floyd-Warshall algorithm, you would have said, wow, that's a really elegant algorithm. How could I have ever come up with this? Whereas now that you're approaching the black belt level in dynamic programming and you see just how mechanically the algorithm, this famous algorithm, is going to fall out of the really quite easy optimal substructure, I hope you say, how could I not have come up with this algorithm? Now, I don't mean to take any credit away from the solutions of Floyd and Warshall. There is one really great idea in how they phrase this optimal substructure. Remember, we talked about this before the Bellman-Ford algorithm. It can be tricky to apply dynamic programming to graph problems because there isn't really an ordering in the input. You just get this bag of vertices and this bag of edges, and it's often unclear how to define bigger and smaller subproblems. So the really nice solution in the Bellman-Ford algorithm was to introduce this extra parameter I. I was a budget on the number of edges, or roughly equivalently, the number of vertices that you were allowed to use in a path between the origin and destination for a given subproblem. This naturally induces an ordering on subproblems. The bigger the edge budget, the bigger the subproblem. We're going to do something similar, but even a little bit more stringent in the Floyd-Warshall solution. We're again going to restrict the number of vertices that can appear in the middle of a path between a given origin and destination and a subproblem. But more than just the number of the vertices we're allowed to use, we're going to restrict exactly which vertices, the identities of the vertices, that the algorithm is permitted to use to get from the given origin to the given destination. And in many ways, the restriction we're going to impose is totally analogous to, say, the knapsack problem, where there wasn't an intrinsic ordering on the items, but we imposed one anyways, and then we just look at prefixes of the items. And bigger subproblems were ones with bigger prefixes of items. Here, we're going to impose an arbitrary ordering on the vertices, and in a given subproblem, you're only allowed to use some prefix of the vertices as internal nodes in a path, and then, of course, the bigger the prefix you're permitted to use, the bigger the subproblem. So to be a little bit more formal about it, let's just impose some arbitrary ordering on the vertices capital V, name the vertices 1, 2, 3, all the way up to n, I don't care how. And I'm going to use the notation capital V superscript k to denote the prefix of the first k vertices, vertices 1 through k. So let me start now setting up the optimal substructure lemma. In contrast to the Bellman-Ford case, I'm only going to prove the optimal substructure lemma for input graphs that have no negative cycle. We'll address the case of negative cycles after we're done with the algorithm. Suppose for now there isn't one. So what then are the subproblems going to be? Well, it's going to be quite analogous to Bellman-Ford. In Bellman-Ford, we were solving the single source shortest path problem. So we needed to compute something for each destination. So that gave us a linear number of subproblems. And then for a given destination, we had this parameter I controlling the edge budget. So that was another linear factor. So we had a quadratic number of subproblems. Here it's going to be the same, except we also have to range over all origins. So we're going to get a cubic number of subproblems. Specifically, a choice for the origin, n choices. A choice for the destination, that's n more choices, plus which prefix of vertices we're allowed to use. So that's still another n choices, so cubic total. So now we focus on an optimal solution to this subproblem, by which I mean amongst all paths which begin at the vertex I, end at the vertex j, and strictly in between I and j as internal nodes contain only vertices from 1 through k. Amongst all of those paths, we look at the one with the shortest length. And because we're looking at the case of no negative cycles, we can assume that this path has no cycles. It's a cycle-free path. So rather than state the conclusion of the optimal substructure lemma right now, let me just make sure you understand what one of these subproblems is. So let's suppose that the origin is the vertex that we've labeled arbitrarily 17. The destination j is the vertex we've labeled 10. And let's suppose k at the moment is only 5. Consider the following graph. Imagine this is a little piece of some much bigger graph. Now, I hope it's clear what the shortest path is between 17 and 10. It's the bottom 2-hop path. That path has total length minus 20. On the other hand, for the subproblem we're dealing with, k equals 5. So what that means is we have this extra constraint on which vertices we can use in the middle of our paths. Now, to be clear, this constraint, k at most 5, that can't apply to the origin and the destination, right? I is 17, j is 10, both of those are bigger than 5, but we don't care. Obviously, any path from I to j has to include both the vertices I and j. So the constraint only applies to vertices in the middle of the path, but this bottom 2-hop path, unfortunately, makes use of the node 7. So that path does not obey the constraint. It is not at most 5. So that path is disallowed. We cannot use it. Therefore, the shortest path from 17 to 10 that makes use only of the first 5, the 5 labeled vertices as intermediate ones would be the top 3-hop path, which has the bigger length of 3. Okay, so I hope it's clear what a subproblem corresponds to. It corresponds to a choice of I, the origin. That's, again, just some vertex labeled something from 1 to n. Similarly, there's a choice of the destination, some other vertex j, which is labeled something from 1 to n. And then there's a choice of the bound k, which governs which vertices you're permitted to use internal to your path. So again, the constraint doesn't apply to the endpoints, just the vertices in between the endpoints. And in the subproblem, the choice of k says you can only use vertices 1 through k internal to your paths. So hopefully that makes sense. Let's move on to the full statement of the optimal substructure lemma. All right, so this is actually going to be one of the simpler optimal substructure lemmas that we've seen in a while. We're back to the glory days of only two cases. The first is trivial. If the shortest path from I to j using only vertices 1 through k as intermediaries doesn't even bother to use the vertex k, well, then it better well be a shortest path from I to j that uses internal nodes only from 1 to k minus 1. Now, it's in case 2, it's going to become apparent what a great idea ordering the vertices, looking at prefixes the vertices, is when you're considering the all pairs version of the shortest path problem. Suppose this path P from I to j does indeed use the vertex k in the middle. Well, then we can think of the path P as comprising two subpaths. The first path P1, which starts at I and goes to the vertex k, and then a path P2, which starts at k and goes to the destination j. Now, here's what's cool. So on this path P, the internal nodes between I and j all lie in 1 through k. Moreover, this path P, remember, is cycle-free, so the vertex k appears exactly once, not more than once. So therefore, if we split the path P into these two parts, P1 and P2, internal to P1, strictly in between I and k, there's only vertices between 1 and k minus 1. Similarly, strictly between k and j and P2, there's only vertices between 1 through k minus 1. Thus, both of these paths P1 and P2 can be thought of as feasible solutions to smaller subproblems, subproblems with an even tighter budget of k minus 1 on the internal nodes that are allowed, and these aren't just feasible solutions for smaller subproblems, they're optimal solutions as well. So how slick is that? That the maximum indexed internal node just splits this shortest path into two shortest paths for smaller subproblems. And you know what? At this point, I am so confident in your facility with dynamic programming, I am not going to even bother to prove this statement. You are totally capable of proving this yourself. The argument is really quite similar to Bellman-Ford. I encourage you to do it as an exercise. So now let's compile the optimal substructure we just identified in all pairs shortest paths into a dynamic programming algorithm, and this will be the Floyd-Warshall algorithm. Let me begin with a quiz and ask you to sort out the base cases. So remember, our subproblems actually have three indices. The first index is the origin I, the second index is the destination j, and then there's our budget k, which controls which of the vertices we're permitted to use as internal nodes in a shortest path in this subproblem. So because of these three indices, we're going to be using a three-dimensional array A. So the plan, of course, is to solve systematically all of these subproblems, where the subproblem corresponding to a choice of I, j, and k is just the length of a shortest path starting at I, ending at j, and using intermediate nodes only labeled 1 through k. And what's cool about these definitions is it's clear which are the bigger subproblems and which are the smaller subproblems. That's controlled completely by the index k. So the smallest set of subproblems, the ones where we have to think through the base case, is when k equals 0. So the quiz asks you, how should we fill in a, I, j, 0 for all of the various choices of the origin I and the destination j? And as usual, if there are no feasible solutions, if no paths from I to j make use only of internal nodes 1 through k, then we define this to be plus infinity. All right, so the correct answer is C. So if I and j are the same, then there is a path that starts at I and ends at j, the empty path. It does in fact have no internal nodes at all, and it has length 0. Similarly, if I and j are directly connected and we look only at paths that have no internal nodes whatsoever, well then we're stuck with the cost of whatever the direct edge from I to j is. So we just fill it in with Cij. On the other hand, if I is not equal to j and I and j are not directly connected, then every path from I to j has at least one internal node, so there are no paths from I to j without any internal nodes. In that case, by definition, we assign a value of plus infinity. So having figured out the base cases, it's now a simple matter to write out the full-blown Floyd-Warshall algorithm. In the past, I've been writing down a recurrence as an intermediate step. I think I'm going to skip that step here. We have so much practice with it. I think we can just jump straight to the code. And in the code, we will solve the problem systematically from the smaller values of k to the bigger values of k. And each time we solve a subproblem, we're just going to do brute force search amongst the two possibilities that we identified in the optimal substructure lemma. So we have our three-dimensional array A, and it's three-dimensional because we have three indices for our subproblems. We got to know what the origin is, we got to know what the destination J is, and we got to know how big a prefix K of vertices we have to work with for internal nodes in our paths. The base case is when K equals 0, so we just fill that in a pre-processing step according to the quiz we just solved. And now we have our triple for loop, one for loop for each of the indices. Now, as always, it's important we solve the smallest subproblems first. The subproblem size is controlled by K, so we better put K as the outermost for loop. The order of I and J is irrelevant, but K better go first. So to compute the value of a given subproblem, A, I, J, K, we just take the better, that is the minimum, of the two candidates identified in our optimal substructure lemma. The first candidate furnished by case 1 is just to inherit the solution computed in the last iteration of the outer for loop, that is I, J, K minus 1. So the second candidate is provided by the second case of the optimal substructure lemma. This is where, in the optimal solution to the current subproblem, we actually do use node K internally on the shortest path. In that case, we know what it has to look like. We have to just be taking the optimal solution from the last iteration of the outer for loop from I to K and concatenating that with, that is, adding to it the length of a shortest path computed last iteration of the outer for loop from K to J. So notice that our code does indeed pass the sanity check you should always use. When we evaluate a subproblem, we already have the solutions to all of the relevant subproblems available for constant time lookup. That's because all of them were computed in the last iteration of the outer for loop. There's also not a whole lot to say about the correctness or the running time. Correctness, it's the usual story. The only non-trivial work is in the optimal substructure lemma. That identifies the only possible two candidates for the optimal solution to a subproblem. We're systematically solving all of them, taking the better of the two only possible candidates. As far as the running time, well, how many subproblems are there? Pretty easy to see. Each of our three for loops takes on n different values, so that's n cubed subproblems overall. Pretty clear that we only do a constant amount of work per subproblem. That gives us the cubic running time. So let me wrap up the discussion of Floyd-Warshall algorithm with a couple odds and ends, answers to two frequently asked questions. So question number 1, which frankly I kind of hope you're wondering about, is, well, what's up with input graphs that do have a negative cost cycle? Let's recap what we've done. We stated and proved the optimal substructure lemma only for input graphs that do not have a negative cost cycle. Our correctness argument for the Floyd-Warshall algorithm relied on the correctness of the recurrence, which in turn relies on the correctness of the optimal substructure lemma. So if you feed in some arbitrary graph to the Floyd-Warshall algorithm, it might have a negative cost cycle, it might not. Well, the algorithm is just going to process its n cubed iterations and fill in this three-dimensional array either way. So you're left at the end of the day with this 3D array filled with numbers. And if it just so happened there was no negative cost cycle in the input graph, then you know that the final batch of numbers when k equals n are in fact the correct shortest path distances. But how do you know if the input graph had a negative cycle or not? How do you know whether you can trust this last batch of numbers when k equals n? Well, there's actually a very slick answer to this question, which is all you need to do is scan the diagonal of the numbers computed in the final round. If the input graph does have a negative cost cycle, then for at least one vertex I, you will see a negative number in the entry A of I, n. So let's assume for the moment that this fact is true, that negative cost cycles will show up in the diagonal in the final round of entries. Then I hope it's clear how you can use the Floyd-Warshall algorithm to solve the general version of the all-pair shortest paths problem. Where by the general version, I mean you're given an input graph, it may or may not have a negative cost cycle, and you have to do one of two things. Either you correctly deduce that the input graph has a negative cost cycle, then you're off the hook, or you compute correct shortest paths between all pairs of vertices. So the way you use that using Floyd-Warshall, you just take the input graph, you just run the algorithm, the n cubed iterations, you scan the diagonal, you scan AIIN for all values of I. If you see a negative number, you say, oh, I'm off the hook, there's a negative cost cycle, sorry. And if the diagonal is all zeros, then you return the final batch of AIJNs as the correct shortest path distances. I'm not going to prove this formally, I'll leave that for you to do in the privacy of your own home, but let me just suggest some intuition about why you would expect this to be true. So suppose the input graph does indeed have a negative cost cycle. Pick some arbitrary vertex on that cycle, let's say vertex x. Define vertex y to be the highest label of some other vertex on the cycle. Now, think about the following point in the Floyd-Warshall algorithm in this triple for loop. Think about when the outer iteration, the value of k, is equal to y. So for the first time, the vertex y is eligible to be on internal nodes of shortest paths. And think about in the inner for loops when both I and j are equal to x. So what is the recurrence, what is the formula in the Floyd-Warshall algorithm going to say? It's going to fill in this particular subproblem value, that is capital A of x, y, with the minimum of two things. So first of all, capital A of x, y minus 1. Who knows what that is? But the second candidate, this is the interesting one candidate to fill in this entry will be capital A of x, y minus 1 plus capital A of y, x, y minus 1. That is, one of the candidates for the entry in this diagonal, capital A of x, y, will be the length of a shortest path from x to y, whose all internal nodes are less than y, plus the length of a shortest path from y back to x, whose internal nodes are all less than y. Well, two candidates for such paths are the two halves of this cycle, right? Y we chose to be the largest indexed node anywhere on the cycle. All the other vertices other than x and y have only smaller indices, so there are permissible internal nodes at the previous iteration. So if you take the sum of these two paths, that's just the cycle length, which by assumption is negative. So at this point in the Floyd-Warshall algorithm, if not earlier, when the outer for loop k is equal to y, and when we're looking from x back to x itself, at that point we'll get a negative number. And because these numbers only go down in future iterations of the outer for loop, that negative number will persist till the end of the algorithm. That's why to check for negative cycle, just scan the diagonal of the final batch of numbers. That tells you whether or not there was one in the input graph. So the second frequently asked question concerns reconstruction. Suppose after you run Floyd-Warshall, you actually want to know the actual sequence of edges, that's the shortest path from your favorite origin I and your favorite destination j. So like in the Bellman-Ford reconstruction solution, we're going to have to store a little bit of extra information, a constant amount of information per subproblem. Now in the Bellman-Ford algorithm, we only had one subproblem per choice of destination. The source was fixed. And for each choice of a destination, we remembered the penultimate vertex on a shortest path to that destination. So for Floyd-Warshall, the number of subproblems is indexed by origins and destinations. And so for each choice of an origin and destination, we're again going to remember some other vertex on a shortest path. But the vertex we remember might not be the second to last one. It might not be the last hop. Rather, what we're going to remember is the highest index vertex on a shortest path from I to j. So I'm going to call this additional information a two-dimensional array capital B. This is indexed just by the choice of the origin and the choice of the destination. And again, the semantics is we want the ij entry of this array to be the max label of any internal node on a shortest ij path. So two things we have to understand. So first of all, how do we compute all of these bij values on the forward pass of the Floyd-Warshall algorithm without affecting its running time? Secondly, if we successfully compute all of these bij's on the forward pass, how do we reconstruct shortest paths by going backward through the filled-in table? So this is all analogous to Bellman-Ford. In Bellman-Ford, we showed that on the forward pass, you could maintain the predecessor pointers. It wasn't a big deal. Just when you recompute shortest paths in a given round of subproblems, if you compute some new shortest path value, i.e. you don't just inherit that solution from the previous round, you just figure out which vertex was responsible for it, and you remember that as your predecessor. And then given the predecessor pointers are correctly computed, you just trace back pointers to reconstruct shortest paths. So here, how do you compute them on the forward direction? Well, remember in the recurrence that we used to fill in the three-dimensional array A, there's two possibilities. Either you just inherit the solution from the previous iteration. That's kind of the boring case. And the interesting case is when you actually use the newly available vertex K in a shortest path from I to J. So whenever you use that second case of the recurrence to reset the value in the three-dimensional array A, at that point you reset the corresponding Bij value to the current value of K. So that is just on the forward pass of Floyd-Warshall, you always remember the last vertex responsible for changing your shortest path distance between I and J. So now let's suppose you've coded up this extension of the forward pass of Floyd-Warshall correctly so that at the end of your triple for loop, you have accurate computations of all of these Bij values. That is, for any origin and destination, you have a little birdie, the two-dimensional array B, that will just tell you in constant time what is the max labeled vertex internal on a shortest IJ path. Well, maybe you really want to know your favorite source is 23, your favorite destination is 17, and you want to reconstruct a shortest path from your oracles, your filled-in tables. So you look into the entry 23, 17 into the B array. This little birdie, this filled-in table, tells you the max labeled vertex on a shortest path between 23 and 17. Maybe it tells you it's the vertex 43. So it promises you that the shortest path comprises 23 on one end, 17 on the other end, a bunch of stuff in the middle, the largest of which is 43. Well, then you're like, okay, cool. Now I know what the shortest path has to be. It's a shortest path from 23 to 43 plus a shortest path from 43 to 17. And you just reconstruct those two shortest paths recursively in exactly the same way. This has got to terminate because at the end of the day, the shortest path is going to have at most n vertices, and you're figuring out one of those vertices every time you do a recursive call. Let's now proceed to the final algorithm for the all-pair shortest path problem that we're going to discuss. It's called Johnson's algorithm, and the algorithm shows something pretty amazing. It shows that even in graphs with negative edge lengths, the all-pair shortest path problem can effectively be reduced to just n invocations of Dijkstra's algorithm, even though Dijkstra's algorithm for correctness needs non-negative edge lengths. So this video will discuss the key idea behind Johnson's algorithm. We'll then proceed to the algorithm itself, and this idea is a way of using vertex weights to reweight shortest path lengths. When we began our discussion of the all-pair shortest path problem, we observed that the problem reduces to n invocations of a suitable subroutine for the single source version of the problem, simply by iterating over all n choices for the source vertex. The running time you get from this reduction is evidently n times the running time of the single source subroutine. And the running time of the subroutine is going to depend on whether your graph has non-negative edge lengths or not. If you're in the lucky case where the graph has non-negative edge lengths, you get to use Dijkstra's algorithm, which runs blazingly fast, almost linear time, m, the number of edges, times log n. If you're dealing with a graph with general edge lengths, then the running time was not so good. It would be n times the Bellman-Ford running time, which itself is mn. At the end of the day, you get a running time of nm log n for the non-negative edges case, or n squared m for the general edge lengths case. And now that we know about the Floyd-Warshall algorithm, which runs in big O of n cubed time, there aren't a whole lot of reasons to care about this solution in general edge lengths that runs Bellman-Ford n times, except perhaps the fundamentally distributed nature of that computation. Johnson's algorithm remarkably shows that the same running time we get here for the non-negative edge length case, n times m times log n, we can get equally well for graphs that have general edge lengths. Specifically, Johnson's algorithm shows that the all-pair shortest path problem in graphs with general edge lengths reduces to one invocation of the Bellman-Ford algorithm, followed by n invocations of Dijkstra's algorithm. As we know, the Bellman-Ford algorithm runs in big O of m times n time. N invocations to Dijkstra's algorithm is going to be n times m times log n. Putting it together, we see that the n invocations of Dijkstra dominate just barely, so the overall running time we'll achieve is big O of nm log n, exactly the same running time we were getting for the non-negative edge length case. So this should probably sound a little too good to be true. How on earth can we reduce the shortest path problem with general edge lengths to the special case where all the edge lengths are non-negative? Indeed, this is a trick that we actually thought some about in part 1, for those of you who are alumni of that course. Suppose you have the single source shortest path problem and you've got a graph with some negative edge lengths. A very natural instinct is to say, well, come on, that can't be that big a deal. Let's just shift the edge lengths so they become non-negative and then compute shortest paths. So if you have some graph where the most negative edge length is -5, why not just add 5 to the length of every single edge? Now you have a new graph, non-negative edge lengths, and you just run Dijkstra's algorithm. Big deal. So this quiz asks you to think about this edge shifting trick in general. Suppose you have a graph and there's a particular source S and destination T you're looking at, and suppose you add some constant number, capital M, to the length of every single edge of the graph. Under what conditions will that preserve the shortest path between S and T? All right, so the correct answer is C. Of the listed conditions, the only one that guarantees that adding a constant m to every edge length preserves the shortest path between a pair of vertices S and T is that all of the paths between that pair of vertices have the same number of edges. And maybe the easiest way to see this is just with a simple example. So consider this simple pink network where there's an S and a T and there's two paths between them, one with 2 hops each of cost 1, one with 1 hop of cost 3. Now evidently in this graph the shortest path is the one that goes through the vertex V. That has length 2, the other one has length 3. Now suppose we add a fixed constant, let's say the constant 2, to every one of these edges. In that case, the 2 edges on top, their lengths increase to 3. The edge on the bottom, its length increases to 5. And you'll see that after we've shifted all of the edge lengths, we've actually changed what the shortest path is. It used to be the 2-hop path on top. Now it's the 1-hop path on bottom. That has length 5. The 2-hop path on top now has length 6. So this shows that the answers A, B, and D are all incorrect. Why is C correct? Well, suppose it was the case that between the vertex S and T, every single path in the graph had exactly the same number of edges. Say every path had 12 edges. Well, then when you add a constant to every edge's length, every path between S and T, their length goes up by exactly the same amount. It goes up by 12 times m if each of the paths have 12 edges in it. So if every single path between S and T goes up by exactly the same amount, well then the shortest path remains exactly the same. The ranking of the lengths of the various paths is exactly the same because we've added exactly the same number to all of them. So the broader point here is that if we want to find a transformation of the lengths of a graph that reduces the general edge length case to the non-negative edge length case, we need to aspire toward transformations that preserve what shortest paths are, and this transformation is not it. There's no reason for you to expect that there'd be any useful transformations of this form, any shortest path preserving transformations that are non-trivial, but such transformations do exist. That's the reweighting technique, which we'll start exploring in the next quiz. So in this quiz, we're again going to think about one of our usual directed graphs. Every edge has a length, and the lengths can be arbitrary real numbers. Here is the twist. For each vertex V, there's going to be a number P sub V associated with that vertex. Don't worry about where these P sub V's come from. We'll discuss that later. Just think of it as any old number. Could be 7, could be -5, whatever. Just one number per vertex. The key idea behind the reweighting technique is to use these n numbers, one weight per vertex, P sub V, to use these n numbers to shift the edge lengths of the graph. I'm going to use C prime to denote these shifted or transformed edge lengths. Here's the exact definition. Consider an arbitrary edge E of this graph G. Let's say the edge goes from the tail U to the head V. The new length, C prime of E, is defined as the original length, CE, plus the weight of this edge's tail, so plus P sub U, minus the weight associated with this edge's head, that is minus P sub V. So for example, consider an edge from U to V that original length is 2, and let's say the weights associated with its tail and head are -4 and -3. Remember, these vertex weights can be arbitrary numbers, positive or negative. Well then, the shifted weight C prime is going to be, by definition, 2 plus -4 minus -3. This, of course, is just equal to 1. So that's the setup. Here's the quiz question. I want you to think about some fixed path, capital P. Let's say it starts at a vertex S and it ends at a vertex T. Now, capital P may or may not be a shortest path. I don't care. It's just any old path starting at S, ending at T. So suppose in the original network, with the original edge lengths C sub E, the total length of this path P was capital L. What is its new length, L prime, under these new edge lengths, C prime? So the correct answer is C. Under the new edge lengths C prime, the path P's length does not in general remain the same, but it shifts by a predictable amount, namely the difference between the node weights associated with S, the origin of the path, and T, the destination of the path. This follows by a simple calculation. So the new length of the path P is, of course, just the sum over the modified edge lengths, the sum over the C primes of the edges in P. So now we just expand each term in terms of its definition. So remember, the new edge length C prime of E is just the original length CE plus the weight associated with the edge's tail, U, minus the weight associated with its head, V. Now consider a vertex other than S or T on this path, some internal vertex on the path. So such a vertex is going to be the tail of exactly one edge of P, and it's going to be the head of exactly one edge of P. So its vertex weight is going to show up with a coefficient of +1 once, and it will show up with a coefficient of -1 once. Obviously those two terms will cancel. So the only vertex weights that matter when we evaluate the sum is the weight of the origin S and the weight of the destination T. The S only shows up once, and it shows up as a tail, so its vertex weight shows up with a +1 contribution. So that's where the P sub S term comes from. Symmetrically, the destination T only shows up once with a -1 coefficient, so that's where the -T comes from. So when the dust settles, all that we're left with is the sum of the original edge lengths that we're using the notation capital L for, plus this shift term, plus P sub S minus P sub T. All right, so now that we've slogged through the algebra, let me explain to you why we went through that exercise. What is the potential application of this reweighting technique? So what did we just learn about the reweighting technique? Well, fix a graph and fix an origin vertex S and a destination vertex T. What we just learned is that when you reweight using these vertex weights, you shift every single ST path by exactly the same amount. The length of every ST path, shortest or otherwise, changes by exactly the quantity P of S minus P sub T. So this is now starting to sound pretty cool, because let's remember our first quiz. In our first quiz, we explored what happens when you just add a fixed amount capital M to every edge of a graph. We noticed it doesn't work in the sense that it can change the shortest path. Why can it change the shortest path? Well, different paths have a different number of edges, so if you add some fixed amount to each edge, you change different paths by different amounts. That can screw up the shortest path. If you're lucky, and all of the paths between an S and a T have exactly the same number of edges, then you shift them all by exactly the same amount, and you preserve the ordering of the paths. But what do we see here? We see that under no assumptions whatsoever about what the paths between S and T like, node reweighting shifts every single path from S to T by exactly the same quantity, the difference between PS and PT. Well, since reweighting changes the length of every path by exactly the same amount, that means it preserves the shortest path. Whatever was the shortest path previously is still the shortest path after we've done reweighting. So what? Why is this interesting? Well, let's dream big. Suppose we could actually come up with vertex weights that transformed the problem into one that we don't know how to solve blazingly fast into one that we do know how to solve blazingly fast. That is, what if we can find vertex weights that change an arbitrary instance that in general has negative edge lengths into a shortest path problem where all of the edge lengths are now non-negative? So if such a transformation existed, I hope that its use would be clear. This would transform an instance of shortest paths where it seems like we're stuck with the Bellman-Ford algorithm because we start with negative edge lengths, and it transforms it into an easier one where we can apply Dijkstra's shortest path algorithm. Now, this best case scenario should sound like a free lunch to you. Why do we think we can do basically a trivial amount of work, just the simple shift of the edge lengths, and transform a seemingly harder problem, shortest paths with general edge lengths, into an easier one, shortest paths with non-negative edge lengths? The catch, of course, is to figure out which vertex weights to use. How do you know the magical edge weights that transform the general edge lengths into the non-negative ones? Actually, more fundamentally, why do we even think that these vertex weights exist? Maybe no matter how you pick the vertex weights, it's impossible to transform all of the edge lengths so that they become non-negative. Well, it turns out, as long as the graph has no negative cycle, which we know is essential to compute shortest paths, if there's no negative cycle, there do always exist magical choices of the vertex weights P sub v that transforms all of the edge lengths to be non-negative. Now, it's not trivial to compute them. You have to do some work, but it's not a prohibitive amount of work. In fact, one invocation of the Bellman-Ford algorithm will be sufficient. Johnson's algorithm puts those ideas together. That'll be the next video. In this video, we'll cover Johnson's very cool algorithm. It shows how to use the reweighting technique we introduced in the last video to reduce the all-pair shortest path problem in graphs that can have negative edge lengths to a single invocation of the Bellman-Ford shortest path algorithm, followed by n invocations of Dijkstra's shortest path algorithm. We concluded last video daydreaming about this best case scenario where we have a graph with negative edge lengths, but somehow we come up with these magical vertex weights that transforms all of the edge lengths to be non-negative. And it turns out that the magical vertex weights which will realize this best case scenario are best computed by a shortest path algorithm. So before describing Johnson's algorithm in general, let me just walk you through some of the steps in an example. So I've drawn a directed graph with 6 vertices and 7 edges. I've annotated each edge with its cost in blue. Notice that some of the edges do indeed have negative costs, so it is not currently an option to run Dijkstra's algorithm on this graph. There is no negative cycle, however, in this graph. It only has one cycle, the directed triangle at the top, and its overall cost is 1. So we could run the Bellman-Ford algorithm on this graph if we wanted. So our strategy is to compute a magical set of vertex weights so that when we transform the edge lengths using the reweighting technique described in the previous video, we wind up with a graph that now has only non-negative edge lengths. So where do these vertex weights come from? Well, the great idea in Johnson's algorithm is to compute them using a subroutine for the single source shortest path problem. To implement this, we need a well-defined instance of the single source shortest path problem. In particular, we need a source vertex. So that's a pretty good idea. There's only one small problem with it, which is that when you pick your arbitrary source vertex, it might not be able to reach all of the other vertices. And to get our magical vertex weights, we're really going to want finite shortest path distances from our arbitrary source to everybody else. For example, in the graph that I've drawn here on the slide, it doesn't matter which of the 6 vertices you choose as your source vertex, you will not be able to reach all of the other 5. So how do we get around this issue? Well, with a simple hack. We're just going to add a new vertex, so a 7th vertex in this example, and we're going to connect this new vertex, which I'm going to just call S, to all of the original vertices with a direct arc of length 0. We are then going to compute shortest paths from this new artificial source vertex S to all of the vertices from the original graph. Notice that by construction, we're going to get a finite shortest path distance from S to all of the vertices. We've installed a direct path from S to everybody else. Notice that because this new vertex S has no edges going into it, it's effectively invisible from the perspective of all of the original vertices in the graph G. So in particular, the shortest path distance between any pair of vertices U and V in the original graph is unchanged by this addition of the vertex S. Similarly, whether or not G has a negative cycle is unaffected by the addition of the vertex S. The next step of Johnson's algorithm is to invoke a single source shortest path algorithm using this newly added vertex S as our source vertex. Now, in this example, and in general, we're thinking about the case of negative edge lengths, so we're not going to be able to use Dijkstra's algorithm to solve this single source version of the problem. We're going to have to use the Bellman-Ford algorithm to do this computation. So let's now go ahead and figure out what are the shortest path distances from S to the other 6 vertices in this graph on the slide. So let's start with the vertex A. What's the shortest path distance from S to A? Well, it's certainly no worse than 0. There's a path directly from S to A of length 0. And indeed, in general, all 6 of the shortest path distances that we compute will be 0 or less. So the question is there a path from S to A that is negative, that's better than 0? Well, what are the other options? We could go from S to C at length 0, but then we'd pay 4 to get back to A. So that has length 4, so that's no good. A little bit better, but still not good enough, would be to zip straight from S to B. That has length 0. From B to C, now we're down to -1, but then we have to go from C to A, and so we add 4, so we get 3. So we conclude that the shortest path from S to A is indeed the direct one-hop path of length 0. Most of the other vertices are more interesting, however. Think, for example, about vertex B. We could, of course, zip straight from S to B along a path of length 0, but we can get shorter than that. If we go first from S to A at length 0, and then from A to B, then that path has combined length -2, and that is, in fact, the shortest path distance from S to B. The shortest path distance to C is just to take that same shortest path to B and then concatenate the edge of cost -1 from B to C. That is, the shortest path from S to T goes S to A to B to C for a combined length of 0 plus -2 plus -1, -3 in all. So now let's move to the bottom of the graph. The vertex Z is pretty easy to think about. There's only one path in the entire graph. That's the direct one from S to Z. So Z is just going to have the trivial shortest path distance of 0. So now for the vertex Y, you got a bunch of different options. You could, of course, go straight from S to Y at length 0, but there's a lot of things better than that. You could also go from S to Z, and then along the -4 arc to Y. That would give you a path of length -4, but you can do even better than that by going first to A, then to B, then to C, and then to Y. So that gives you a path whose edge costs are 0, -2, -1, and -3. That gives you a combined total of -6, the shortest path distance to Y. Similarly, the shortest path to get to X, the best thing to do is to accumulate all of the negative weight at the top of the graph, go via vertex C, and it's true you have to pay the cost of 2 to get from C to X, but you still end up with a net length of -1, which outperforms the direct 0-length path from S to X. Now, the brilliant insight in Johnson's algorithm is that this shortest path computation is extremely useful. In fact, these computed shortest path distances are exactly the magical vertex weights that we're seeking. They're going to transform all of the edge lengths from general to non-negative. So let's define the weight P sub V of a vertex V from the original graph, that is one of the 6 vertices in this example that we started with, as the shortest path distance we just computed from the extra vertex S to that vertex V. What I want to do next is see the effect of reweighting using these vertex weights. So to do that, let me redraw the example. So let's recall the formula for the reweighting technique. Given vertex weights like these, you define the new length C'E of an edge E, say from U to V, as its original length CE plus the weight of its tail, P sub U, minus the weight of its head, P sub V. So let's just do this computation for each of the 7 edges. Let's start at the top, edge A, comma B. So we start with its original length -2. We add the weight of the tail, so we're adding 0. And then we subtract the weight at the head, so we're subtracting -2. That is, we're adding 2. So we get -2 plus 2, or 0, for the new length C'E for the edge A, comma B. Similarly, for the edge B, comma C, we take the original length -1, we add to it -2, and then we subtract -3. That is, we add 3. And again, it all cancels out. We get 0 for the new cost of arc B, comma C. For the arc C, comma A, we take the original length 4, we add -3, and we subtract 0. So the arc C, comma A has a strictly positive shifted length. It's now 1. If we look at the arc C, comma X, we take the original length 2, we add -3, and we subtract -1. So that again all cancels out, and C, comma X has a new cost of 0. Same thing happens with the arc C, comma Y. We start with -3, we add another -3, we subtract -6, that gives us 0. For the arc Z, comma Y, we start with 1, we add 0, we subtract -1, so we get a new cost of 2. on the arc z comma x. Finally, for the arc z comma y, we start with minus 4, we add 0, we subtract minus 6, that is, we add 6, so that gives us a new length of 2. So I don't expect you to have intuition or semantics for the computations that we just did, but at least in this example, the proof is in the pudding. We just used these shortest path distances as weights, and reweighting magically made all 7 edges have non-negative edge lengths. They all have length either 0, 1, or 2. So what we've now done, at least in this example, is realize the best case scenario we were dreaming about. Remember what the key point of the reweighting technique video was. We pointed out that reweighting preserves shortest paths. If you have some vertex weights, some p sub v's, you change all the edge lengths by reweighting. For every origin s and every destination t, you shift the length of every st path by exactly the same amount, by p sub s minus p sub t, the difference between the vertex weights at the origin and the destination. So by changing all paths by exactly the same amount, you preserve which path is the shortest. So that's a cute party trick. It's not really clear it would be useful, but we were hoping that maybe reweighting in a shortest path preserving way could allow us to transform the general edge lengths version of a shortest path problem to the non-negative edge lengths version of the problem, so that we are not stuck with a slower Bellman-Ford algorithm, and instead we get to use the faster Dijkstra's algorithm. And that's now exactly what we can get away with here, at least in this example. We did the transformation, the new graph has only non-negative edge lengths. Now we can just run Dijkstra's algorithm once for each choice of the source vertex to compute all of the shortest path distances. We're now well positioned to state Johnson's algorithm in its full generality. The input, as usual, is a directed graph G. Each edge has an edge length C sub B. It could be positive or negative. The input graph G may or may not have a negative cost cycle. As usual, when we talk about solving a shortest path problem, we mean that if there is no negative cost cycle, then we have no excuse, so we better correctly compute all of the desired shortest paths, in this case between all pairs of vertices. If there is a negative cost cycle, we're off the hook. We don't have to compute shortest paths, but we need to correctly report that the graph does indeed have a negative cost cycle. Step 1 is the same hack that we used in the example. We want to make sure that there's a vertex from which we can reach everybody else. So let's just add a new one that by construction has that property. So we add one new vertex, a little s. We add n new edges, one from s to each of the original vertices, and each of those new n edges has length 0. We're going to call this new bigger graph G prime. The second step, just like in the example, is to run a shortest path computation using this new vertex S as the source. Since the graph G in general has negative edge costs, we have to resort to the Bellman-Ford algorithm to execute this shortest path computation. Recall that the Bellman-Ford algorithm will do one of two things. Either it will correctly compute the shortest path distances that we're after from the source vertex S to everybody else, or it will correctly report that the graph it was fed, namely G prime, contains a negative cost cycle. Now, if G prime contains a negative cost cycle, that cycle has to be in the original graph G. The new vertex S that we added has no incoming arcs at all, so it certainly can't be on any cycle. So any negative cycle is the responsibility of the original graph G. Therefore, if Bellman-Ford finds us a negative cost cycle, we're free to just halt and correctly report that same result. So from here on out, we can safely assume that G and G prime have no negative cost cycle, and therefore that the Bellman-Ford algorithm did indeed correctly compute shortest path distances from S to everybody else. As in the example, we are going to use these shortest path distances, all of which are finite by construction, as our vertex weights, our p sub v's. We then form the new edge lengths, the C primes, in the usual way. C prime of an edge E going from U to V is the original length CE plus the weight of the tail P sub U minus the weight of the head P sub V. In the example, we saw that the new edge lengths C prime were all non-negative. We will shortly prove that that property holds in general. If you define your vertex weights in terms of shortest path distances from the new vertex S to everybody else in this augmented graph G prime, it is always the case that your new edge lengths will be non-negative. Assuming that for now, it makes sense to use Dijkstra's algorithm n times, once for each choice of the source vertex, to compute all pairs' shortest paths in the graph G with the new edge length C prime. In a particular iteration of this for loop, say when we're using the vertex U as the source vertex, we're going to be computing n of the shortest path distances that we care about from U to the various n possible destinations. And let's call those shortest paths computed by Dijkstra in this iteration d prime of U comma V. So perhaps you're thinking that at this point we're done, right? We transformed the edge lengths using reweighting to make them non-negative, and as we know, once things are non-negative, n Dijkstra's and you're good to go. But there's one final piece of bookkeeping that we have to keep track of. So the shortest path distances that we compute in step 4, these d primes, these are the shortest path distances with respect to the modified costs, the C primes. And what we're responsible for outputting is the shortest path distances with respect to the original lengths, the C's. But fortunately, there's a very easy way to extract the true shortest path distances from the D primes, from the shortest path distances relative to the modified costs. We know the D primes are wrong. They're computed with respect to the wrong costs, but we know exactly what they're off by. So the D primes are off by exactly P sub U minus P sub V amount. So to go from the D primes back to the shortest path distances that we really care about, we just need to subtract that term back off. And that's step 5. That completes the description of Johnson's algorithm, which in effect is a reduction from the all pairs shortest path problem with general edge lengths to n+1 instances of the single source version of the problem, only one of which has general edge lengths, n of which have only non-negative edge lengths. Analyzing the running time of Johnson's algorithm is straightforward. Let's just look at the work done in each of the 5 steps. In step 1, we just add one new vertex and n new edges, so that takes O of n time to accomplish. In step 2, we run the Bellman-Ford algorithm, so we know that takes O of m times n time. In step 3, we have to compute the modified costs, but given the shortest path distances computed by Bellman-Ford, that's constant time per edge, or O of m time overall. In step 4, we run Dijkstra's algorithm n times, and the running time of one invocation is m times log n. In step 5, we do constant work for each choice of u and v, so O of n squared work overall. So you can see that step 4 dominates, and the running time is equivalent to n invocations of Dijkstra's algorithm m times n times log n. As usual, when discussing graph algorithms, I am thinking about the graph as at least being weakly connected. I'm thinking of the number of edges m as being big omega of n. So why is this running time so cool? Well, 2 reasons. The first reason is that for sparse graphs, this solution blows away the previous algorithms that we had that could handle negative edge lengths. The 2 previous solutions that we knew that you could use with graphs with negative edge lengths were either run Bellman-Ford n times or use the Floyd-Warshall algorithm. And in sparse graphs, where m is big O of n, both of those solutions run in cubic time, O of n cubed time. This solution for sparse graphs, when m is big O of n, is O of n squared times a log n factor. So it's way better than either using Bellman-Ford n times or using Floyd-Warshall. The second reason this running time is so cool is that it matches the running time we were getting already in the special case when edge lengths were non-negative. So this is very different than how we were conditioned to think about the world when we talked about single source shortest path problems. Remember, in those problems we have Dijkstra's algorithm, which only handles non-negative edge lengths but runs in near linear time, and there's no algorithm known for single source shortest paths that's near linear that can handle negative edge lengths. The Bellman-Ford algorithm certainly is not near linear running time. That's big O of m times n. Johnson's algorithm shows that while negative edge lengths are indeed an issue, they can be handled in one shot using just one invocation of Bellman-Ford. While the Bellman-Ford algorithm is indeed quite a bit slower than Dijkstra's algorithm, it's only roughly a factor of n slower. So one invocation of Bellman-Ford doesn't change the overall running time when we already have to do n invocations of Dijkstra's algorithm, even in the special case of the problem where all of the edge lengths are non-negative. So that is why for all pair shortest paths, we see a convergence in the performance of algorithms that solve the problem in general and algorithms that only solve the problem in the special case of non-negative edge lengths. The missing piece to the correctness argument is understanding why, in general, the modified edge lengths, the C'(e)s, are guaranteed to be non-negative. We saw that they were non-negative in a specific example, but we have not yet proved it in general. We'll do that on the next slide. Assuming for the moment that that is true, that the modified edge lengths are indeed non-negative, and therefore when we invoke Dijkstra, it will correctly compute shortest paths, we're pretty much done. In particular, recall that we had a quiz in the previous video where we analyzed the ramifications of reweighting. And we saw that if you reweight using particular vertex weights, some p sub v's, then for a given choice of an origin u and a given choice of a destination v, every single uv path has its length changed by exactly the same amount, by a common amount, namely the difference between u's vertex weight p sub u and the destination v's vertex weight p sub v. So that means when we invoke Dijkstra's algorithm in step 4, it indeed gets the shortest paths correct. The shortest path distances are incorrect, but we know exactly how much they're off by. They're off by pu minus p sub v, and that is corrected for in step 5. So that's why assuming correctness of Dijkstra's algorithm, which in turn relies on non-negativity of the modified edge lengths, the end result of Johnson's algorithm is indeed the correct shortest path distances. To finish the analysis of Johnson's algorithm, all that remains is to prove the following claim, which is that for every single edge of the graph, its length after we do reweighting is non-negative. So the proof, in fact, is not hard. It follows quite easily from properties of shortest path distances. So fix your favorite edge, E, let's say going from U to V. The vertex weights are, by construction, just shortest path distances from the vertex little s, where remember s is the extra source vertex that we added to the original input graph G. So by the way we constructed the graph G', there is at least one path from this auxiliary source vertex S to every other vertex. So there is some shortest path from S to U. Let's call it capital P. By definition, the length of capital P has to be little p sub u. It's a simple matter to obtain from this path capital P, which goes from S to U, a path which goes from S all the way to V, namely just concatenate the edge UV as a final hop. The length of this path, which goes from S to V, is of course just the length incurred going from S to U, which is just P sub U, plus the length of the final hop, which is just the length of this edge, C sub UV. Now this is just some old path from S to V. The shortest path from S to V can, of course, only be shorter. And remember, P sub V, the vertex weighted V, is by definition the length of a shortest path from S to V. And now we're good to go, because the modified length of this edge C, that is C' sub E, is just the difference between the right-hand side of this inequality and the left-hand side. So that's why the difference is guaranteed to be non-negative. Since this was an arbitrary edge, it holds for all of the edges. That completes the proof and the analysis of Johnson's algorithm. In this video, we'll begin our study of our final topic. First of all, what are NP-complete or computationally intractable problems? And second of all, what are some good strategies for approaching them algorithmically? Let's begin by formally defining computational tractability via polynomial time solvability. That is, we're going to define the complexity class P. As you know from the past several weeks of hard work, the focus of these design and analysis of algorithms courses is to learn practical algorithms and relevant supporting theory for fundamental computational problems. By now we have a very long list of such problems: sorting, searching, shortest paths, minimum spanning trees, sequence alignment, and so on. But the sad fact is, I've given you a quite biased sample thus far of computational problems, and for many important computational problems, including ones you are likely to run into in your own projects, there is no known efficient, let alone blazingly fast, algorithm for solving the problem. And inasmuch as the focus of these courses is what you can do with algorithms rather than what you can't do, it would nevertheless be fraudulent, I think, to teach you about algorithms without discussing the specter of intractability that haunts the professional algorithm designer and the serious programmer. In the same way, your programmer toolbox should include lots of different design paradigms like dynamic programming, greedy algorithms, divide and conquer, lots of different data structures, hash tables, balanced search trees, and so on. That toolbox also should include the knowledge of computationally intractable, that is, NP-complete problems. Maybe even how to establish problems are NP-complete. And again, this is because these problems are likely to show up in your own projects. It is not uncommon that a graduate student at Stanford will come into my office asking for some advice, how to approach a problem that's come up in their own project from an algorithmic perspective. Very often, after they've sketched the problem for 2 minutes, 5 minutes on my whiteboard, it's very easy to see that it is in fact an NP-complete problem. They should not seek out an efficient, exactly correct algorithm, and instead they should resort to one of the strategies for dealing with NP-complete problems that we'll be discussing later. So in the next sequence of videos, my goal is to formalize the notion of computational intractability through the definition of NP-completeness, and also give you a couple of examples. The relatively brief discussion that I'm going to give you of NP-completeness is no substitute for a proper study of the topic. I encourage you to seek out a textbook or other free courses on the web to learn more. And indeed, NP-completeness, I think, is a topic worth learning at least twice from multiple different perspectives. And indeed, those of you who have studied it before, I hope you find my treatment somewhat complementary to previous treatments that you might have seen. Indeed, NP-completeness is really one of the most famous, important, and influential exports from all of computer science to the broader scientific world. And as so many different disciplines are getting increasingly computational, and here I'm thinking about everything from the mathematical sciences to the natural sciences, even to the social sciences, these fields have really no choice but to confront and learn about NP-completeness, since it genuinely governs what can be accomplished computationally and what cannot. My perspective here will be unapologetically that of an algorithm designer, and in particular, after our discussion of NP-completeness, the rest of this course is going to focus on algorithmic approaches to these problems. If you're confronted with an NP-complete problem, what should you do about it? So rather than starting out by formalizing computational intractability, it's a little simpler to begin by defining computational tractability. That brings us to the uber-important definition of polynomial time solvability. So the definition's a bit of a mouthful, but it's sort of exactly what you would think it would be. So a problem is polynomial time solvable, naturally, if there's a polynomial time algorithm that solves it. That is, there's an algorithm and there's a constant k, so that if you feed in an input of length n to this algorithm, then it will correctly solve the problem. Either it'll correctly answer yes or no, or it'll correctly output an optimal solution, whatever. It correctly solves it in time big O of n to the k. Pretty much all of the problems we've discussed, it's been kind of obvious what the input length was. It was, for example, the number of vertices plus the number of edges, or it was the number of numbers that had to be sorted, etc. For an abstract problem, just informally, I would encourage you to think about the input length n as the number of keystrokes on a computer that would be required to describe that given instance. And yes, it is true that, strictly speaking, to be polynomial time solvable, all you need is a running time of big O of n to the k for some constant k. Even if you get k equals 10,000, that is enough to meet the demands of this definition. Of course, for concrete problems, you're going to see small values of k. In this course, k has usually been 1, 2, or 3. So a quick comment for those of you that are wondering about randomized algorithms, and of course we saw some cool examples of randomized algorithms back in part 1. So to keep the discussion simple when we discuss computational intractability, let's just think only about deterministic algorithms. But at the same time, don't worry. Really, all of the qualitative conclusions we're going to reach are believed to hold equally well for randomized algorithms. In particular, we don't think that there are problems that deterministic algorithms require exponential time, and yet randomization allows you to magically get polynomial time. And there's even some mathematical evidence suggesting that that is the case. So that brings us to the definition of the complexity class capital P. Capital P is just defined as the set of all polynomial time solvable problems. The set of all problems that admit a polynomial time algorithm solving it. For those of you who have heard of the P versus NP question, this is the same P. Throughout these courses, we've exhibited many examples of problems in P, right? That's really been sort of the whole point of the course. Sequence alignment, minimum cut, sorting, minimum spanning tree, shortest paths, and so on. There are two exceptions. One we talked about explicitly at the time, which is when we discussed shortest paths in graphs with negative edge costs. And we stated that if you have negative cost cycles and you wanted shortest paths that are simple, that do not have any cycles in them, then that turns out to be an NP-complete problem. For those of you that know about reductions, it's an easy reduction from the Hamiltonian path problem. So we did not give a polynomial and time algorithm for that version of the shortest path problem. We just punted on it. And the second example is a really subtle one. So believe it or not, we did not actually give a polynomial time algorithm for the knapsack problem. So this requires an explanation, because at the time in our dynamic programming algorithm, I'll bet it felt like it was a polynomial time algorithm. So let's review what its running time was. So in the knapsack problem, the input is n items that have values and sizes. And also you're given this knapsack capacity, which is a positive integer capital W. And our table, our two-dimensional array, had theta of n times capital W subproblems. We spent constant time filling in each entry. So the running time of our dynamic programming algorithm was theta of n, the number of items, times capital W, the knapsack capacity. What, on the other hand, is the length of an instance of knapsack? Well, as we just said, the input to knapsack is two n plus 1 numbers, the n sizes, the n values, and the knapsack capacity. And naturally, to write down any one of these numbers, you only need log of the magnitude of the number, right? So if you have an integer k and you want to write it in binary, that's log base 2 of k bits. If you want to write it down in base 10 digits, it's going to be log base 10 of k, which is the same up to a constant factor. So the point is the input length is going to be proportional to n and proportional to log of the magnitudes of the numbers, in particular log of capital W. So here's another way to see why the dynamic programming algorithm is exponential in terms of the input length. Let me use an analogy. Suppose you were solving some problem over graph cuts. So remember, the number of cuts in a graph is exponential to the number of vertices. It's roughly 2 to the n for n vertices. So that means if you're doing brute force search and I add just one more vertex to the graph, it doubles the running time of your algorithm. That's exponential growth. But actually the same thing is going on in the knapsack problem with our dynamic programming algorithm. Suppose we write everything in base 10 and I just add one extra 0 to the knapsack capacity. I multiply it by 10. Well, then the number of subproblems you have to solve goes up by 10. So again, I just added one digit, one keystroke to the input, and yet your running time got multiplied by a constant factor. So it is, again, exponential growth with respect to the encoding length of the input. Now, it's no accident that we failed to get a polynomial time algorithm for the knapsack problem, because that is, in fact, an NP-complete problem. And again, we'll explain what NP-complete means shortly. So that's the mathematical definition of the complexity class P, but more important than the math is the interpretation. That is, how should you think about the class P? How should you think about polynomial time solvability? To the practicing algorithm designer, the practicing programmer, membership in P, polynomial time solvability, can be thought of as a rough litmus test for computational tractability. Now, the identification of algorithms that run in big O of n to the k time for some constant k and practical computationally efficient algorithms is imperfect. There are, of course, algorithms which in principle run in polynomial time but are too slow to be useful in practice. Conversely, there are algorithms which are not polynomial time but are useful in practice. You already coded one up when you did the dynamic programming solution to knapsack, and we'll see several more examples in future lectures. And more generally, anyone who has the guts to write down a precise mathematical definition like this complexity class P needs to be ready for the inevitability that the definition will accommodate a few edge cases that you wish it didn't, and that it will exclude a few edge cases that you wish it didn't. This is an inevitable friction between the binary nature of mathematical properties and the fuzziness of reality. These edge cases are absolutely no excuse to ignore or dismiss a mathematical definition like this one. Quite the contrary, the friction makes it that much more astonishing that you could write down a clean mathematical definition, something that either is satisfied or not satisfied by every single computational problem, and have it serve as such a useful guide to classify problems into the tractable in practice problems and the intractable in practice problems. And we now have 40 years of experience that indicates this definition has been unreasonably effective in just that kind of classification. Generally speaking, computational problems in P can be well solved using off-the-shelf solutions, as we've seen in the many examples in this class. Problems that are believed not to be in P generally require significant computational resources, significant human resources, and a lot of domain expertise to solve in practice. So we've mentioned in passing a couple of problems that are believed to not be polynomial time solvable, but let me pause here and tell you about a more famous one, the traveling salesman problem. The traveling salesman problem remarkably just doesn't sound that different than the minimum spanning tree problem, a problem for which we now know a litany of greedy algorithms that run in near linear time. So the input is an undirected graph, and let's go ahead and assume that it's a complete graph. So there's an edge between every pair of vertices. Every edge has a cost, and the problem is non-trivial even if every edge cost is just either 1 or 2. Let me draw an example in green with 4 vertices. The responsibility of an algorithm for the TSP problem is to output a tour, that is, a cycle that visits every single vertex exactly once, and amongst all tours, which you can think of as a permutation of the vertices, the order in which you visit them, you want the one that minimizes the sum of the edge costs. So for example, in the green graph that I've drawn, the minimum cost tour has total cost 13. So the TSP problem is simple enough to state. It's clear you could solve it by brute force search in roughly n factorial time, just by trying all permutations of the vertices. But, we've seen many examples in this class where you can do better than brute force search. And the TSP problem, people have been studying seriously from a computational perspective since at least the 1950s, including many huge names in optimization, people like George Danzig. So despite the interest over 60 years, there is, to date, no known polynomial time algorithm that solves the traveling salesman problem. In fact, way back in 1965, Jack Edmonds, in a remarkable paper called Paths, Trees, and Flowers, conjectured that no polynomial time algorithm exists for the traveling salesman problem. This conjecture remains unresolved to this day, almost 50 years later. As we'll see, this is equivalent to the conjecture that P is not equal to NP. So how would you formalize a proof of this conjecture? How would you amass evidence that this conjecture holds in the absence of a proof? Those are the topics of the upcoming videos. How do we amass evidence of computational intractability of something like the traveling salesman problem? The key idea is through the formalism of completeness, which in turn depends on the idea of a reduction between two problems. We left off last video with Edmonds' prescient conjecture from 1965 in his paper Paths, Trees, and Flowers, when, while pondering the traveling salesman problem, he conjectures that there is no polynomial time algorithm for it. That conjecture is equivalent, as we'll see, to a conjecture called P not equal to NP, and this is not resolved. This remains to this day one of the most fundamental open problems in all of mathematics. It's important that research in algorithms does not grind to a halt just because we have this open and presumably extremely difficult P versus NP problem that we don't yet understand. We still want guidance about which problems are easy and which problems are hard. So a pretty great idea for giving us such guidance while at the same time evading actually answering the P versus NP problem is to show that problems are difficult in a relative sense. Amass evidence of intractability by showing that a problem is at least as hard as many other computational problems. To make this idea of relative difficulty precise, we need to say what we mean that one problem is as hard as another. The language for that is a reduction from one problem to another. We say that a computational problem, say pi 1, reduces to another one, pi 2, if all you need to solve pi 1 efficiently is an efficient algorithm for pi 2. That is, if I gave to you on a silver platter a polynomial time algorithm for the problem pi 2, then using that as a subroutine, you could build a polynomial time algorithm for pi 1. So we'll see some concrete examples in just a sec, but let me just mention I'm being slightly informal with this definition. You'll see something a little bit more formal if you look at a textbook or take a class specifically on this topic. But this is how you should think about reductions. All you need to solve pi 1 is someone handing you an efficient subroutine for pi 2. That is the algorithmic way of thinking about reductions. Indeed, by virtue of being immersed in algorithms over the past many weeks, we have examples of reductions. The next quiz is going to ask you to recall some of them. So the correct answer is all of the above. A, B, and C are all legitimate reductions from one computational problem to another. So for example, answer A, this is something we discussed back in part 1 of the course when we first motivated linear time median algorithms. At that point, we were arguing that for a median algorithm to be interesting, it better be faster than n log n time. That's why we were shooting for linear time. The reason being that one perfectly correct algorithm for computing a median is you take the input array, you sort it, for example, using merge sort in n log n time, and you return the middle element. That's going to be the median. The second answer, B, so this is something we mentioned in passing in the naive implementation of Kruskall's algorithm, where we wanted to check cycles when we were thinking about adding a new edge. And we observed that one way to check if a graph has a cycle is you just run depth first search on that graph. If there's a cycle, you'll detect it by exploring an edge which points backward to a vertex that you're still in the middle of exploring. The third example is maybe more interesting in the sense that we invoke the provided subroutine more than once. When we first introduced the all pairs shortest path problem, we observed that one solution, and in certain cases it's actually a very good solution, is to just invoke a single source shortest path subroutine, like Dijkstra's algorithm or the Bellman-Ford algorithm, n times once for each choice of the source. But again, it's still a reduction. Given an efficient algorithm, a polynomial time algorithm, for the single source shortest path problem, you just run it n times. That gives you a polynomial time algorithm for the all pairs shortest path problem. In fact, seasoned algorithm designers and seasoned programmers are always looking for opportunities to employ reductions. So when someone describes to you a computational problem, the very first thing you should try to think through is this a problem I already know how to solve, just merely in disguise? So maybe if you have to make a sequence of decisions, maybe you can phrase it as a shortest path problem, a problem that you already know excellent solutions to. And if that fails, if the computational problem you're confronted with isn't literally the same as one you already know how to solve, maybe by invoking known primitives, known algorithms, a small number of times, that's sufficient to solve this new computational problem that you're confronted with. So all of these are what I think of as honorable uses of reductions. So it's somehow the light side of the force. It spreads the frontier of tractability to cover the things we can do with algorithms wider and wider. Now, for NP-completeness, for establishing computational intractability, we have to turn this world on its head. This relies on a perverse use of reductions, which I'll explain next. So suppose that the problem pi 1 reduces to pi 2 in the sense that all you need to solve pi 1 in polynomial time is a polynomial time algorithm for pi 2. That's the only missing piece. Now, as algorithm designers, you're probably thinking about the happy case where we have a polynomial time algorithm for pi 2 sitting on the shelf. We have something like Dijkstra's algorithm or Bellman-Ford algorithm. We take it off the shelf and we use it combined with this reduction to solve pi 1. But let's think about the contrapositive of what it means when one problem reduces to another. And now let's think about the case where we don't actually believe that it's possible to solve pi 1 in polynomial time. Well, if we don't think it's possible to solve pi 1 efficiently, and pi 1 reduces to merely computing pi 2 efficiently, well then we certainly can't believe that it's possible to compute pi 2 efficiently either. That is, if pi 1 reduces to pi 2, and it just so happens that pi 1 cannot be solved in polynomial time, then pi 2 cannot be solved in polynomial time either. So this is the perverse use of a reduction that I mentioned earlier. This is the dark side of the force Rather than using a reduction to enlarge the frontier of tractability from pi 2 to include pi 1 also, we're spreading the frontier of intractability from pi 1 to pi 2. So this then is what we mean formally when we say that one problem is at least as hard as another. If pi 1 reduces to pi 2, what does that say? That says pi 2 allows you to solve pi 1. Maybe it lets you do other stuff as well. So therefore pi 2 is at least as hard as pi 1. So we now have the vocabulary to say that one problem is at least as hard as another one. And let's remember what our plan was. Our plan was to amass evidence of the intractability of the traveling salesman problem by saying it's at least as hard as lots of other stuff. So to pass from as hard as a single problem to a big set of problems, we're going to talk about the notion of completeness. Formally, consider some set C of problems, and it's going to be tricky to get the right set of problems. We'll discuss that in detail in the next video, but for now just let C be any old set of problems. We call a computational problem pi complete for C. We call it C complete if it's at least as hard as everything in C, if everything in C reduces to pi. Oh, and also this problem pi, it should be in this class itself. So the second constraint here is the more important one. It's the one that fits more directly into our narrative. Remember, we wanted to have vocabulary for saying one problem is as hard as a whole bunch of other stuff. C is the bunch of other stuff. So pi is at least as hard as everything in C. That is, everything in C reduces to pi. One nice reason to have this first constraint also to assume that the problem pi is a member of C is that gives the following nice interpretation. We can think of this problem pi as being a hardest problem in the set C. It's in C and it's at least as hard as everything else in the class. So we're starting to see a confluence between our strategic plan, amassing evidence for the intractability of TSP by arguing it's as hard as a bunch of other stuff, and the mathematical formalism, right? This notion of completeness gives us a language to say that a problem is at least as hard as a bunch of other stuff. So how should we define all of this other stuff? That is, what is a suitable choice for the class C? Well, we'd like to present the strongest evidence, the most compelling case possible of the traveling salesman problem being intractable. So that says we should strive for the biggest set C that we can find. The more stuff this problem is as hard as, the greater the evidence of its intractability. So we want to prove it complete for a really big set C. Well, why not be ambitious and reach for the stars? Why don't we just show that the traveling salesman problem is the hardest problem in existence? It's C complete, even if we take the set C to be all computational problems. Well, this is a good starting point, but it turns out this is too ambitious. We're not going to be able to prove this fact. There are indeed computational problems out there that are certainly strictly harder, strictly more difficult to solve than the traveling salesman problem. One I hope you've heard of is the halting problem. So in the halting problem, it's very simple. You're given as input some code, say a program written in C, and you're given an input, and the responsibility of the algorithm is to decide whether or not the provided program will halt eventually when you run it with the provided input. Perhaps the obvious approach to the halting problem is to just simulate the provided program in an interpreter, in effect, on the supplied input. But here's the problem. Suppose you've been simulating the provided program on the provided input, and you've been running for, say, 10 hours. Maybe you suspect the thing is in an infinite loop and it's never going to halt, but how do you know? Maybe if you ran it for one more hour, it would halt. What if you've been running it for 10 years? Maybe now you're pretty sure it's in an infinite loop and never going to halt. But how do you know? Maybe it's going to halt tomorrow. The problem of not knowing when you're done is an issue not just with the naive simulation approach to the problem, but with any possible approach to this computational problem. Indeed, Turing proved in his landmark 1936 paper that there is no algorithm, however slow, guaranteed to always correctly solve the halting problem. So this is one of those theorems which is simultaneously, at least in my opinion, very deep, but also the proof is just like 4 lines. You prove it by contradiction. You assume that an algorithm for the halting problem does exist, and then using the code for that program, you construct a program that, on the one hand, can't halt, and on the other hand, can't not halt. Obviously a contradiction. So the purported algorithm for solving the halting problem can exist. So this is the kind of argument I find just totally baffling. I like to recall von Neumann's quote that there's some things in mathematics that you don't ever understand, you just get used to. And this kind of diagonalization argument, inspired by Cantor's original argument that there's an uncountable number of real numbers, I think falls squarely in that category. Anyways, the point is that the traveling salesman problem no longer looks quite that bad. And we now realize that our original thought to prove that the TSP problem is at least as hard as every other problem is a little misguided, is a little too ambitious. So it's certainly not at least as hard as the halting problem. The halting problem is what's called undecidable. There's no algorithm for it whatsoever, whatever time bound I might give you. Whereas the TSP problem, by contrast, if I give you a big enough time bound, roughly n factorial for n vertices, you can solve the problem, namely using our favorite punching bag, brute force search. You can just try every one of the finite possibilities and pick the best one. But the high-level idea at the top of this slide, that is proving the traveling salesman problem complete for a big class of problems, is still a good one. We just have to refine our understanding of the suitable choice of the class C. In particular, by virtue of being solvable by brute force search, there are certain problems that we cannot prove the TSP is at least as hard as, but maybe we can prove that amongst all problems which can be solved using brute force search, amongst such problems, TSP is the hardest one. Now, to execute this idea, we'll of course have to define what it means for a problem to be brute force solvable. That will motivate the complexity class NP, the subject of the next video. We now arrive at the heart of the discussion, the definition of the complexity class NP as computational problems where you can efficiently recognize a solution, roughly the same thing as problems solvable using brute force search. The idea of NP-completeness, that a problem can be as hard as any other problem where you can efficiently recognize a solution. The ubiquity of NP-complete problems, including possibly a problem you're working on right now in one of your own projects, and what should be part of your toolbox, a simple recipe for proving that problems are NP-complete. We left off the last video noting that the traveling salesman problem, by virtue of being solvable in exponential time using brute force search, is certainly not as hard as notorious problems like the halting problem. So perhaps we can instead amass evidence of intractability for the TSP by showing it's as hard as any other problem solvable using brute force search. That is, every other brute force search solvable problem reduces to solving the traveling salesman problem. To turn this idea into mathematics, we have to identify the minimal ingredients necessary to solve a problem using brute force search. And the key idea turns out to be the efficient recognition of purported solutions. Specifically, we say that a computational problem, like say the traveling salesman problem, or frankly almost any other problem we've talked about in these classes, is a member of the complexity class NP if it meets the following two criteria. The first property is sort of a simple prerequisite. It asserts that solutions have length polynomial in the input size. The second property, and this is really the key one, is that if someone offers up to you a purported solution to an NP problem, you can verify its correctness in polynomial time. To make sense of this abstract definition, let's think about some concrete examples. Let's start just with the traveling salesman problem. So consider an instance of the traveling salesman problem. It's specified by some n vertices and distances amongst all of the pairs of vertices. And suppose we really want to know whether or not there's a tour that has total length at most 1,000. So let's for the moment set aside the problem of checking whether or not one of the n factorial tours does indeed have cost at most 1,000. Let's instead think about the much more modest question of whether or not a single proposed tour has cost at most 1,000. Well, that computational problem, just verifying whether or not a single suggested tour meets the target or not, that's an easy computational problem, right? The tour is specified just by an order in which you're supposed to visit the vertices. The length of that ordering is certainly polynomial in the length of the input, and all you got to do is add up the n edges that get traversed in this tour and check if the sum is at most 1,000 or not. This argument shows that checking whether or not there exists a tour with total cost at most some threshold does indeed belong to the complexity class NP, right? You can write down a purported solution in polynomial length. All you need to do is specify the ordering, and you can verify whether or not a candidate solution, whether or not a proposed tour, meets the threshold in linear time, just by adding up the corresponding edge costs. If it bothers you that I moved away from the problem of computing an optimal minimum cost tour and studied instead the seemingly easier problem of just checking does there exist a tour that has total cost at most a given threshold, notice that the former problem reduces to multiple indications of the latter problem just by binary search over the threshold. The same reasoning can be applied to pretty much all of the computational problems we've seen in these courses, placing all of them into the complexity class NP. So for the types of problems we've been thinking about, solutions can generally be specified in linear space, correctness can be verified in linear time. Another genre of problems that we haven't really discussed in these classes but are important in many application domains and are also canonical NP problems are constraint satisfaction problems. In general, in a constraint satisfaction problem, you have a bunch of variables. The simplest case would be binary or Boolean variables. And then you have a list of constraints. And each constraint specifies for a subset of the variables a permitted list of configurations of those variables. So one simple case, which some of you will have seen, and if you study NP-completeness properly, you'll definitely see it, will be the 3-sat problem. The 3-sat problem does indeed concern Boolean variables, so each variable xi can either be 0 or 1, and you can think of the clauses as forbidding a single assignment to a triple of vertices. So a clause might say, you are not allowed to simultaneously assign x3 to 1, x5 to 0, and x8 to 1. So clauses forbid particular triples of assignments, and the question then is, does there exist an assignment of all of the variables to 0 and 1 that simultaneously satisfies all of the constraints? These kinds of constraint satisfaction problems also belong to the complexity class NP. So here, if you have a purported assignment of all of the variables to values that meets all of the constraints, well, you can write it down very simply, just the value for each of the variables, and it's easy to check. I just iterate through the constraints one at a time and see if, yes, indeed, the values that you're suggesting for the variables in that constraint are on the list of permissible value combinations. At the beginning of this video, I suggested that the complexity class NP would represent problems that are brute force solvable in the same way that the traveling salesman problem is. If you look at the actual definition I just gave you of the class NP, it's in terms of efficient recognition of solutions. But let's now observe that this definition of NP, in terms of efficient verification of purported solutions, does indeed imply that these problems can be solved in exponential time using brute force search. So really, all you do here is check each of the candidate solutions one at a time. And in doing so, you see very clearly the role of the two properties in the definition of an NP problem. The role of the first property, saying solution length has to be polynomial in the input size, in turn restricts the number of possible solutions, the number of bit strings of that given length, to be at most exponential in the input size. The second property, of course, assures you that for each of those only exponentially many possibilities, you can verify whether or not it is in fact a correct solution, whether or not it's a short TSP tour, whether or not it's a satisfying assignment to some variables in a constraint satisfaction problem in polynomial time. Now, because the requirements for membership in the class NP are so weak, the class NP is very big. Right? All membership in NP requires essentially is the ability to efficiently recognize a solution. You know one when you see one. And as you can imagine, that property is met by many of the computational problems that we ever think about. Factoring almost any graph problem you'd ever think about, sequencing problems, most constraint satisfaction problems, and so on. As we've said, it's true that not every natural computational problem is NP. The halting problem is an extreme example. That's in fact undecidable. There's no algorithm at all. There's also some natural problems in some application domains which are neither in NP nor are they undecidable. So model checking is one domain that furnishes lots of examples of problems strictly harder than NP. The vastness of the complexity class NP means that NP-completeness is strong evidence of intractability. Remember what it means for a problem to be complete for some set of problems. It means it's as hard as any other problem in that set. Every other problem in that set reduces to the complete problem. Therefore, suppose you had a polynomial time algorithm for just one NP-complete problem. You would get automatically, by the definition of a reduction, a polynomial time algorithm for every single computational problem in NP. Every single problem for which you can efficiently recognize a solution. That is, solving just one NP-complete problem in polynomial time would imply that NP is the same as P. Every problem in NP can be solved in polynomial time. It's pretty hard to really grok all of the ramifications of this kind of result if P were to equal NP. So just as one example, modern e-commerce as we know it would fall apart like a house of cards. That's because it depends on the security of crypto systems like RSA, which in turn assumes the computational intractability of problems like factoring. Yet, an efficient algorithm for even the most obscure NP-complete problem would automatically imply, at least in principle, a polynomial time algorithm for factoring. So this provides a satisfying resolution to a narrative we began in the previous video. Recall we were discussing the traveling salesman problem, and like thousands of other people, we were wondering whether or not there's a polynomial time algorithm for it or not. For example, Edmonds conjectured in 65 that there is no polynomial time algorithm for it. Now, obviously what you really want is the answer. You either want a proof of Edmonds' conjecture that there's no efficient algorithm for TSP, or even more astonishingly, you'd want a polynomial time algorithm that solves the problem. But we also have to face the reality that we may not know the answer for sure to this question for quite a while. Years? Certainly. Decades? Probably. Centuries? Who knows? Maybe. So the challenge then for people thinking about algorithms and computation is to nevertheless devise a theory which usefully differentiates tractable problems from relatively intractable ones, even in the face of this massive deficiency of our understanding of what is possible and what is impossible. And the brilliant way out is relative difficulty as now personified by NP-completeness. If you want to amass extremely strong evidence of the computational intractability of a problem, prove that it's NP-complete. Prove that a polynomial time algorithm for the problem, if it existed, would solve thousands upon thousands of unsolved computational problems. So for those of you out there that fancy yourself computer scientists, I hope you feel some pride seeing this definition. I mean, how cool is it that our discipline came up with such a great concept of an NP-complete problem? The fact that there's a universal problem that simultaneously encodes all computational problems in which you can efficiently recognize a solution. There remains, however, a niggling issue. In general, when you're confronted with a mathematical definition, like the definition of NP-completeness that I just gave you, you should demand two things. The first thing you should demand is an explanation of why you should care. That is, if the definition is met, is satisfied, what are the interesting consequences? I'd like to think I've given you a very satisfying answer to that question for the definition of NP-completeness. I've argued that if a problem is NP-complete, then that's strong evidence of computational intractability, in the sense that a polynomial time algorithm for this NP-complete problem, if one hypothetically existed, that would automatically solve efficiently thousands of fundamental computational problems, anything for which you can efficiently recognize a solution. But the second thing you should demand from somebody who offers you a mathematical definition is examples. Do things that I care about actually meet this definition? And in NP-completeness, I haven't shown you anything. And indeed, when you look at this interpretation, a single problem that simultaneously is encoding all problems with efficiently recognizable solutions, you might well wonder, could such objects ever exist? And the reason the theory of NP-completeness is so powerful and over the past 40 years has been exported from computer science to all kinds of other disciplines is that that question also has an incredibly satisfying answer. It turns out tons of problems are not merely in NP, they don't merely have efficiently recognizable solutions. Thousands and thousands of problems are in fact NP-complete, as hard as any other problem in NP. So both the definition of NP-completeness and the fact that, amazingly, there exist NP-complete problems, that's due to independently Steve Cook and Leonid Levin. So Cook and Levin came up with their largely similar theories independently. Cook was at that time, as he is today, at the University of Toronto. Leonid Levin was behind the Iron Curtain. So he was working in the Soviet Union, so it took a while before his results were known in the West. These days, Levin is a professor at Boston University. Both Cook and Levin proved not just the basic existence result, but also gave some hints that problems that people really care about are also going to be NP-complete. For example, some constraint satisfaction problems like 3-SAT. But the vast scope of NP-completeness, the sheer breadth of problems that would eventually be proven NP-complete, was first made clear in a 1972 paper by Richard Karp. In that paper, he showed that 21 different problems are NP-complete, including the traveling salesman problem and various problems that many different communities had been stuck on for decades. It now became clear that NP-completeness was the fundamental obstacle preventing progress in efficient algorithms across many, many different domains. So another thing that's amazing about NP-completeness, and a big reason for why it's been so successfully exported from, first of all, theoretical computer science to computer science more broadly, and then beyond into engineering and the other sciences, is that it's quite easy to stand on the shoulders of these giants and prove that new problems, problems that you care about, are also NP-complete. So imagine that there's some computational problem pi that you really care about. This is just crucial to the project that you're working on. And you're stuck. You've been trying for weeks to solve it, throwing everything in your toolbox at it. You've tried greedy algorithms, divide and conquer, dynamic programming, randomization. You've thrown every data structure in the book at it, hash tables, heap search trees. Nothing works. You can't come up with an efficient algorithm. At that point, you should contemplate the possibility that the issue is not your own lack of cleverness or ingenuity. The issue is not having too few tools in your programmer toolbox. Perhaps the issue is intractability of the computational problem that you're trying to solve. So when you reach this point of exasperation, it's time to consider applying the following two-step recipe for establishing that the problem pi is NP-complete. Of course, the problem doesn't go away just because you prove it's NP-complete, but you should approach it using a different algorithmic strategy. And we'll discuss some of the most popular such strategies of approaching NP-complete problems in the rest of this course. So let me state the two-step recipe just at a very high level. So the first thing you need to do is settle on a suitable choice of an NP-complete problem, pi prime. The second thing you need to do is you need to show that pi prime reduces to the problem you care about, pi. That shows that your problem is at least as hard as this NP-complete problem, in the sense that the NP-complete problem reduces to yours, and therefore your problem, assuming it's in NP, is NP-complete as well. So clearly the devil is in the details of successfully executing this two-step recipe. And you might well be wondering, well, how on earth do I know which NP-complete problem pi prime I should use? And then secondly, how am I going to come up with this reduction from this NP-complete problem pi prime to my own problem pi? But don't be intimidated by either of these two steps. With just a little bit of practice, you can actually get quite good at both of the steps and execute this recipe successfully in a lot of different cases. So one thing that should make the first step less intimidating is there are some excellent lists of NP-complete problems, in particular simple ones that tend to be useful in devising your own reductions. And the canonical such list is a book by Gary and Johnson called Computers and Intractability. It's from 1979, but it's still incredibly useful. I don't think I know of another computer science book that's more than 30 years old, which is as useful as this one. So there still remains the question of how do you actually come up with one of these reductions from a known NP-complete problem pi prime to the problem you actually care about, pi. But don't be intimidated by this step either. So first of all, as an algorithms person, you should be thinking about reductions all the time anyways. This should be a very natural mode of thought for you. For example, when we first started talking about all pairs shortest paths, we quickly observed that it reduces to the single source shortest paths problem. So that mentality of solving one problem using another is equally useful in the design of NP-completeness reductions. And also, there's a lot of resources available to gain facility with NP-completeness reductions. You can look in the various algorithms textbooks. Generally, they have lots of examples. The Gary and Johnson book is a good one. There's some online courses that study NP-completeness in more depth. Those resources will give you a lot of examples of NP-completeness reductions. It'll offer some tips on how to come up with them yourself. And most importantly, practice will make perfect. So I strongly encourage you to take advantage of those resources. I think you'll be pleased to have NP-completeness as part of your toolbox. Certainly, nobody wins if you spend weeks or months of your life inadvertently trying to prove that P equals NP. So I hope that pretty much all of you had heard about the P versus NP question before you enrolled in this class, but if you haven't, you can pretty much guess what that question is. I've defined for you both of these classes of problems. P is the class of problems that are polynomial times solvable, whereas the problems in NP have the property that, at least given a solution, you can quickly verify that it is indeed a correct solution. It's widely conjectured that P is not equal to NP. That is, merely the ability to efficiently verify purported solutions is not sufficient to guarantee polynomial times solvability. Indeed, Edmonds back in 1965, before we even had the vocabulary NP, remember that came along only in 71, Edmonds already in 65 was essentially conjecturing that P is not equal to NP. In the form that he was conjecturing there's no polynomial time algorithm that solves the traveling salesman problem. But let me emphasize, we genuinely do not know the answer to this question. There is no proof of this conjecture. P versus NP question is arguably the open question in computer science. It's also certainly one of the most important and deepest open questions in all of mathematics. For example, in 2000, the Clay Mathematics Institute published a list of 7 Millennium Prize problems. The P versus NP question is one of those 7 problems. All of these problems are extremely difficult and extremely important. The only one that's been solved to date is the Poincare conjecture. The Riemann hypothesis is another example on that list. And they're not called the Millennium Prize problems for nothing. If you solve one of these mathematical problems, you get a cash prize of $1 million. Now, while $1 million is obviously nothing to sneeze at, I think it sort of understates the importance of a mathematical question like P versus NP. And the advance in our knowledge that a solution to the question would provide, I think would be much more significant than a prize check. So how come so many people think that P is not equal to NP rather than the opposite, P equals NP? Well, I think the dominant reason is sort of a psychological reason, namely that if it were the case that P is equal to NP, then all you'd have to do, remember, is exhibit a polynomial time algorithm for just one NP-complete problem. And there are tons of NP-complete problems. And a lot of extremely smart people have had NP-complete problems that they've really cared about, and either on purpose or accidentally, they've been trying to develop efficient algorithms for them. No one has ever succeeded in over a half-century of serious computational work. The second reason is sort of philosophical. P equals NP just doesn't seem to jive with the way the world works. Think about, for example, when you do a homework problem in a class like this one. And consider 2 different tasks. The first task is I give you a question and I ask you to come up with a correct solution, say a proof of some mathematical statement. The second task would be just grade somebody else's suggested proof. Well, generally it seems a lot harder to actually come up with a correct argument from scratch compared to just verifying a correct solution provided by somebody else. And yet, P equals NP would be saying that these 2 tasks have exactly the same complexity. It's just as easy to solve homework problems as it is to just read and verify the correct solutions. So I don't know about you, but it's always seemed to me to be a lot harder to come up with a mathematical argument from scratch as opposed to simply grading somebody else's solution. Somehow it seems to require a degree of creativity to pluck out from this exponentially big space of proofs a correct one for the statement at hand. Yet P equals NP would suggest that that creativity could be efficiently automated. But of course, P versus NP being a mathematical question, we'd really like some mathematical evidence of which way it goes. For example, that P is not equal to NP. And here we really know shockingly little. There just isn't that much concrete evidence at this point that, for example, P is not equal to NP. Now, maybe it seems bizarre to you that we're struggling to prove that P is not equal to NP. Maybe it just seems sort of obvious that there's no way that you can always construct proofs in time polynomial in what you need to verify proofs. But the reason this is so hard to prove mathematically is because of the insane richness of the space of polynomial time algorithms. And indeed, it's this richness that we've been exploiting all along in these design and analysis of algorithms classes. Think, for example, about matrix multiplication. Had I not shown you Strasson's algorithm, I probably could have convinced you more or less that there was no way to solve matrix multiplication faster than cubic time. You just look at the definition of the problem and it seems like you have to do cubic work. Yet, Strasson's algorithm and other follow-ups show you can do fundamentally better than the naive cubic running time algorithm for matrix multiplication. So there really are some quite counterintuitive and hard to discover unusually efficient algorithms within the landscape of polynomial time solutions. And who's to say that there aren't some more exotic species in this landscape of polynomial time solvability that have yet to be discovered, which can make inroads even on NP-complete problems? At this point, we really don't know. At the very least, our currently primitive understanding of the fauna within the complexity class P is an intimidating obstruction to a proof that P is not equal to NP. I should also mention that as an interesting counterpoint to Edmund's conjecture in 65 was a conjecture by Gödel. This is the same logician Kurt Gödel of Gödel's completeness and incompleteness theorems. He wrote a letter to John von Neumann in 1956 where he actually conjectured the opposite, that P is equal to NP. So who knows? So I've tried to highlight for you the most important things that an algorithm designer and serious programmer should know about NP problems and NP completeness. One thing I haven't explained, which you might be wondering about, is what on earth does NP stand for anyways? A common guess would be not polynomial. But this is not what it stands for. The answer is going to be a little bit more obscure, and indeed it's a bit of an anachronism, non-deterministic polynomial. So this is referring to a different but mathematically equivalent way to define the complexity class NP in terms of an abstract machine model known as non-deterministic Turing machines. But generally for someone who's thinking about algorithms, generally for the programmer, I would advise against thinking about problems in NP in terms of this original definition with this abstract machine model, and I'd instead strongly encourage you to think about the definition I gave you in terms of the efficient recognition, the efficient verification of purported solutions. Again, they're mathematically equivalent, and I think efficient verification makes more sense to the algorithm designer. Maybe you're thinking that NP is a perhaps not that good and somewhat inscrutable definition for what's a super important concept. But it's not for lack of discussion and effort on the community's part. So very soon after the work of Cook and Karp, it was clear to everybody working in the West on algorithms and computation that this was a super important concept and people needed to straighten out the vocabulary ASAP. So Don Knuth ran a poll amongst members of the community. He reported on the results in his SIGAC News article from 1974, A Terminological Proposal, and NP-completeness was the winner, and that was then adopted in the landmark book Design and Analysis of Algorithms by Aho, Hopcroft, and Ullman, and that's the way it's been ever since. There is one suggestion that was passed over, which I find quite amusing. Let me tell you about. The suggestion was PET, P-E-T. So what is PET acronym for? Well, it's flexible. So initially, the interpretation would be possibly exponential time problem. Now, suppose that someday people prove that P is not equal to NP. then the meaning would change to provably exponential time. So now is not the time to nitpick with the suggestion that you could prove p not equal to np without actually proving an exponential lower bound, merely a superpolynomial bound. Let's leave objections like that aside and ask, what would happen if p actually turned out to be equal to np? Well, then you could call PET previously exponential time problems. But, of course, at this point, PET is nothing more than an amusing historical footnote. NP-complete is the phrase that you gotta know. This video is a segue between bad news and good news. The bad news, which we've now discussed, is NP-completeness, the fact that there are computationally intractable problems out there in the world. In fact, they're fairly ubiquitous, and you're likely to encounter them in your own projects. The good news is that NP-completeness is hardly a death sentence. Indeed, our algorithmic toolbox is now rich enough to provide many different strategies toward coping with NP-complete problems. So suppose you'd identified a computational problem on which the success of your new startup company rests. Maybe you've spent the last several weeks throwing the kitchen sink at it. All the algorithm design paradigms you know, all the data structures, all the primitives, nothing works. Finally, you decide to try to prove the problem is NP-complete, and you succeed. Now you have an explanation for why your weeks of effort have come to naught. But that doesn't change the fact that this is the problem that governs the success of your project. What should you do? Well, the good news is NP-completeness is certainly not a death sentence. There are people solving, or at least approximately solving, NP-complete problems all the time. However, knowing that your problem is NP-complete does tell you where to set your expectations. You should not expect some general purpose, super fast algorithm like we have for other computational problems, like say sorting or single source shortest paths. Unless you're dealing with unusually small or well-structured inputs, you're going to have to work pretty hard to solve this problem and also possibly make some compromises. The rest of this course is devoted to strategies for solving or approximately solving NP-complete problems. In the rest of this video, I'll give you an orientation for what those strategies are and what you can expect to come. So as usual, I'm going to focus here on general purpose strategies that cut across multiple application domains. As usual, these general principles should just be a starting point. You should take them and run with them, augmenting them with whatever domain expertise you have in the specific problem that you need to solve. The first strategy is to focus on computationally tractable special cases of an NP-complete problem. Relatedly, you want to think about what's special about your domain or about the data sets that you're working with and try to understand if there's special structure which can be exploited in your algorithm. Let me point out we've already done this in a couple of cases in this course. The first example we saw concerns the weighted independence set. So we studied this problem on path graphs, but the computational problem makes perfect sense in general graphs. The general problem is I give you as input an undirected graph. Every vertex has a weight, and I want the maximum weight subset of vertices that's an independent set. And remember, in an independent set, you are forbidden to take any two vertices that are neighbors. So in an independent set, none of the pairs of vertices that you've picked are joined by an edge. In general graphs, the weighted independent set problem is NP-complete, so we certainly don't expect it to have a polynomial time algorithm. But in the special case where the graph is a path, as we saw, there's a linear time dynamic programming algorithm that exactly solves the weighted independent set problem. So path graphs form a special case of the weighted independent set problem that's computationally tractable, solvable in polynomial, even linear time. In fact, the frontier of tractability can be pushed well beyond path graphs. On the homework, I asked you to think through the case of graphs that are trees, and notice that you could still do dynamic programming efficiently to compute weighted independent sets in trees. You can even get computationally efficient algorithms for a broader class of graphs known as bounded tree width graphs. So the definition of that's a little outside the scope of this course, but you can go even beyond trees. So the second example follows from our dynamic programming algorithm for the knapsack problem. So we discussed that running time and we explained why it's exponential time. The running time of our dynamic programming knapsack algorithm is n, the number of items, times capital W, the knapsack capacity. And because it only takes log W bits to specify the capacity capital W, we don't call that a polynomial time algorithm. But imagine you only have to solve a knapsack instance where the capacity is not too big. Maybe even say the capacity capital W is big O of n. And you definitely will see knapsack instances in practice which possess that property. Well, then our dynamic programming algorithm just runs in time O of n squared, and that's a bona fide polynomial time algorithm for this special case of a small knapsack capacity. So next, let me mention a couple of examples we're going to see in the forthcoming videos. The first one is going to concern the 2-sat problem. So 2-sat is a type of constraint satisfaction problem. Remember, in a constraint satisfaction problem, you have a bunch of variables. Each one gets assigned a value. So the simplest case is the Boolean case, where each variable can be 0 or 1, false or true. And then you have a bunch of clauses, which specify the permitted joint values of a collection of variables. The 2 in 2-sat refers to the fact that each constraint involves the joint values of only a pair of variables. So a canonical constraint in a 2-sat instance is going to, for 2 variables, specify 3 joint assignments that are allowed and 1 that's forbidden. So for example, maybe it will say, oh, for variables x3 and x7, it's okay to set them both to true, it's okay to set them both to false, it's okay to set 3 to true and 7 to false, but it's forbidden to set 3 to false and 7 to true. So that's a canonical constraint in a 2-sat instance. 3-sat, it's the same thing, except the constraints involve the joint values to a triple of variables, and it's going to forbid 1 out of the 8 possibilities. Now, the 3-sat problem is a canonical NP-complete problem. That was really singled out by Cook and Levin as being sufficiently expressive to encode all problems in NP. But if each constraint has size only 2, then, as we'll see, the problem becomes polynomial time solvable. There's a couple ways of proving that. We're going to talk about a local search algorithm that checks whether or not there is indeed an assignment to the variables that simultaneously satisfies all of the given constraints. So the final example we'll discuss in more detail later, but just very briefly, we're going to discuss the vertex cover problem. This is a graph problem, and a vertex cover is just the complement of an independent set. So while an independent set cannot take 2 vertices from the same edge, in the vertex cover problem, you have to take at least 1 vertex from every single edge. And then what you want is you want the vertex cover that minimizes the sum of the vertex weights. Yet again, this is an NP-complete problem in general, but we're going to focus on the special case where the optimal solution is small. That is, we're going to focus on graphs where there's a small number of vertices such that every single edge has at least 1 endpoint in that small set. And we'll see that for that special case, using a smart kind of exhaustive search, we'll actually be able to solve the problem in polynomial time. So let me reiterate that these tractable special cases are meant primarily to be building blocks upon which you can draw in a possibly more sophisticated approach to your NP-complete problem. So just to make this a little more concrete, let me just kind of dream up one scenario to let you know what I'm thinking about. Imagine, for example, that you have a project where, unfortunately, it's not really 2-sat that you're confronting. It's actually a 3-sat instance. So you're feeling kind of bummed, 3-sat's NP-complete, and maybe you have 1,000 variables. And certainly you can't do brute force search over the 2 to the 1,000 possible ways of assigning values to your 1,000 variables. But maybe the good news is, because you have domain expertise, because you understand this problem instance, you know that, yeah, there's 1,000 variables, but there's really 20 that are crucial. You have a feeling that all of the action basically is boiling down to how these 20 core variables get assigned. Well, now maybe you can mix together some brute force search with some of these tractable special cases. For example, you could enumerate overall 2 to the 20 ways of assigning values to this core set of 20 variables. 2 to the 20 is roughly 1,000,000. That's not so bad. And now what you're going to do is, for each of these 1,000,000 scenarios, you check whether there's a way to extend that tentative assignment of 20 values to the 20 variables to the other 980 variables so that all of the constraints get satisfied. The original problem is solvable if and only if there exists a way of assigning values to these 20 variables that successfully extends to the other 980. Now, because these are the crucial variables and it's where all the action is, maybe as soon as you assign all of them, 0s and 1s, the residual sat instance is tractable. For example, maybe it just becomes a simple 2-sat instance, and then you can solve it in polynomial time. So this gives you a hybrid approach, brute force search at the top level, tractable special cases for each guess of assignments to the 20 variables, and you're off to the races. And I hope it's clear, I mean this as just one possible way that you might combine the various building blocks we're developing into a more elaborate approach to tackling an NP-complete problem. And that's generally what they take. They take a fairly elaborate approach because, after all, they are NP-complete. You've got to respect that. So with that digression complete, let me mention what are the other two strategies we're going to be exploring in the lectures to come. So the second strategy, which is certainly one very common in practice, is to resort to heuristics. That is, to algorithms which are not guaranteed to be correct. We haven't really seen examples of heuristics in the course thus far. Those of you that are alumni of Part 1, perhaps we could classify Karger's randomized minimum cut algorithm as a heuristic, because it did have a small failure probability of failing to find the minimum cut. But rather, I'm going to focus on some examples in the upcoming lectures. I'm going to use the knapsack problem as a case study, and what we'll see is that our toolbox, which contains various algorithm design paradigms, it's useful not just for designing correct algorithms, but it's also useful for designing heuristics. So in particular, we'll get a pretty good algorithm for the knapsack problem using the greedy algorithm design paradigm, and we'll get an excellent heuristic for knapsack using the dynamic programming algorithm design paradigm. The final strategy is for situations where you are unwilling to relax correctness. You're unwilling to consider heuristics. Now, of course, for an NP-complete problem, if you're always going to be correct, you don't expect to run in polynomial time. But there are still opportunities to have algorithms that, while exponential time in the worst case, are smarter than naive brute force search. So we have, in fact, already seen one example that can be interpreted as an implementation of this strategy. That's for the knapsack problem. So in the knapsack problem, naive brute force search would just run over all possible subsets of the items. It would check if a subset of items fit in the knapsack. If it does, it remembers the value, and then it just returns the feasible solution with maximum value. That has time proportional to 2 to the n, where n is the number of items. Our dynamic programming algorithm has running time n times capital W. Now, of course, this is no better than 2 to the n if the knapsack capacity is huge, if it is itself 2 to the n. But as we argued, if W is smaller, this algorithm is going to be faster. And also, as you learned on the third programming assignment, sometimes even though W is big, dynamic programming is going to beat the crap out of brute force search. So I'll show you a couple of other examples. We'll talk about the traveling salesman problem, where naive brute force search would take roughly n factorial time, where n is the number of vertices. We'll give an alternative dynamic programming based solution, which runs in time only 2 to the n, which is much better than n factorial. The third example, which we'll cover in a forthcoming video, we already alluded to briefly on the last slide. It's for the vertex cover problem. So this is where you're given a graph. Every vertex has a weight, and you want the minimum weight subset of vertices that includes at least one endpoint from every edge. We're going to consider the version of the problem where you want to check whether or not it's possible to have a vertex cover that uses only k vertices, whether or not there exists k vertices that includes one endpoint at least from each edge. The naive brute force search will run in time n to the k, which gets absurd even when k is quite small, but we're going to show that there's a smarter algorithm, which is still exponential in k, but runs in time only 2 to the k times the size of the graph. In this video and the next, we'll develop an exact algorithm for solving what's called the vertex cover problem. This is a well-known NP-complete problem. As such, we certainly don't expect our exact algorithm to run in polynomial time on general instances. But the algorithm does showcase 2 of the algorithmic strategies that we discussed for dealing with NP-complete problems. First of all, we can interpret this algorithm as on general instances, while it's true running in exponential time, nevertheless improving markedly over the more obvious naive brute force search. This illustrates the point that, for many NP-complete problems, there's a lot of room for algorithmic ingenuity, even though you're not going to come up with a polynomial time solution. A second interpretation of the algorithm we're going to develop is that it's polynomial time for special classes of instances, in particular instances that have an unusually good optimal solution. So let me introduce you to the vertex cover problem. The input is simply an undirected graph. The goal is to identify the smallest size, that is the minimum cardinality of a vertex cover of the graph. What is a vertex cover? We call a subset of the vertices a vertex cover if, for every edge, at least one, possibly both, of the edge's endpoints lie in the set S. There is, of course, always a feasible solution. You could always choose every single vertex. That's certainly going to be a vertex cover. But the hard question is, how do you make sure you get one endpoint from each edge in the most parsimonious way? So what might this problem represent? Well, perhaps you're assembling a team of some sort. So maybe a team of programmers, maybe of lawyers, maybe of football players. Who knows? But think of the vertices as being potential people that you could recruit onto your team. And think of an edge as representing a potential task that your team might have to complete. And the two vertices in the edge represent the two people who are capable of accomplishing that task. So then what a vertex cover is, it says hire enough people so that every single task you can accomplish. You have one of the two people in your team that's capable of accomplishing that task. So you could, of course, imagine various generalizations of this problem. You could have a weight for each vertex, for example, indicating the salary that you'd have to pay that person. You could also imagine that instead of edges, you have what are called hyperedges if more than two people are capable of accomplishing a given task. But the unweighted graph vertex cover problem will be interesting enough for our purposes here. Many people are of the opinion that this is a poorly monikered problem. Many people think it should be called the edge cover problem, not the vertex cover problem, because you're choosing vertices to, in some sense, cover the edges by picking at least one of their endpoints. But this is the conventional name for this problem. In the vertex cover problem, you're choosing a set of vertices, and edges provide the constraints. Let's now jump to a quiz to make sure the problem definition is clear. So the correct answer is A. Let's consider each of the two graphs in turn. Let's start with a star graph on n vertices. So this has one vertex in the center and n-1 spokes. The claim is it has a vertex cover of size 1, obviously the minimum possible. That vertex cover comprises just that center vertex. Why is it a vertex cover? Well, every single edge is a spoke, and one of its endpoints is the center vertex. So you just pick the one vertex, and you hit all of the n-1 edges of the graph. So how about a clique on n vertices? So a graph in which every single one of the n choose 2 edges is present. Why is n-1 vertices necessary and sufficient for a vertex cover? Well, to see why it's necessary, consider any set that excludes at least 2 vertices of the graph. Because it's a clique, there's an edge between those 2 excluded vertices, and that's an edge such that neither of its endpoints is in this set. So that's why the set is not a vertex cover if it has the most n-2 vertices in it. On the other hand, if it only excludes one vertex, then there cannot be an edge with both of its endpoints missing from the set, because there's only one vertex in total missing for the set. So that's why any subset of n-1 vertices will be a vertex cover of a clique. n-1 is sufficient. Figuring out the minimum size of a vertex cover in these two special graphs probably didn't seem that hard, and it's not. But when you're talking about general graphs that you don't know anything about, computing the minimum cardinality vertex cover is in fact an NP-complete problem. There is no polynomial time algorithm that solves it unless P equals NP. So that's definitely a bummer. So let's review our strategies for dealing with NP-complete problems that we discussed in an earlier video. So the first strategy is to identify computationally tractable special cases of your NP-complete problem. Now, in the best case scenario, the version of the problem that you have to solve in your own application lies squarely inside one of these computationally tractable special cases. Then you're good to go. More commonly, the instances that arise in your application won't necessarily be in one of the computationally tractable special cases, but it can still be useful to have subroutines ready for various special cases. One thing we discussed in the past is the potential of a hybrid approach. Perhaps you do a little bit of brute force search, and for most of the branches of your brute force search, the residual problem falls into a computationally tractable special case. And it turns out there's some quite interesting computationally tractable special cases of the vertex cover problem. And the story here is very much in parallel with discussions we've had in the past about the independent set problem. So in particular, you can solve vertex cover in polynomial time on path graphs, just like we did with independent sets, actually more generally in trees, or even more generally in what's called graphs of bounded tree width. But at least for trees, that's an application of dynamic programming, which you're now in a good position to solve yourself. So I encourage you to think that through as an exercise. Why can you solve the vertex cover problem in polynomial time in trees? So another quite interesting class of graphs where you can solve the vertex cover problem in polynomial time is the class of bipartite graphs. One way to think about a bipartite graph, it's a graph that has no odd cycle, so then obviously trees are a special case. An equivalent definition is that you can partition the vertex set into two groups, A and B, so that every single edge has exactly one endpoint in each of A and B. That is, bipartite graphs can also be thought of as the graphs for which there's a cut that slices every single edge of the graph. It's far from obvious how to solve the vertex cover problem efficiently in bipartite graphs, but it can be done. It's an application of what's called the maximum flow problem. That's a graph problem which lies just beyond the techniques that we're covering in this class. So what I'm going to cover in the next video is using a different algorithm, yet another computationally tractable special case of vertex cover, specifically when you're interested in the case that the vertex cover is small. And what I mean here by small is logarithmic in the number of vertices or less. A second strategy for dealing with NP-complete problems is to relax the requirement of correctness and to focus on heuristics, algorithms that are fast but need not produce an optimal solution. So there are some pretty good heuristics available for the vertex cover problem. I'm not going to discuss them here because I think that time will be better spent discussing heuristics for the knapsack problem. But you can, for example, use the greedy algorithm design paradigm to generate some heuristics for vertex cover. Now, some greedy algorithms do better than others, but if you make the greedy choices judiciously, you can get pretty good guarantees for the vertex cover problem. So the third strategy is to insist on correctness, in which case you're not expecting to get polynomial time for general instances unless you're intent on proving p equals np. And so while you're expecting an exponential running time, you still want a running time which is qualitatively better than naive brute force search. And this is exactly the point of the next video. We're going to give an algorithm which is indeed based on enumeration, but it's a smarter enumeration than naive brute force search. So we'll get a faster exponential running time, and that'll allow us to solve a wider class of problems. The goal of this video is to develop an exact algorithm for solving the vertex cover problem. The algorithm will run in exponential time in the worst case in general instances, but is nevertheless qualitatively better than naive brute force search. One consequence of this smarter search algorithm is that the vertex cover problem is computationally tractable in the special case where you're looking for a small optimal solution that uses at most a logarithmic number of vertices. Let me remind you quickly of the vertex cover problem. The input is simply an undirected graph G. A vertex cover of a graph is a subset of vertices that includes at least one endpoint of each edge of the graph. The goal in the vertex cover problem is to compute the smallest size of a vertex cover. Let's consider a variant on this problem where we're additionally given a target value k. K here is going to be a positive integer, and we want to know whether or not there is a vertex cover with size k or smaller. Now, as stated, I haven't really made the problem any easier. If you could solve this version of the problem where you're given a target k, you could also solve the original one where you want to know the smallest value of any vertex cover. Namely, just run this subroutine for all possible values of k from 1 up to n, and the smallest value of k for which you can find a vertex cover is then the answer to the original optimization version of the problem. Rather, to make the problem easier, I want to think about the special case where k is small. So for now, I'm going to be deliberately vague about what I mean by small. We'll fill in those details in due time. Now, why might you be interested in the vertex cover problem when k is small? Well, we talked, for example, one thing you might be modeling is hiring a team. Each vertex corresponds to a potential team member, someone capable of performing various tasks. A vertex cover means you hire a team that is capable of handling any task that might be thrown your way, where the edges of the graph correspond to tasks, and the endpoints correspond to the two people capable of performing the task. And you can imagine maybe you're only interested in forming a team if it has reasonable size. So you have a budget for how many people you could hire, and then you're only interested in solving the vertex cover problem when there's a good solution, a small cardinality vertex cover. Otherwise, you just punt and you're not willing to take on the project. You could also imagine maybe you have some domain expertise that suggests that your graphs do have small vertex covers. Recall, a star is just a vertex cover of size 1. So if you know that your graph is star-like in some sense, you might expect that there's an optimal solution that has few vertices. Is it useful, algorithmically, to focus on the case of k small? Well, yeah, sure. If you're looking for a small optimal solution, then brute force search isn't as bad as usual. If you want to know whether or not there's a vertex cover comprising only k vertices, you can just check every subset of k vertices. The number of subsets of k vertices, assuming that there were n to start with, would be n choose k, and for small k, that's going to be like theta of n to the k. So in principle, this naive brute force search runs in polynomial time as long as k is constant, as long as k is big O of 1. But practically speaking, I mean, you can't really imagine running this naive brute force search algorithm unless k was super small. You know, say k equal 3, maybe k equal to 4, depending on the size of your graph. In any case, this naive search is limited to very small values of k. And it's then natural to ask, as we always do, can we do better? Is there a smarter type of search? So the answer is yes, there is a smarter way to go about this search that's going to allow us to solve the problem for qualitatively larger values of k. The search algorithm is going to be driven by a lemma which is similar in spirit to the kind of reasoning we did about optimal solutions in our dynamic programming algorithms. I think it would be a little misleading to call it an optimal substructure lemma, so let me just call it a substructure lemma. So consider some input. So the job of our algorithm is to check whether some undirected graph G has a vertex cover of size k or not. Consider also some edge, let's say between u and v, of this graph. In the same way in all of our dynamic programming optimal substructure lemmas, we thought about taking the original instance and reducing it by 1 in some sense. Removing an item, removing a vertex, removing a position of the alignment, and so on. We're going to be thinking about this graph G, but with one fewer vertex. Actually, two different graphs of that form. One that we get by deleting u, that's one endpoint of the edge that we chose, and in addition to u, all of the edges incident to it. And we'll also look at the graph that we get by deleting v, the other endpoint of the edge, and all of its incident edges. I'll use the notation GU for the graph we get by deleting U, and G sub V for the graph we get by deleting V. The lemma asserts that we can reduce the question that we care about, namely does or does not G have a vertex cover of size k, to analogous questions on the smaller graphs GU and GV. Specifically, G does have a vertex cover of size k if and only if at least one of GU or GV has a vertex cover of size k minus 1. So the proof is not too hard. I'll be able to squeeze it in on this slide, and then once we know the substructure lemma is true, I'll show you how that leads to a smarter search algorithm for vertex cover. So this is an if and only if statement, so we have to have two different parts of the proof, assuming the left prove the right, assuming the right prove the left. Let's start by assuming the right-hand side. Let's assume that GU or GV or both does in fact have a vertex cover of size k minus 1. Let's show that then G must have a vertex cover of size k as well. It doesn't matter which of GU or GV has the good vertex cover. Let's just say GU. So let's think for a second about which edges of the original input graph G survive into the smaller graph GU. For the purpose of this proof, there's basically two types of edges in the world. There's ones where one of the endpoints is U, that is edges incident to U, and then there's edges where neither endpoint is the vertex U. So the edges in the graph GU are precisely those where neither of the two endpoints is U. So let's call those edges E sub U. Those are edges not incident to U, the edges in G sub U. And then we'll call the edges incident to U that got deleted f sub u. So let's call this set of k-1 vertices that's a vertex cover in G sub u, let's call it capital S. What does it mean to be a vertex cover? It means you include at least one endpoint of every edge. So S, by virtue of being a vertex cover for G sub u, it means for every edge of E sub u, that is every edge of the original graph, neither of whose endpoints is u, S contains at least one of the endpoints. So if we think about capital S in the original graph capital G, the only edges that it's missing are those of F sub u, are those where one of the two endpoints was the vertex u. Well, that means if we just take capital S and we throw in the vertex u, we get a bona fide vertex cover of the original graph capital G. S takes care of all of the edges of E sub u by definition, and then u single-handedly takes care of all of the edges in F sub u, because all of those edges are incident to u. So that's why if we assume the right-hand side, we can conclude the left. If either GU or GV, let's say GU, has a small vertex cover size of most k-1, all we need to do is augment it by the missing vertex u, and boom, we get a vertex cover of the desired size k back in the original graph G. So what about the other direction of the substructure lemma? Now we assume that the original graph G does in fact have a vertex cover of size only k, and we show that has to be reflected in one of these two subgraphs. Either GU or GV must itself have a small vertex cover, size only k-1. Let's let capital S denote this small vertex cover of the original graph G. So S has k vertices, and every edge has at least one of its endpoints represented among this set. In particular, the edge uv that we singled out at the beginning, one of its endpoints, either u or v, maybe both, but certainly one of them has to be in the set capital S. Let's say u is in S. So let's think about the pink picture from the other direction of the proof. Let's think about exactly the same decomposition of the original edge set capital E into two sets. Now this set S, remember, it's a vertex cover of the original graph G, so S contains at least one endpoint of every edge. But now U, which is one of the vertices in S, sure, it is an endpoint of every edge of F sub U, every edge incident to U, but U is not an endpoint of any of the edges in E sub U. So what that means is the other k-1 vertices of S have to be responsible for containing endpoints of all of the edges that survive into G sub U. The vertex U takes care of edges incident to it. S with U removed, those k-1 vertices include an endpoint from all of the other edges, all of the edges in E sub U. So that completes the proof of the forward direction and therefore of the substructure lemma. Let's see how this substructure lemma naturally leads to a recursive search algorithm. The algorithm is recursive. I'm not going to bother to specify the base cases, which is when you're given a graph with at most one vertex, or whether you're given a value of k equal to 0 or 1. So let's assume that the graph has at least two vertices and that k is at least equal to 2. I wouldn't be surprised if this algorithm reminds you of some of the recursive implementations we discussed for various dynamic programming algorithms. And in the same way those algorithms exhibited exponential running time without memoization, we're going to see an exponential running time here. For all of our dynamic programming algorithms, we were able to cleverly organize subproblems from smallest to largest, thereby eliminating redundantly solving the same subproblems over and over again, yielding polynomial runtime bounds. Here, we're going to be stuck with the exponential running time bound. Obviously not surprising given that it's an NP-complete problem, but still, if you really want to understand this deeply, take this recursive search algorithm, try to come up with a polynomial time version. Try to come up with a small set of subproblems ordered from smallest to largest that you can solve systematically. You will be inevitably stymied in those attempts, but you'll better appreciate what's non-trivial about the recursive solution here. In step 1 of the algorithm, we pick some arbitrary edge u, v. Why is it useful to focus on an edge? Well, by the definition of a vertex cover, it has to include either u or v. So that's our initial clue. We're going to proceed optimistically. We're looking for a vertex cover of size k, so let's assume one exists. What does the substructure lemma tells us? It says that if such a solution exists, then necessarily either GU or GV or both themselves have small vertex covers of size only k-1. Moreover, it's a simple matter to extend such vertex covers to a small one for G. You just augment them by the missing vertex. So let's first adopt as a working hypothesis that G sub u has a small vertex cover of size only k minus 1. Let's recursively try to find it. If our recursive search comes back with a solution, a vertex cover of size k minus 1 for GU, we're good to go. We just augment that by the vertex u, and that's our vertex cover of size k for the original graph G. If that recursive call fails to find a small vertex cover, we say, oh, well, then it must be that V is the key to getting a small vertex cover. So we do exactly the same thing. We recursively search G sub V for a vertex cover of size k minus 1. If the second recursive call also fails to find a small vertex cover, one of size only k minus 1, then by the substructure claim the other direction, we know that the original graph G cannot have a vertex cover of size k. If it did, the substructure lemma tells us one of the two recursive calls would have succeeded. Since they both failed, we conclude correctly that the original graph did not have a small vertex cover. The correctness analysis is straightforward. Formally, you would proceed by induction. So the inductive hypothesis would then guarantee the correctness of the two recursive calls. So on the smaller subproblems GU and GV, the recursive calls correctly detect whether or not there are vertex covers of size k minus 1. The substructure lemma guarantees that we correctly compile the results of the two recursive calls into the output of our algorithm. So if one of the two recursive calls succeeds, we're good to go. We just output the vertex cover of size k as desired. And this is the crucial part. If both of the recursive calls fail, then by the substructure lemma, we know we correctly report fail. We know there is not a vertex cover of size k or less in the original graph G. So let's analyze the running time using an ad hoc analysis. Let's think about the number of recursive calls that there can be over the entire trajectory of the algorithm, or equivalently, the number of nodes in the recursion tree generated by the algorithm. And then we'll come up with a bound on how much work is done in a given recursive call, not counting the work done by its recursive subcalls. And now the cool part, and this is really where the role of a small value of k comes into play, is that each time we recurse, we subtract 1 from the target size of a vertex cover that we're looking for. Remember, if we are given as input the parameter k, each of our recursive calls involves the parameter value k minus 1. So what this does is limit the recursion depth, or the depth of the recursion tree generated by this algorithm, to be at most k. Initially, you start with k. Each time you recurse, you decrement it by 1. You're going to hit base cases by the time k is around 1 or 0. Putting those two observations together, branching factor bounded by 2, recursion depth bounded by k, the number of recursive calls in total over the entire lifetime of this algorithm is going to be bounded by 2 to the k. Moreover, if you inspect the pseudocode, you see that not a whole lot of actions going on other than the recursive subcalls. So even with a very sloppy implementation where you have to construct G sub u and G sub v from the input graph G, even if you do that crudely, you're going to get a linear time bound, big O of m work per recursive call, not counting the work that gets done later by the recursive subcalls. So that means an upper bound on the total amount of work done by this algorithm is the number of recursive calls 2 to the k times the work per call m, 2 to the k times m. Now this running time, you'll of course notice, is still exponential in k, but of course it has to be exponential unless we intend on proving p equals np. Don't forget, the vertex cover problem is NP-complete. So what have we accomplished? We had a trivial exponential time algorithm by brute force search earlier. Why did we go through this rigmarole to come up with a second algorithm with this exponential runtime bound? Well, this is a qualitatively better running time bound than we had before with naive brute force search. Here's 2 ways to see why this running time bound is qualitatively superior. So first, let's just inspect this running time from a mathematical perspective, and let's ask how large can we take k while still having a polynomial time algorithm. Recall that our naive brute force search algorithm, where you just try each subset of k vertices, ran in time theta of n to the k, and so that's polynomial time if k is constant, and it's super polynomial time if k is bigger than a constant. For this running time bound 2 to the k times m, we can let k grow as large as log of the graph size and still have a polynomial time algorithm. So now let's segue from these mathematical bounds to thinking through actually implementing these algorithms and running them on actual data. So for the naive brute force search, you've got this running time of n to the k. And even for a relatively small graph, let's say n is maybe 50 or 100, you're not going to be able to run this naive brute force search algorithm except for extremely small values of k. 3, 4, maybe 5 if you're lucky. So naive brute force search has very limited range of applicability. So by contrast, our smarter search algorithm can accommodate a noticeably larger range of k's. So remember, the running time here is 2 to the k times the graph size. And so even for values of k up to 20, for many networks of interest, you're going to be able to implement and run this algorithm in a reasonable amount of time. In this video and the next, we're going to revisit the famous traveling salesman problem. When we first talked about TSP, it was bad news. The context was NP-completeness. We discussed Edmonds' conjecture that it's widely believed there's no known polynomial time algorithm for solving the TSP problem. But let's talk about some good news, the fact that you can do better than naive brute force search. In fact, it's going to be another neat application of the dynamic programming algorithm design paradigm. So let me remind you briefly about the traveling salesman problem. The input, very simple, just a complete undirected graph, and each of the n choose 2 edges has a non-negative cost. The responsibility of the algorithm is to figure out the minimum cost way of visiting each vertex exactly once. That is, you're supposed to output a TOR, a permutation on the vertices, that minimizes the sum of the corresponding n edges. For example, in this 4-vertex pink network, the minimum cost TOR has overall cost 13. You could, of course, solve the problem using brute force search. The running time of brute force search would be roughly n factorial. This would allow you to solve problems with, say, 12, 13, maybe 14 vertices. In this video and the next, we'll develop a dynamic programming algorithm that solves the TSP problem. Now, of course, TSP is NP-complete. We have to respect that. We're not expecting a polynomial time algorithm. But this dynamic programming algorithm will run quite a bit faster than brute force search. The running time will be big O of n squared times 2 to the n. 2 to the n is, of course, exponential, but it's quite a bit better than n factorial. N factorial is more ballpark n to the n. Okay, if you look up Stirling's approximation, you'll see it's really n over a constant raised to the n, but still that's much, much bigger than a constant 2 raised to the n. To make it more concrete, you could run this dynamic programming algorithm for values of n probably pushing 30 or so. So I realize these are still pretty absurdly small problem sizes compared to the size of the arrays that we can sort, compared to the size of the graphs on which we compute strongly connected components or shortest paths, but that's how it goes with NP-complete problems. You have to work pretty hard even to solve modest-sized problems. So at least this dynamic programming algorithm proves the point that even for NP-complete problems, there are opportunities to improve over brute force search, and the programmer toolbox I've already equipped you with is sufficient to make some of those improvements. For the traveling salesman problem in particular, it's been a benchmark problem for the development of tools and optimization, and people have worked very hard to solve very large instances of the traveling salesman problem, even with tens of thousands of cities, even sometimes over 100,000 cities. But, I mean, this often represents years of work. As I said earlier, there's some really nice sort of popular accounts of the traveling salesman problem books out there. Check it out if you want to know more about the state of the art for solving large TSP instances. So I said we're going to pursue a dynamic programming approach to the TSP, so that means we should be looking for optimal substructure, a way in which an optimal solution must necessarily be composed of an optimal solution to a smaller subproblem extended in some easy way to the original problem. So what could that look like for TSP? So of all the problems that we've tackled using dynamic programming, I think the one which seems the most like TSP is single source shortest paths. So think about a TOR not as a cycle exactly, but as a path from some vertex, let's say vertex number 1, looping all the way back to itself, with of course the constraint that it should visit each other vertex exactly once en route. We want to minimize the overall cost of this path from one back to itself, so that sounds a lot like wanting to minimize the length of a path from some source to some destination. And I'm sure you'll recall that our dynamic programming algorithm for the single source shortest path problem was the Bellman-Ford algorithm. So what then did the subproblems look like in the Bellman-Ford algorithm? Well, the cool idea there was to measure subproblem size using an edge budget. So a canonical subproblem in Bellman-Ford was to compute the length of a shortest path from the given source vertex to some destination vertex v that has I edges or less. So by analogy, we could think here about subproblems where we want the shortest path from the starting node vertex number 1 to some other vertex, j, that uses at most I edges. So precisely, let's define subproblems as follows. For a given choice I, this represents the number of edges that you're allowed to use. A given destination j, let's assume the vertices are just named from 1 to n, so I'll call a generic destination j an integer from 1 to n. Let's denote capital L sub ij as the shortest length of a path from the starting vertex 1 to this destination j using at most I edges. So suppose we try to set up a dynamic programming algorithm using these subproblems. What do you think? Can we use these to get a polynomial time algorithm for the TSP problem? All right, so the correct answer is C. So this proposed collection of subproblems does not yield a polynomial time algorithm. That is, D is not the correct answer. That would be surprising, right? TSP is an NP-complete problem, so if this gave a polynomial time algorithm, we could all report directly to the Clay Institute for our $1 million cash prize. Now, there's a lot of students in this class, but at least we'd each get 20 bucks or so out of the deal. So that's not the case. This is not going to yield a polynomial time algorithm. What's the problem? Well, the problem is also not A. It's not that there are too many subproblems. We only have O of n choices for I and O of n choices for j, so there's only a quadratic number of subproblems, just like in Bellman-Ford. That's totally reasonable. We also can correctly compute the value of larger subproblems from smaller ones. It's really exactly the same as what we were doing in Bellman-Ford. The problem is that our semantics are incorrect. By solving these subproblems, we don't actually get an optimal solution to the traveling salesman instance that we started with. So what are we hoping is going to be the case? Well, in our dynamic programming algorithms thus far, after we solved all of the subproblems, the answer to the original question was just lying there waiting for us in the biggest subproblem. So here the biggest subproblem would correspond to I equaling n, where you're allowed to use up to n edges in your path. The issue with these subproblems is they only specify an upper bound I on the number of edges you're allowed to use. They does not enforce that you have to use your full budget of I edges. So that means when we look at these biggest subproblems, yeah, the shortest paths could use as much as n edges if they wanted, but in general they won't. They'll use much fewer than n edges, they'll skip tons of the vertices, and that's not a traveling salesman tour. A traveling salesman tour has to visit every vertex once. That is not enforced by these subproblems. That problem doesn't seem so hard to fix. Let's just insist in each subproblem that instead of using at most I edges in the shortest path, it has to use exactly I edges in the shortest path. So while this set of subproblems is not quite as misguided as the previous one, the answer remains the same. The answer is still C. Of course, we still don't get a polynomial time algorithm. We're not planning to prove P equals NP. The number of subproblems hasn't changed. It's still quadratic. And if you think about it, you can still efficiently solve for bigger subproblems with a bigger edge budget, given the solutions to all of the smaller subproblems. So what's the issue? The issue is that our semantics are still incorrect. Just because you solve all of these subproblems doesn't mean you can extract from it the cost of a minimum cost traveling salesman tour. So the problem, briefly, is that we don't enforce the constraint that you can't visit a vertex more than once. What were we hoping would be true? We were hoping that when we look at the biggest subproblem, so this is when I is equal to n, and we're looking at paths that have exactly n edges, and when we take j, the destination, to be 1, the same as the origin, we were hoping that that shortest path with n edges from 1 back to itself would be a tour, and therefore the minimum cost traveling salesman tour. But that need not be the case. Just because this path has n edges and it starts at 1 and it ends at 1 doesn't mean it's a tour. It might, for example, visit vertices 7 and 23 twice, and as a result, it never visits vertices 14 or 29 at all. For this reason, the number computed by the largest subproblem when I equals n and when j equals 1, that can be much, much smaller than the true answer for the minimum cost traveling salesman tour. A good algorithm designer is nothing if not tenacious, so let's just recognize the flaw in this proposal that we're not enforcing the fact that you can't have repeat visits to a vertex, and let's just change the subproblems yet again to explicitly disallow repeated visits to a vertex. So precisely, let's index the subproblems in exactly the same way as before. There's going to be one for each budget I and one for each destination j. For a given I and a given j, the value of the subproblem is now defined as the length of a shortest path beginning at 1, ending at j, using exactly I edges with the additional constraint that no repeated vertices are allowed. The one exception being that if j is equal to 1, then of course you're allowed to have 1 at the beginning and 1 at the end. But for the internal vertices in a shortest path, we do not allow repeats. So what do you think? Does this refined collection of subproblems allow us to get a polynomial time algorithm for the traveling salesman problem? So the answer to this quiz is more subtle than the past couple, and the correct answer has switched from C to B. It's still the case that there's a quadratic number of subproblems. It's still the case that we don't expect a polynomial time algorithm. But now that with this different definition of subproblems, they do capture the TSP. Specifically, look at the biggest subproblem. Take I equal to n, take j equal to 1. The responsibility of that subproblem is to compute the shortest path from 1 to 1 that has exactly n edges and no vertices repeated internally. That is exactly the original problem that we started with. That is exactly TSP. The issue is that you cannot efficiently solve larger subproblems, problems with a larger edge budget, given the solutions to the smaller subproblems. The smaller subproblems are just not very useful for solving the bigger subproblems. And the reason is a little bit subtle. Now the hope would be that, like in all our previous dynamic programming algorithms, you can just formulate a recurrence which tells you how to fill in, how to solve bigger subproblems given solutions to smaller ones. And there's even a natural guess for these subproblems what you hope the recurrence might be. Recurrences generally follow from a thought experiment about what optimal solutions have to look like. So you'd want to focus on a particular subproblem, a given destination j, and a given budget I on the number of edges. You'd say, well, let's think about an optimal solution. So what is that? That's a path. It starts at 1. It ends at j. It has exactly I edges. It has no repeated vertices. And amongst all such paths, it has the minimum length. And it's natural to proceed by analogy with Bellman-Ford and say, well, wouldn't it be cool if a little birdie told me what the penultimate vertex k was on this shortest path from 1 to j? So if I knew that the second to last vertex on a shortest path was k, well then surely the length of this path would be the length of an optimal path from 1 to k using exactly I minus 1 edges and no repeated vertices with this final hop kj concatenated at the end. Now, of course, you don't know what the second to last vertex k is, but no big deal. As usual in dynamic programming, we're just going to try all of the possibilities. So we can encode this brute force search as a minimum over the sensible choices for k. Clearly, k should not be equal to j. It should be some other vertex that precedes j. And ignoring some base cases, let's also preclude k from being 1. That's the starting vertex. And of course, pictorially, what we have in mind is we have in mind taking some shortest path from 1 to k. So we'd look that up. That would be previously computed in some smaller subproblem, and then concatenating to it a final hop that goes from k to j. Well, hey, that sounds pretty good, right? Doesn't that kind of sound like maybe this is the key ingredient to a polynomial time algorithm for TSP? So what's the problem? Well, the problem is that we've defined our subproblems to disallow repeated visits to a vertex. So when we compute a subproblem, we better make sure we're respecting that constraint, that no repeated visits are allowed. And if we have in our mind concatenating a shortest path from 1 to k with no repeats with this final hop k to j, well, this might result in a repeated visit to j. In particular, for all we know, the shortest path from 1 to k that uses exactly I minus 1 edges and has no repeated vertices, that path might well go through j, in which case concatenating this final hop kj results in a cycle, a second visit to j. So this bug means that the proposed recurrence is not correct. The recurrence is computing something which in general is less than the actual shortest path length from 1 to j with exactly I edges with the no repeat visits constraint respected. That could be a bigger number than what's computed by this recurrence. And I encourage you to think about, is there any way to fix this bug? Could you propose a different, more complicated recurrence, which was still easy to evaluate, but was actually getting the subproblem value correct? I don't think you're going to find one. So the moral of the story is that this constraint in the traveling salesman problem that each vertex gets visited exactly once, that's a quite tricky constraint, and we're going to have to work quite hard to make sure it's satisfied. The solution we're going to use is in some sense a logical next step from this recurrence here. We need to be able to know more information about subproblems than just where they end. We actually need to know the identities of the vertices on the path used to travel from 1 to k. We need to know whether or not v is on that path. So we're going to look at a much bigger set of subproblems where we remember not just destinations, but also all of the intermediate stops. That idea will translate to a dynamic programming algorithm, not a polynomial time one, needless to say. The details are coming right up. Having laid the groundwork in the previous video, we're now ready to follow our usual dynamic programming recipe to develop a faster than brute force search dynamic programming algorithm for the traveling salesman problem. Iterating through all of those quizzes in the last video, we developed some healthy respect for the traveling salesman problem. We understood why the more natural approaches, which were sufficient for the shortest path problem, for example the Bellman-Ford algorithm, are not good enough to solve TSP. Now, no surprise, TSP is an NP-complete problem, so we were sort of ready for this, but we now understand it in a pretty concrete way. In the single source shortest path problem, in a subproblem, all you need to know is where is the path ending and how long could the path be. That's not enough for the traveling salesman problem because there's this extra tricky constraint that at the end of the day we want to visit every vertex exactly once. So in particular, to make sure we don't have repeat vertices show up in our subproblem solutions, we're going to need to remember not just where smaller subproblems end, but also the identities of all of the intermediate vertices in the path. Here then is the final definition of the subproblems that we're going to use. We still want to keep track of where this path ends, so we still have our destination j. But rather than just specifying a number of vertices that you visit on this path, we specify exactly which vertices get visited. So that's going to be a subset, capital S, a subset of 1 through n, and of course it better contain the initial vertex 1 and the final vertex j. And so for a given choice of j and a given set choice of capital S, we define L sub S comma j as the length of a shortest path that starts at vertex 1, ends at vertex j, visits precisely the vertices in capital S exactly once each. Now I can understand if your eyes widen a little bit when you see this definition. After all, there's an awful lot of choices for this set capital S, an exponential number. So you'd be right to wonder whether this approach could possibly give any savings whatsoever over naive brute force search. One thing worth pointing out, and in some sense the source of the computational savings, is that in a given subproblem, while it's true we're keeping track of which vertices are visited en route from 1 to j, we are not keeping track of the order in which those vertices get visited. And indeed, if we had one subproblem for every ordering in which you might visit vertices from a given source to a given destination, then we'd be stuck with a factorial number of subproblems. As it is, since we forget the ordering, we only focus on subsets, that gets us down in more than 2 to the n range. And that's ultimately where the savings over brute force search comes from. So as usual, once we've gotten the right set of subproblems, the rest of the dynamic programming recipe pretty much writes itself. But to fill in the details, let me just tell you exactly what the optimal substructure limit is, what's the corresponding recurrence, and then the final pseudocode that gives us our better than brute force search algorithm for the traveling salesman problem. So for the optimal substructure lemma, we just focus on one particular subproblem. So that corresponds to a choice of the destination j and a choice of the set S. It specifies 1, the starting point, j, the ending point, plus the rest of the intermediate vertices that we've got to visit along the way, exactly once each. So now we proceed exactly as we did in Bellman-Ford, namely by focusing on the last hop of this path P. So if the last hop is, say, from vertex k to vertex j, then we can look at the previous part of the path, call it P prime. What can we say about it? Well, clearly it begins at the vertex 1. Clearly it ends at the vertex k. Because the path P visited every vertex in S exactly once, the path P' visits every vertex in the set S minus J exactly once. And, of course, the optimal substructure lemma says not only is P' some path from 1 to K, visiting exactly the vertices of S minus J once each, it is the shortest such path. The proof is an utterly standard cut and paste argument like we've been doing for all our other optimal substructure lemmas. I'll leave it as an exercise for you to fill in the details. As usual, the optimal substructure lemma naturally induces a recurrence. The recurrence just says, well, let's look at all of the candidates for an optimal solution identified by the lemma and do brute force search among all those candidates. That is, for a given subproblem indexed by a destination J and a set of vertices S, what the recurrence does is it takes the best case scenario, that is the best choice of the second to last vertex K. Of course, K should lie somewhere in the set capital S. Also, it should not be the vertex J. And for a given choice of K, we know the corresponding candidate solution has to be a shortest path from 1 to K, visiting exactly the vertices of S minus J, combined with the cost of the corresponding final hop from K to J. And effectively, we're using the same measure of subproblem size that we were in the Bellman-Ford solution, just the number of allowable intermediate vertices. Of course, here the subproblem also specifies exactly which those vertices are, but as far as a measure of size, we just use the cardinality of that set. As always, the important property of the size measure is that to solve a subproblem of a given size, you only need to know the answers of subproblems with strictly smaller size, and staring at the recurrence, you see that that is indeed the case here. You only care about subproblems that visit one fewer vertex, because in particular, J is excluded. The dynamic programming algorithm writes itself. We have a two-dimensional array, 2 dimensions, because we have 2 indices for each subproblem, one specifying the final vertex J, the other specifying the set capital S. It turns out we can get away with a pretty small set of base cases. We're only going to need to pre-compute the entries of the 2D array in which the final destination J equals 1, is the same as the starting vertex. Now, if S happens to contain just the vertex 1, then the empty path goes from 1 to 1 with no intermediate stops. That has length 0. Otherwise, if S contains extra vertices, there's no way to go from 1 back to 1 with intermediate stops, visiting vertex 1 only once. So we define the other subproblems where J equals 1 to have plus infinity value. Now, as usual, we solve all the subproblems systematically using the recurrence. We want to make sure that all the smaller subproblems are solved before the bigger ones. So in our outer for loop, we iterate over the measure of subproblem size, which remember is the cardinality of the set S. Amongst subproblems of the same size, we don't care what order we solve them. So we just iterate through the sets S of cardinality M in arbitrary order. So these outer 2 for loops accomplish the following. They iterate through the relevant choices of capital S. That is, sets S that have cardinality at least 2 and that contain the vertex 1. So that's the first index of our 2D array. What about the second index, J? So this is where the shortest path in a given subproblem is supposed to stop. Well, subproblems only make sense, or only defined, if that final vertex J is one of the vertices capital S that you're supposed to visit. So when we get to a given choice of capital S, at that point we're just going to iterate through all of the relevant choices of J. And if you recall our argument in the base case and the fact that the set S has size at least 2, there's no point in trying J equals to 1. So now that we have a subproblem, we have our choice of S, we have our choice of J, we just compute the recurrence for this particular subproblem. So what is that? Well, we take a best case choice of the penultimate vertex. So that's some vertex that we've got to visit, a vertex K in capital S, other than the one where we stop. So it can't be equal to J. And then, given a choice of K, what is the corresponding solution of that candidate path from 1 to J? Well, it's whatever the shortest path is from 1 to K, which of course is visiting everything in S except for J, plus whatever the cost of the final hop is from K to J. So the recurrence just figures out what is the optimal choice of k by brute force search, and then by our optimal substructure lemma, we know that's the correct answer to this subproblem. Now, in almost all of our dynamic programming algorithms, after we solved all the subproblems, all we did was return the value of the biggest one. Here we actually have to do a tiny bit of extra work. It is not the case that the solution we care about, the minimum cost traveling salesman tour, is literally one of the subproblems. However, it is true that we can easily compute the minimum cost of a traveling salesman tour given solutions to all of the subproblems. So what is the biggest subproblem? Well, there's actually n of them. Remember, our measure of subproblem size is the cardinality of the set S, the number of vertices that you've got to visit in that subproblem. So in the biggest subproblems, S is equal to everything. You have to compute a shortest path that visits each of the n vertices exactly once. So what are the semantics of one of those subproblems for a given choice of the second index j? There's n different choices for that final vertex j. That subproblem was responsible for computing the length of a shortest path that starts at the vertex 1, that concludes at the vertex j, and that visits every single vertex exactly once. Now, how is this different than a traveling salesman tour? Well, all that's missing is that final hop, that hop from j to 1. So what this means is that after we've solved all of the subproblems in our triple for loop, we can complete the algorithm with one final brute force search. This final time the brute force search is over the choice of j, the last vertex that you visit, before you return home to vertex number 1. So you can skip the choice of j equal 1, that one doesn't make sense, but for the other n-1 possibilities for that final vertex j, you take the previously computed value of a shortest path that starts at 1 and goes to j and visits everybody exactly once. You tack onto that the cost of the final hop, going home to 1 from vertex j, and of those n-1 different solutions, you return the best of them. That is in fact the cost of the minimum cost traveling salesman tour. The correctness argument is the same as it always is. The correctness of the optimal substructure lemma implies the correctness of the recurrence, and then the correctness of the dynamic programming algorithm follows from the correctness of the recurrence plus induction. The running time is equally straightforward. So because in the subproblems we're keeping track of a lot of information, specifically the identities of all of the intermediate vertices, there are a lot of subproblems. So in particular, there's roughly 2 to the n choices for the set capital S. There's roughly n choices for the final destination j. So combining those, we get n times 2 to the n subproblems. How much work do you do per subproblem? Well, you have to execute this brute force search over the choices of the vertex k, the second to last vertex on the path. K could be almost anything in the set capital S. Capital S could have linear size. So you're going to do O of n work per subproblem. Thus, the overall amount of work, as promised, is big O of n squared times 2 to the n. This is still exponential time. There's still severe limits on how big a value of n you're going to be able to execute this algorithm for. That said, the problem is NP-complete, and you have to respect its computational intractability. And again, at least this shows there are often interesting algorithmic opportunities to beat brute force search, even for NP-complete problems like the traveling salesman problem. This sequence of videos is about the design and analysis of heuristics, algorithms which are generally guaranteed to be fast, but not guaranteed to be 100% correct. As a case study, we're going to revisit the knapsack problem that we thought about earlier in the dynamic programming section. Let's briefly review the 3 strategies for dealing with NP-complete problems. All of these are relevant for the knapsack problem. The first strategy is to identify computationally tractable special cases of the NP-complete problem that you're grappling with. If you're lucky, the instances relevant for your application will fall squarely into one of these computationally tractable special cases. Even otherwise, it's useful to have these kinds of subroutines lying around. Perhaps with a little bit of extra work, you can reduce your problem instances to one of these computationally tractable special cases. A dynamic programming solution for the knapsack problem identifies one such special case, namely knapsack instances where the knapsack capacity is small. For example, if it's comparable to the number of items. The second approach is the design and analysis of heuristics, algorithms which are not guaranteed to be 100% optimal. I'll have more to say about those in a second. The third strategy is to insist on a correct algorithm, and being an NP-complete problem, you're then expecting to see exponential running time, but still to have running time qualitatively better than what you'd achieve with naive brute force search. Our dynamic programming solution to the knapsack problem can be viewed as a contribution in this direction. Naive brute force search, enumerating over all possible subsets of items, is going to take time proportional to 2 to the n, where n is the number of items. The dynamic programming algorithm takes time proportional to n, the number of items, times capital W, the knapsack capacity. For most problems of interest, this dynamic programming solution, albeit exponential for reasons we've discussed in the past, will be a significant improvement over naive brute force search. Let's now return to the subject of heuristics, the topic for today. Happily, despite being NP-complete, the knapsack problem admits some quite useful heuristics. We're going to study 2 of them. First, we'll use the greedy algorithm design paradigm to come up with a pretty good heuristic. Pleasingly, this pretty good greedy heuristic is also blazingly fast. We'll then pull out a different tool, namely dynamic programming, to develop yet another heuristic. It's going to be polynomial time, not as fast as the greedy solution, but its accuracy will be excellent. It will get within a 1 minus epsilon factor of optimal, where epsilon is a parameter that we can tune as we wish. Now, there's zillions and zillions of algorithms in the world, and anybody can write one of them down. So if someone proposes an algorithm to you, the onus is on them to convince you that it's a good idea, to convince you that it's, in some sense, a good algorithm. Canonically, in these courses, I've been making that argument in 2 ways. First of all, I provide you with an argument that the algorithm that I propose is correct. It always is guaranteed to solve the problem that we're interested in. Secondly, I argue that it solves the problem using a reasonable amount of resources. So one great exhibit A would be, say, Dijkstra's algorithm. We wanted to solve the shortest path problem with a single source and non-negative edge lengths. I gave you a proof that Dijkstra's algorithm always successfully achieves that goal, and I showed you an implementation so that the running time was not much more than what it takes to just read the input. Now, of course, this best case scenario is not going to be realized for NP-complete problems, and in particular for the knapsack problem. So you have to give up either on the correctness or on the running time. You have to make a compromise. A tricky question then is, how do you argue that the compromise you're making is not overly severe? How do you argue that your approach to an NP-complete problem is a good one? Heuristics relax correctness, and so one would like an argument that says correctness is not relaxed by too much. In the best case scenario, when you propose a heuristic, you should supply a performance guarantee which says that the solution is almost correct in some sense on every single instance, or failing that, at least on many instances of interest. Now, in practice, you do bump into problems that are so hard you wind up having to resort to heuristics where you really don't have a good understanding of how or when they work, where you really just cross your fingers, run the heuristic, and hope for the best. Local search is probably the preeminent example of this type of heuristic, something like the k-means algorithm for clustering. But for the problem we're going to talk about today, we're going to seek out heuristics that have worst-case performance guarantees. And of course, a broader theme of this discussion, and the reason I'm using knapsack as an example, is this will show us how our programmer toolbox, our algorithm toolbox, is now rich enough to design not just lots of different exact algorithms, but also lots of useful heuristics for NP-complete problems. So let me briefly remind you what the knapsack problem is. As input, we are given 2 n plus 1 numbers. There's n items. Each one has a positive value and a positive weight. The final number is a knapsack capacity, capital W. The goal is to pack the knapsack with the most valuable set of items. That is, you're seeking out a subset S of items, and it should have the property that the sum of the sizes of the items in your set S is bounded above by the knapsack capacity, capital W. Subject to that constraint, your subset of chosen items should maximize the sum of the values. This is a fundamental problem that comes up all the time, in particular as a subroutine. Really, whenever you have a constrained resource that you want to use in the best way possible, that's basically the knapsack problem. So let's turn to heuristics for the knapsack problem. So now that I've told you that we're happy with heuristics, we're willing to relax correctness, this all of a sudden resuscitates the greedy algorithm design paradigm as a feasible approach to the knapsack problem. Because the knapsack problem is NP-complete, we certainly are not expecting to find an exactly correct greedy algorithm, but maybe there's a greedy algorithm which is pretty good, and we're expecting most greedy algorithms are going to run extremely quickly. So let's talk through a potential greedy approach to the knapsack problem. Probably the first idea you'd have would be to consider the items in some order, and when you consider an item, you make an irrevocable decision at that point whether to include it in your solution or not. So the question then is, in what order should you look at the items? Well, what's our objective? Our objective is to maximize the value of our set. So obviously high value items are important. So maybe the first idea would be to sort the items from highest value to lowest value. But if you think about that proposal for, say, 30 seconds, you quickly realize that this is a little naive. This is not the whole story. If you have a high-value item that fills up the whole knapsack, it seems like that's not quite as useful if you had an almost as high-value item that basically had size close to 0, that didn't use up any of the knapsack at all. Remember that each item has two properties, not just its value, but also its size, and both of these are important. We want to prefer items that have a lot of value, but we also want to prefer items that are small. So I hope many of you are now sensing a strong parallel between the present discussion and the discussion we had with our first serious study of a greedy algorithm. That was scheduling jobs on a single machine to minimize the sum of the weighted completion times. In that old scheduling problem, just like in this one, each object had two parameters. Back then it was a job length and a job weight or a job priority, and you had a preference for jobs that were higher weight, you wanted them to be first, and you had a preference for shorter jobs, you wanted them to be first. Here again, we have items, two parameters, the value and the size. High value is good, low size is good. Back in the scheduling problem, the key idea was to look at jobs ratios and schedule in that order. By analogy, here in the knapsack problem, if we want to take the two parameters of each item, form a single parameter by which we can then sort the jobs, a natural first cut to look at is a ratio. Since we prefer high values and we prefer low weights, the sensible thing to look at is the ratio of the value of an item divided by its size, and we're then going to consider items from the highest values of these ratios to the lowest values of these ratios. One way to think of this is that we consider the items in order of non-decreasing bang per buck. We're always trying to get the most value for our money, where money is the amount of the knapsack capacity that we're spending. So now that we have our greedy ordering, we just proceed through the items one at a time, and we pack the items into the knapsack in this ordering. Now, what happens here, and didn't actually trouble us in the scheduling problem, is at some point we might no longer be able to pack items into the knapsack. The thing might get full. So once that happens, once we reach an item which doesn't fit in the knapsack, given the items that we've already packed into it, we just stop the greedy algorithm. So if you think about it, the way I've written this algorithm, aborting as soon as you fail to pack one item, is not really what you would do in practice. You'd do something a little bit smarter. If you fail to pack some given item, say item k plus 1, well, maybe item k plus 2, yeah, it has a worse ratio, but maybe it's much smaller. Maybe item k plus 2 does fit in the knapsack, and then there's no reason not to just take it. So in practice, you'd go through the entire list of items, and you would just pack whatever fits, skipping whatever doesn't fit. For simplicity, I'm going to go ahead and analyze this slightly worse heuristic in the slides to follow. So just a real quick example, let's consider the following 3-item instance. So I've taken the liberty of sorting the items by ratio. The first item has value 2 and size 1 for a ratio of 2. The second item has a ratio of 4/3, value 4, size 3. And the third item has a ratio of 1, value and weight equal to 3. Let's say the knapsack capacity is 5. So what does the greedy solution do? It first packs in item number 1. Then there's a residual knapsack capacity of 4, so there's room for item number 2. It packs that. Now there's a residual knapsack capacity of only 1, so there isn't any room for item number 3, so it halts. So the greedy algorithm is just going to output the set 1, 2. In this particular example, you'll notice that this greedy solution of value 6 is in fact the optimal solution. You can't do better. But let's look at a second example with just 2 items. So in this particular instance, what is the value of the output of the greedy algorithm, and what is the value of an optimal solution? So the correct answer is A. Since the knapsack capacity is 1,000 and the sum of the sizes of the jobs is 1,001, there's no room for both of them. The greedy algorithm, unfortunately, because the first tiny item has a smaller ratio, will pack in item number 1, and that leaves no room for item number 2. So the value of the greedy algorithm solution is just 2, whereas the optimal solution is, of course, to just take the second item. Yeah, its ratio is worse, but on the other hand, it fills up the whole knapsack, and so overall your value is 1,000, which obviously blows away the greedy solution. This quiz shows that, at least for general instances, the greedy knapsack heuristic we've devised thus far can be arbitrarily bad. It can be terrible with respect to an optimal solution. There is, however, a simple fix to address this issue. We're going to add a very simple step 3 to our greedy heuristic. So the new step 3 is just going to compare 2 different candidate solutions and return whichever one is better, whichever one has a bigger total value. The first candidate is just what we were doing before. It's just the output of step 2 of the algorithm. The second candidate is whichever item by itself has the maximum value. In other words, this new greedy algorithm, it just runs the old one, but then it does a final sanity check. It looks at each item individually and it says, well, if this item just by itself dominates the solution I've computed thus far, I return this single item by itself instead. There's no question that adding this new step 3 fixes the problem in the quiz on the last slide. If you add this step 3, then we will choose that item that has value 1,000 instead of the lousy solution of value 2 that we computed in step 2. But it may seem that this step 3 is just kind of a hack meant to address that specific instance. But remarkably, just adding this step 3 transforms this greedy heuristic into one that has a reasonably good worst-case performance guarantee. Precisely, the value of the solution computed by this 3-step greedy algorithm is always at least 50% of the value of an optimal solution. So the jargon for this kind of algorithm is a 1/2 approximation algorithm. For every instance, it's guaranteed to compute a solution with value at least 1/2 that of an optimal solution. Also, as you would hope from a greedy heuristic, it runs extremely quickly. Basically, all we do is sort the items, so the running time is O of n log n. In the next video, we'll provide a proof of this theorem, and as we'll see, under some additional assumptions about the type of instance, the performance guarantee will in fact be much, much better than 50%. Let's now turn to the analysis of our 3-step greedy heuristic for the knapsack problem and show why it has a good worst-case performance guarantee. So the goal is to prove that the value of the solution output by this 3-step greedy algorithm is always at least half the value of an optimal solution, a maximum value solution that respects the knapsack capacity. The key idea behind the analysis is a thought experiment in which we use, as a yardstick, an algorithm which gets to cheat. Recall that in step 1 of our greedy heuristic, we sort the items in non-increasing order of bang per buck, that is, via the ratio of the value over the size. In step 2 of the greedy heuristic, we pack the items in this order. So maybe the first k items for some value of k in this order fit into the knapsack, but then we don't have room for item k plus 1. And at that point, we stop this step of the heuristic. The thought experiment is to imagine that our algorithm gets to cheat and pack a fraction of this item k plus 1 into the knapsack to fill it up fully. So for example, if we pack in the first k items, and after that there's only 7 residual units of capacity in the knapsack, and suppose item k plus 1 has size 10, then we envision taking 70% of item k plus 1 and filling up the knapsack with that fraction. The value, let's say it's prorated. So let's say by filling in 70% of the item into the knapsack, we get 70% of its value. So we're going to call the output of this cheating algorithm the greedy fractional solution. So just to give a super simple example, imagine you had a knapsack of capacity 3 and you had 2 items both of size 2. Let's say one has value 3, one has value 2. Well, then in the greedy fractional solution, you begin by considering item 1 that has the higher ratio of 3/2. That fits fully into the knapsack. Then you move on to item 2. It only fits 50% into the knapsack. And the total value of the solution would be the full value of item 1, that's 3, plus 50% of the value of item 2, so that adds 1 more. So the value of the greedy solution here would be 4. The greedy fractional solution would be 4. In the next quiz, I'm going to ask you to ponder what properties this greedy fractional solution has relative to feasible solutions of the knapsack instance. The correct answer is D. The greedy fractional solution is always at least as good as the best non-fractional solution, and in fact it can be strictly better. Indeed, if you look at the last slide in that simple 2-item example, in that instance the greedy fractional solution is better, strictly better than every single feasible solution. Now, it's not going to be strictly better in every single instance, because there's going to be instances where the greedy fractional solution happens to use no fractions. It happens to just fill the knapsack fully using 100% of various items, and then there's no way that can be better than an optimal non-fractional solution. So I'm not going to prove this fact for you in gory detail, but let me give you just an outline of the argument. So the claim is that the greedy fractional solution of a knapsack instance is guaranteed to be at least as good, have at least as large a total value as every feasible solution, that is, every non-fractional solution. The proof of this would fit in fantastically in the greedy algorithms section of this course. That's really what it is. One way you can prove this formally is using an exchange argument. That's what I'll sketch at a high level here. I'll leave it as an exercise to you to fill in the details, but it's really very similar to our proof of optimality for the greedy algorithm for why sorting by ratios minimizes the weighted sum of completion times of a bunch of jobs on a single machine. So how should we proceed? We have to prove that the greedy fractional solution is as good as every feasible solution, every non-fractional solution. So fix such a solution, call it S. This is a subset of items that fit into the knapsack. So you could imagine, for example, a scenario in which the greedy fractional solution packs item number 1, and then item number 2 doesn't fit into the knapsack, but if we take 80% of item number 2, then that fully fills up the knapsack. So that might be the greedy fractional solution, and maybe we're thinking about a non-fractional solution where item 1 is equally well packed there, but instead of item 2, which wouldn't fit, it uses item 4, which is smaller. And then maybe there's some little bit left over of unfilled knapsack capacity for this non-fractional solution, capital S. So the interesting case is where S packs some stuff that the greedy fractional solution does not, and let's suppose it uses up L units of the knapsack capacity via items which are not packed by the greedy fractional solution. Well, on the other hand, the greedy fractional solution completely fills up the knapsack. It uses all of the space, all capital W units. So if there's L units of stuff in S, which are not in the greedy fractional solution, there have to equally well be at least L units of stuff in the greedy fractional solution, which are not packed by S. So this might make it seem like the two solutions are apples and oranges. Each of them packs some stuff that the other one doesn't. But they're not apples and oranges. The greedy fractional solution really is better. Why? Well, by the greedy criterion, everything not packed by the greedy fractional solution has bang per buck worse than everything that it did packed. So these L units that are missing from the greedy fractional solution are less valuable than the L units that it includes. So since the L units of stuff in the greedy fractional solution missing from capital S are a better use of space than the L units of stuff that are in S but not the greedy fractional solution, some easy algebra shows that indeed the overall value of the greedy fractional solution is at least the overall value of S. Since S was arbitrary, that shows that the greedy fractional solution is in some sense better than optimal. It's better than all of the non-fractional feasible solutions. Now, it's not clear at the moment why we bothered to do this thought experiment, which transpired in some fantasy world where we were allowed to pack items fractionally. Now, what we really care about is our three-step greedy algorithm, and that is not in the fantasy world. That's in the real world where we cannot pack items fractionally. So what good could this thought experiment be? Well, as we'll see in the analysis in the next slide, it provides a useful yardstick, a hypothetical benchmark against which we can compare the performance of our three-step greedy algorithm. Here's the analysis. Step 1 of our algorithm sorts the items in non-increasing order of value per size. Step 2 of our greedy heuristic picks the maximal prefix of items who fit into the knapsack. Let's say that maximal prefix comprises the first k items. The k plus first item is the first one that does not fit in the knapsack given the previous selections. So here's the cool part. Remember, we added this step 3 to our greedy algorithm so that it considered 2 different candidate solutions and picked the better of them. The first candidate solution was just the outcome of step 2. So therefore, we can definitely say that the output of our 3-step greedy algorithm is at least as good as the total value of these first k items chosen in step 2. The second candidate considered in step 3 of our greedy algorithm is the maximum value item all by itself. So one such item all by itself that would be considered by our greedy algorithm was this k plus first item, the item on which we got stuck in step 2. So therefore, whatever the value of our output of our 3-step greedy algorithm is, it's definitely at least the value of item k plus 1 in isolation. So let's add these two inequalities together. On the left-hand side, what do we get? We get double the value of our 3-step greedy algorithm. On the right-hand side, we get the first k items and also the item k plus 1. That is, we get the total value of the first k plus 1 items. So now we're in a position to connect this inequality to the fractional greedy solution. So remember, what is the greedy fractional solution? Well, it packs the first k items, and then the item on which it gets stuck, namely item k plus 1, it fills up the knapsack fully with a suitable fraction of item k plus 1, and the value that the algorithm gets is prorated according to the fraction that it fits in. Well, what we have here on the right-hand side in green is even better than the greedy fractional solution. This is the first k plus 1 items, 100% of them. The greedy fractional solution has the first k items, 100%, and some fraction of item k plus 1. So the value of the fractional greedy solution is even worse than the right-hand side here. And the whole point of our thought experiment was to argue that the greedy fractional solution is even better than optimal. That has value at least as much as every feasible knapsack solution. Divide both sides by 2 and you'll see we've proved the theorem. The output of the 3-step greedy algorithm is guaranteed to be at least 50% that of an optimal solution. That's cool. We have a non-trivial worst-case performance guarantee for our simple and blazingly fast 3-step greedy heuristic for the knapsack problem. But maybe you were hoping to do a little bit better than within 50% of an optimal solution. Maybe in the back of your mind you were really rooting for something more like 90% or even better. There's a few roads we can take that might lead to better performance guarantees. The best case scenario is if we could just sharpen our analysis of this greedy heuristic. That is, don't change the algorithm, don't make any new assumptions, just have a better proof. And maybe the 50% will improve to some other number. That would be the best case. The second thing we could do is if we really loved this algorithm, for example, it being so fast, we could try to identify additional assumptions on instances that allow us to prove better performance guarantees than this 50% guarantee which holds for all instances. The third thing we could try and do is just come up with a better algorithm that in fact has better performance guarantees. So what I want to show you on this slide is that the first case, the best case scenario of just sharpening the analysis of this greedy algorithm is not feasible. The analysis cannot be sharpened. The 50% can be realized for certain instances. Then we'll tackle the other two approaches and we will in fact get better performance guarantees, either under extra assumptions about the instances or alternatively using a more sophisticated algorithm. So here's an example that shows that there really are knapsack instances on which this 3-step greedy algorithm might obtain merely 50% of the value of an optimal solution. In this example, we're going to set the knapsack capacity capital W to be 1,000. There's going to be 3 items. Item 1 will have a value of 502 and a size of 501. The second and third items are going to be identical. Both are going to have value 500. Both are going to have size 500. So what is the greedy algorithm going to do? Well, in step 1, it sorts the items according to the value per size ratio. And you'll notice that the first item has a ratio slightly bigger than 1. So it's going to be considered first before items 2 or 3. In step 2 of the greedy algorithm, it packs item 1 in the knapsack. That leaves only 499 units of residual capacity, not enough room for either item 2 or item 3. So step 2 of the greedy algorithm just outputs the first item by itself. Step 3 of the algorithm considers the max value item in isolation. That again is item 1. For this reason, the greedy algorithm will output the solution, which is just item 1 for a value of 502. And I'm sure you've noticed that there's a better solution if you eschew item 1 and instead choose items 2 and 3. They both fit in the knapsack. They fill it fully for a combined value of 1,000, which is essentially twice as big as the value of the greedy solution. So what does this example teach us? Well, it argues that if we want performance guarantees better than 50%, we have one of two options. First, if we really want to keep analyzing our 3-step greedy algorithm, we're going to have to make extra assumptions about the instances in order to prove performance guarantees better than 50%. There are some instances out there where the performance is as bad as 50% of optimal. The second approach we can take is to look at better algorithms, which might have better guarantees on worst-case instances. So in the next slide, I'll show you a refined analysis of the 3-step greedy algorithm, conditions under which it performs much better than 50%. In a separate sequence of videos, we'll develop a dynamic programming-based heuristic, which is guaranteed to have much better performance on all instances. So there's a few different assumptions you can impose on knapsack instances that will enable you to prove better performance guarantees for greedy heuristics. Let me just show you one that's both simple and also it's a condition that's met in many knapsack instances that arise in practice. So let's focus on knapsack instances where no item is especially big compared to the knapsack capacity. For concreteness, let's say that the size of every item is at most 10% of the knapsack capacity, capital W. As you'll see, there's nothing special about the number 10%. I'm just using that to keep the discussion concrete. So I claim that without changing our algorithm at all, using exactly the same 3-step greedy algorithm, actually we can even get away with the original 2-step greedy algorithm, we can prove performance guarantees much better than 50% as long as the instance satisfies this property. Why is this assumption useful? Well, let's think about step 2 of our greedy algorithm. So we've sorted the items in non-increasing order of value per size. We're packing the items one at a time. Now, at some point we get stuck. There's some item k plus 1 where if we tried to put it in the knapsack, we would overflow the capacity. Well, by assumption, this k plus 1th item, its size is at most 10% of the original knapsack capacity. So if sticking in item k plus 1 would cause it to overflow, that means there's less than 10% of the knapsack capacity currently available. That is, the knapsack is currently 90% full or more with the items that we've already packed in so far. So this is sounding pretty good. Our greedy criterion ensures that whatever fraction of the knapsack we wind up using, we're using in the most valuable possible way. And we've just noticed that this assumption on the instance implies that we use almost all of the knapsack. To make this intuition precise, we compare the output of our greedy algorithm, even just after step 2, to our favorite hypothetical benchmark, namely the greedy fractional solution. What's the difference between these two solutions? Well, they're almost the same. The only difference is that the greedy fractional solution gets to pack that last bit of the knapsack, which we know is at most 10%, with a suitable fraction of item k plus 1. So the value that we're missing in our solution is that final 10% at most of the greedy fractional solution. Now, in the greedy fractional solution, the items are packed in decreasing order of bang per buck, of value per size. So this last 10% of the greedy fractional solution is also the least important. It's making the least valuable use of capacity. So this final at most 10% of the greedy fractional solution can account for at most 10% of its overall value. So whatever we're missing in our solution for our greedy algorithm, it's at most 10% of the overall value of the greedy fractional solution. That is, we're getting at least 90% of the value of the greedy fractional solution. And we know from our thought experiment that the greedy fractional solution is even better than optimal, is at least as good as any feasible knapsack solution. Therefore, the output of our greedy algorithm, even if we don't use the 3rd step, is 90% as good as the value of an optimal solution. All of this reasoning holds equally well with a number different than 10%. So for example, if you only knew that every size was at most 20% of the knapsack, then you'd get that the greedy solution would be at least 80% of optimal. On the other hand, if you knew that every item had size at most 1% of the knapsack capacity, then just the two-step greedy algorithm would get you within 99%. Our greedy heuristic for the knapsack problem is pretty good, but let's work a little harder and do quite a bit better. We're going to accomplish a quite ambitious goal. The knapsack problem being NP-complete is not, we expect, going to admit an exact polynomial time algorithm. Let's shoot for the next best thing, arbitrarily close approximation. That is, let's accept from a user error parameter epsilon and return a solution whose value is guaranteed to be at least 1 minus epsilon times that of an optimal knapsack solution. So a client who wants to be guaranteed that this heuristic outputs a solution within 99% of optimal just has to set epsilon to be 0.01. If this sounds a little too good to be true, there is a catch. The running time is going to increase as we take epsilon to be smaller and smaller. But what this algorithm exports to the client is an accuracy running time trade-off. That is, it exports, via this parameter epsilon, a knob that the user can turn wherever they want. If you want more accuracy and are willing to wait a little bit longer, you set epsilon to be smaller. If you want something really fast and you're okay with a bit of inaccuracy, you take epsilon to be bigger. And this is as good as it gets for NP-complete problems. Assuming P is not equal to NP, there's no way to solve it exactly in polynomial time. The next best thing you could hope for is arbitrarily close approximation in polynomial time. That is what we will get for the knapsack problem using a dynamic programming-based heuristic. Sadly, the knapsack problem is the exception that proves the rule. Most NP-complete problems, it is believed you cannot get arbitrarily close approximation. One concrete example is the vertex cover problem. We discussed exact exponential time algorithms for vertex cover in a separate video. And you can talk about polynomial time heuristics for vertex cover, and there are some good ones. You can get within a factor 2 of an optimum vertex cover in polynomial time. But it is believed you cannot get arbitrarily close approximation of the optimal vertex cover in polynomial time. In fact, if you came up with such an algorithm, that would imply P equals NP. While there are some other problems out there like knapsack that admit arbitrarily close approximation, there's many more out there which are like vertex cover, where, assuming P not equal to NP, it is not possible to get arbitrarily close approximation in polynomial time. But this is an algorithms class. We should stay positive and focus on what you can do. So let's move on to the arbitrarily close approximation for knapsack. So the high-level idea is both very cool but also very natural. What we're going to do is we're going to take the knapsack instance that we're given, so items that have values and weights and some knapsack capacity, and we're going to massage it a little bit. Not too much, just a little bit, but we want to put it squarely in one of our computationally tractable special cases, and then we're going to solve this transformed version of the original input. Now, because we're not solving the problem that we were given, we're not going to get the right answer, but as long as we didn't transform it too much, we can hope that the optimal solution to the transform problem is a pretty good approximation of the original problem that we were given. Well, what's a computationally tractable special case of the knapsack problem? To date, we do know one, but we only know one so far, which is if we assume that the sizes of the items in the knapsack capacity are integers, we can go back to our dynamic programming solution of the knapsack problem, which runs in time n the number of items times capital W, the knapsack capacity. So if it were the case that the knapsack capacity W wasn't too big, if, for example, it was polynomial in the number of items n, then this dynamic programming algorithm would run in polynomial time. For technical reasons, which I'll say a little bit more about later, this computationally tractable special case is not well suited for deployment in a dynamic programming heuristic. Instead, we're going to want to develop a second, similar, but different computationally tractable special case. The second special case is when the sizes in the knapsack capacity can be arbitrary, but where the item values are integers that are not too big. This assumption can also be exploited by a dynamic programming algorithm. As we'll show in a separate video, there's a different dynamic programming algorithm for the knapsack problem whose running time is n squared times the largest item value, n squared times v max. So from this second dynamic programming algorithm, we can extract a second computationally tractable special case of the knapsack problem. Namely, if all of the item values are small integers, say a polynomial in the number of items n, then this dynamic programming algorithm already gives us a polynomial time algorithm for instances of that form. Armed with this second computationally tractable special case, we can now return to the high-level idea at the beginning of this slide and execute it. Here's how we do it. Our knapsack algorithm is given some knapsack instance. The item values need not be small integers. Now we massage the instance a little bit. We transform it so that it becomes an instance that we know how to solve in polynomial time. How do we do that? We force the item values to be small integers. How do you take arbitrary numbers and make sure that they're small numbers? Well, the first thing to try is drop the low order bits, and that's essentially what we're going to do. Our algorithm then solves this transformed instance. By construction, the instance has small item values, so we can solve it in polynomial time using our second dynamic programming algorithm. Now, we're probably not going to get an optimal solution to the original instance. After all, we solved the wrong instance. We transformed the values before invoking our dynamic programming algorithm. But the hope, and this is just a hope, this is definitely going to require a proof, the hope is that we didn't lose too much information just by throwing out some lower order bits. So, by virtue of computing a solution which is 100% optimal for the almost correct problem, maybe that solution is also almost optimal for the fully correct problem. So here is the algorithm in full detail. It really only has two steps. First, we do the transformation. We round the item values to be small integers. Then we invoke the second dynamic programming algorithm on the transformed instance. Precisely, here's how we round each item value v sub I. To begin, we decrease vi to the nearest multiple of a parameter m. I'm going to leave this parameter m unspecified at the moment, and therefore this algorithm will be undetermined. Once we start analyzing the algorithm, we'll see what the parameter m has to be as a function of epsilon. So don't forget that epsilon is the accuracy parameter supplied by our client. If the client sets a given value of epsilon, what it means is that our responsibility is to output a feasible solution with value at least 1 minus epsilon times that of an optimal solution. So the smaller the epsilon, the more accurate our algorithm needs to be. When we round an item value vi down to the nearest multiple of m, we're decreasing it by an amount somewhere between 0 and m. If vi was already a multiple of m, we don't decrease it at all. If vi was just below a multiple of m, then we wind up decreasing it by essentially m. Therefore, the bigger the m, the more information we're throwing out about our instance, and the less we should expect our accuracy. That is, the smaller the value of epsilon, the more accuracy demanded by our client, the smaller we're going to have to take our value of m. Now, once we've made everything a multiple of m, we may as well just scale down. We may as well just divide everything by m. We're going to get integers. The integers that we get after rounding down to the nearest multiple of m and then dividing by m are going to be called the v-hats. An alternative, succinct way to describe the v-hats is v hat I is, by definition, vi divided by m rounded down. And so these funny brackets in blue on the right, that's called the floor operator. That takes in a real number and returns the biggest integer that's less than or equal to the input. Thus, what is the transformation? In effect, we take the item values that we're given, we divide them by this parameter m, and then we also round down just to make sure we're dealing with integers. Step 2 of our heuristic is to just invoke the second dynamic programming algorithm to solve exactly the transformed instance. That is, we feed into that second dynamic programming algorithm the instance with n items. The sizes are exactly the same as in the knapsack instance we were given originally. The knapsack capacity, capital W, is exactly the same as we were given originally, but we feed in the values v hat 1 through v hat n. That is, we solve it with respect to the transformed values, not with respect to the original values, the vi's. Let's make two quick observations before we conclude. So first of all, remember the dynamic programming algorithm, the second one for knapsack, the running time is n squared times the largest item value. And of course here we're running the dynamic programming algorithm with these transformed item values, the v hats. So therefore, if the v hats are big, then this running time is slow. But if the v hats are small, then this running time is going to be reasonable. Now let's remember the definition of the v hats. They're essentially the original item values divided by this magical parameter m, which we haven't yet specified. But qualitatively, if m is big, the v hats are going to be small and the running time is going to be fast. On the other hand, if m is small, the v hats are going to be big and this algorithm is going to be slow. So that's how m controls the running time of this dynamic programming based heuristic. Also, remember we argued how intuitively it seemed to be controlling the accuracy. The more you jack up m, the more information you lose when you round the v's and transform them into the v hats. And so the less accuracy you're going to have. So bigger m means on the one hand faster running time, but at the cost of worse accuracy. So this parameter m really is a knob that we can tune to figure out whether we want a faster algorithm or higher accuracy. The non-trivial statement, which we need to prove in the next video, is that there's a sweet spot for m, that you can simultaneously get a pretty good running time, polynomial running time, and excellent accuracy. So one trivial observation, but that's still really nice, is that this dynamic programming based heuristic is guaranteed to produce a feasible solution. Whatever output of items we get in step 2, it's guaranteed to fit inside the knapsack. The reason for that is we pass to the dynamic programming algorithm in step 2 fully accurate sizes, the original WIs, and similarly a fully accurate knapsack capacity, capital W. Therefore, the feasible solutions for the transformed knapsack instance are exactly the same as they were in the original knapsack instance. This explains why we needed to develop a second dynamic programming algorithm for knapsack rather than trying to use the first one we developed. Thankfully, there is this second computationally tractable special case where the items have small sizes, and that turns out to be exactly what you want to make this two-step recipe work. The analysis is coming right up. In this video, we'll develop our second dynamic programming solution for the knapsack problem. Why do we need a second algorithm? Well, it's a crucial building block in our heuristic that achieves arbitrarily close approximation to the knapsack problem in polynomial time. Recall that in the knapsack problem, the input is two n plus 1 numbers. There's n items, each one has a positive value, vi, and a positive size, wi. Additionally, we're given a knapsack capacity, capital W. Back in the dynamic programming section of this course, we already devised an algorithm for this problem. That algorithm assumed that the item sizes were integral and also that the knapsack capacity is an integer. The running time of that dynamic programming algorithm was big O of n, the number of items, times capital W, the knapsack capacity. In particular, we get a polynomial time algorithm for the special case of knapsack when the knapsack capacity is not too big, when it's polynomial in n. It turns out that this is not the right special case on which to build an algorithm which has arbitrarily good approximation in polynomial time. Rather, for that kind of heuristic, what we really want is a polynomial time solution for the special case where item values are small. That is precisely the solution we're going to provide in this video. We will be assuming that the integer values are all integers, the sizes and the knapsack capacity can be whatever, and the dynamic programming solution that we develop will have running time big O of n squared times Vmax. Vmax here denotes the maximum value of any item. The running times of the two algorithms are more in parallel than the notation might suggest. Probably it looks like there's an extra factor of n in the second dynamic programming algorithm. But that's the wrong way to think about it. For the first algorithm, think of W as an upper bound on the largest total size that a feasible solution might possess. In the second algorithm, think of n times Vmax as an upper bound on the maximum total value that any feasible solution might possess. In the first algorithm, we're focused on size. In the second algorithm, we're focused on value. And in either case, the running time is the maximum quantity that we have to worry about times the number of items n. Now, since all of you are survivors of my dynamic programming bootcamp, I don't feel the need to develop this solution in great detail. Let me just jump to the relevant subproblems. So the subproblems here will be a twist on the ones that we used in our first dynamic programming algorithm for knapsack. The part that's going to be exactly the same is we're going to have an index I. I specifies which prefix of items we're permitted to use in a given subproblem. Now, in general, in the knapsack problem, you're simultaneously trying to get the value high while keeping the weight small. So the way we organize things in our first dynamic programming algorithm is the second index into a subproblem specified the residual capacity x that we were allowed to use, and then while respecting that capacity x, we asked for the largest value that we could obtain, just using the first I items. Here, we're going to turn that on its head. We're going to have a second parameter x, which is the value that we're striving for. So we want to get value x or more, and we're going to try to minimize the total size that we need to use, subject to getting value at least x. So the first index I ranges as usual from 0 to n. This corresponds to all the prefixes of items you might be interested in. The second parameter x ranges over all of the targets for total value that you might be interested in. Now remember, we're assuming in this video that every item value is an integer. So that means any subset of items will have an integral total value, so we only need to worry about integer values of x. In addition, we never need to worry about trying to achieve a total value bigger than n, the number of items, times Vmax, the largest value of any item. In fact, you could replace this upper bound n times Vmax by the sum of the Vi's if you prefer. So for a given choice of I and x, I'm going to use capital S sub ix to denote the optimal value of that corresponding subproblem. So that is the minimum weight, the minimum total size that is sufficient to achieve a total value of x or more while being restricted to using just the first I items. If there is in fact no way to get the target value of x using just the first I items, that is if the sum of the values of these items is already less than x, we just define this to be plus infinity. So let's write down the natural recurrence. Let's assume here that I is at least 1. So the structure here is going to be exactly the same as it was in our first dynamic programming algorithm for the knapsack problem. Specifically, let's focus on a subproblem, a choice of I and a choice of x. That final item I is either in this optimal solution for the subproblem or it's not. That gives us two cases, and the recurrence is just going to do brute force search over the two cases. Because we're trying to minimize the total size required to achieve a given value target, here the brute force search is going to take the form of a minimum. What are the two candidates for an optimal solution? Well, the boring one is when you don't even bother to use item I. Then, of course, you just inherit an optimal solution, a minimum size solution, using just the first I-1 items, achieving the same value target x. On the other hand, suppose that in an optimal solution to the subproblem, you do actually use item I. Well, this contributes the size of item I to the weight of this optimal solution, so that's going to be W sub I. What can we say about the rest of the items in this optimal solution? Well, because the solution here achieves a value target of x, the items in this solution other than I must be achieving by themselves a value target of x minus v sub I. And of course, by the usual cut and paste argument, amongst all subsets of the first I-1 items with that property, they better well have the minimum total weight. So one quick edge case in this second case, if vi is actually bigger than x and we have a negative index here, we just interpret this quantity as 0. That's because item I alone meets the value target of x. Let's now wrap things up with the pseudocode of the new dynamic programming algorithm. So A will be our usual table. It has 2 dimensions because subproblems are indexed by 2 parameters. I, the prefix, that ranges from 0 to n, and x, the value target, that ranges from 0 to the maximum imaginable value. Let's say n times Vmax. So the base case is when I equals 0, that is, you're not allowed to use any items. In this case, we have to fill it in with plus infinity. Well, except if x itself is 0, then the answer is 0. Now we just populate the table using the recurrence in a double for loop. The structure here is exactly the same as in our first knapsack dynamic programming algorithm. In the first dynamic programming solution that we developed for knapsack, we could return the correct answer in constant time given the filled-in table. That's because one of the subproblems in that dynamic programming algorithm literally was the original problem. When I is equal to n and x is equal to the full knapsack capacity capital W, the responsibility of that subproblem was to compute the max value solution subject to the capacity capital W using all of the items. That's literally the original problem. By contrast, in this dynamic programming algorithm, none of the subproblems are literally the original problem that we wanted to solve. In this new dynamic programming algorithm, however, none of the subproblems correspond directly to the original problem that we wanted to solve. None of them tell you the maximum value of a feasible solution. To see why, let's inspect the largest batch of subproblems, when I is equal to n, and you can use whatever subset of items that you want. The second index of one of these problems is a target value x. That might be a number like, say, 17,231. So after you've run this algorithm and you've filled in the whole table, what do you know in this subproblem? You will have computed the smallest total size of a bunch of items that has total value at least 17,231. So that's going to be some number. Maybe it's 11,298. But what if your knapsack capacity is only 10,000? Then this is not a feasible solution, so it doesn't do you any good. Okay, well, that's not quite true. It does do you some good. If you know that every single solution that gets value 17,231 or more has size bigger than your knapsack capacity, well, then you know that the optimal solution has to be less than 17,231. There is no feasible way to get a total value that high. Now, you realize that if you knew this information for every single target value x, and you do, once you've filled in the entire table, that's sufficient to figure out the optimal solution, to figure out the biggest value of a feasible solution. All you need to do is scan through this final batch of subproblems. You begin with the largest conceivable target value x, and then you get less and less ambitious as you keep finding infeasible solutions. So you scan from high target values to low target values, and you're looking for the first, that is the largest target value x, such that there exists a subset of items meeting that target value whose total size is at most your knapsack capacity. That is going to be the optimal solution. That first target value x that can be feasibly met given your knapsack capacity. Analyzing the running time is straightforward. So how many subproblems are there, or equivalently, how many iterations of our double for loop do we have? Well, it's n outer iterations and then n times vmax inner iterations, so that's n squared vmax overall. Our brute force search is over only 2 candidates, so we only do constant work per iteration of the double for loop. And the final line we do is scan through the largest batch of subproblems, so that's O of n times vmax. So the running time is dominated just by the constant work per subproblem, and so our overall running time is O of n squared times vmax as promised. Let's turn to the analysis of our dynamic programming-based heuristic for the knapsack problem. In particular, let's understand precisely how the running time of this heuristic depends on the desired accuracy epsilon. Let me jog your memory. What are the 2 steps of our dynamic programming-based heuristic? The first thing we do is we massage the item values. We round them so that they are relatively small integers. Precisely for each item I, we define v hat to be what you get by dividing the item size by m and then rounding down to the nearest integer. In step 2, we invoke our second dynamic programming solution for the knapsack problem, and we pass to it these new values, the v hats, as well as the original item sizes and the original knapsack capacity. This algorithm, as stated, is underdetermined. That's because I haven't told you how to set the parameter m. We do at least understand qualitatively the role of m and how it influences the choice in the accuracy running time trade-off. Specifically, the bigger we set m, the more information we lose when we round the original values, the vi's, to the v hat i's. More loss in information should translate to less accuracy. Larger m, less accuracy. On the other hand, the bigger we take m, the smaller the transformed item values, the v hats. Remember, the running time of our second dynamic programming algorithm is proportional to the largest item value, so smaller item values translates to faster running times. Summarizing, the bigger the m, the less the accuracy, but the faster the algorithm. Here's our plan for the analysis. We begin by studying the accuracy constraint. Remember the setup. The client is giving us a positive parameter epsilon, and it is our responsibility to output a feasible solution whose total value is at least 1 minus epsilon times that of an optimal solution. This constraint on our algorithm's accuracy should translate to an upper bound on how large a value of m we can get away with. Remember, as we jack up m, we lose accuracy. So the first question we're going to study is, how large an m can we get away with while still being guaranteed to compute a solution within 1 minus epsilon times that of an optimal one? Once we solve this problem and we understand how large a value of m we can get away with, how aggressive we're permitted to be with the scaling, we'll then evaluate the running time of the resulting algorithm for that particular choice of m. To answer this first question, how big can we take m subject to an accuracy constraint of 1 minus epsilon, it's important to understand in detail how the rounded item values, the v hats, compare to the original item values, the v's. That's what this quiz is meant to ask you to think about. Remember how we obtain v hat I from vi. First we decrease it to the next multiple of m, then we divide it by m. So we can think of m times v hat of I as what we have just after we've rounded down to the nearest multiple of m, and before we actually divided by m. So how did we get to this m times v hat I? We decreased vi down to the next nearest multiple, so we decreased it by somewhere between 0 and m. So that result is somewhere between vi minus m and vi. So let's now assemble a few preliminaries crucial for the accuracy analysis. So what did we learn from the quiz? We learned that for each item I, the rounded value v hat I scaled up by m. So intuitively, this is after we've rounded vi down to the nearest multiple, but before we've divided. That lies somewhere between vi as an upper bound and vi minus m as a lower bound. So let me extract from this two different inequalities. One which expresses an upper bound on vi in terms of v hat I, and then one which expresses a lower bound on vi in terms of v hat I. So there are two inequalities which are immediate from this fact. Let me go ahead and give them names 1 and 2. We'll put these to use in the next slide. So first of all, the value vi, well, that's lower bounded by m times the rounded value v hat I. And then v hat I, we can lower bound that by vi after we subtract m from it. So we'll call those inequalities 1 and 2. So these first two inequalities, they're important for us, but they don't have a lot of content. They're just sort of immediate from our definition of step 1 of our algorithm, from the way we do our rounding. But step 2 of our algorithm gives us a third inequality, which is much more powerful. And this says, well, look, in the second step, we solve a knapsack instance optimally. It's true we solve it for the wrong values. We solve it for the v hats. But for these rounded values of the v hats, the solution we come up with is better than any other. In particular, if we measure value using the rounded values, the v hats, then the solution S output by our heuristic is even better than the solution S star optimal for the original problem, optimal for the VIs. That is, if we sum up the v hat i's of the items in our solution S, and we compare it to the sum of the v hat i's in any other solution, in particular the solution S star optimal for the original instance, we come out ahead. Our sum of values is bigger. That's going to be our inequality number 3. These 3 inequalities are pretty much all we got going for us, but fortunately they are sufficient to solve the problem that we asked, to determine how large an m we can get away with, subject to guaranteeing an accuracy of 1 minus epsilon. To see this, let's just follow our nose. Let's just see what happens if we chain these 3 inequalities together. Now, the third one seems to have the most content. That really says we're optimally solving this problem with the transform values of the v hats. So let's start by just writing down yet again inequality number 3. So inequality 3 just says that the sum of the transform values, the sum of the v hats in our heuristic solution, capital S, is at least as good as any other solution, in particular that of the solution S star, optimal for the original problem with the original item values. So inequality 3 is a fine starting point. Fundamentally, what we're trying to do here is lower bound the performance of the solution S spit out by our heuristic, and that's what this inequality does. The one problem is it's justifying the performance of S in terms of the wrong data, in terms of the transformed values of the v-hats, whereas what we really care about are the original values of the v's. So we need to take this inequality 3 as a seed and grow from it a chain of inequalities, rewriting on both the left-hand side and the right-hand side these transformed values of the v-hats in terms of the original values of the v's. And we'll use inequalities 1 and 2 to do that. As we grow the chain to the left, we want quantities that are only getting bigger and bigger. As we grow the chain to the right, we want quantities that are only getting smaller and smaller. Hopefully, at the end of the day, when the dust settles, we'll have an approximate optimality result for our heuristic solution S. Now, if you look back at inequalities 1 and 2, you'll see that both are in terms of the quantity m times v hat. So it's going to be convenient to multiply both sides of this inequality by m. Of course, it's still valid if I do that. To extend this chain of inequalities on the left-hand side, we need to tack on a quantity which is only bigger. That is, we need to upper bound m times v hat I in terms of the original value vi. But inequality 1 simply says that indeed m times v hat I is never bigger than the original value vi. So we simply apply inequality 1 to each item in the heuristic solution capital S, and we get an upper bound of sum over the items in our solution S of the value of that item. So that's great. We get a lower bound on the performance of our solution. That's exactly what we want. To grow the chain of inequalities to the right, we need a quantity which is only smaller. That is, we want to lower bound m times v hat I in terms of some function of the original value v sub I. Now, v sub I can be bigger than m times v hat I. Remember, we rounded down, but inequality 2 says it can only be bigger by, at most, m. So if we subtract m from vi, we get a lower bound on m times v hat I. So we just apply that term by term to the optimal solution S star. So just by following our nose in this way, we get exactly what we want. We get on the left-hand side what we really care about, namely the total value of the solution output by our heuristic. And this is the total value with the original values, mind you, not with the transformed ones, with the ones we really care about. We get a lower bound on that total value. That's exactly what we wanted. In terms of the best case scenario, the total value of the optimal solution. And the only blemish is we pick up this error of at most minus m for each item I in the optimal solution S star. So let's just lower bound this crudely. The optimal solution S star, it can only have n items at most, so we pick up a minus m at worst for each of those at most n items. So if we subtract an error term of m times n, that gives us a lower bound on the value of our solution S. So now that the dust is cleared, we see that we have a performance guarantee for our solution S in terms of that of the optimal solution S star. Basically, we're off by this error term of m times n. Remember, m is this parameter that governs how aggressively we scale the item values, and it's controlling the running time accuracy trade-off. We were expecting this all along. We argued that the bigger you take m, the more information you lose, so the less accuracy you'd expect, and indeed, the extent that we're off by the optimal solution is growing linearly in this parameter m. The question we're striving to answer, remember, is how big an m can we get away with and still be sure that our solution is within a 1 minus epsilon factor of the optimal one? Well, to achieve this, we just need to make sure that the worst case error in our solution, m times n, is never bigger than an epsilon fraction of the optimal solution's value. That is, we just set m small enough that m times n is not more than epsilon times the optimal value. So this inequality is meant to tell us how to set the parameter m in our algorithm, but you'd be right to complain that on the right-hand side there's a quantity here that we don't actually know, right? We don't actually know the optimal value of the optimal solution S star. That, after all, is what we're trying to compute, at least approximately, in the first place. So instead what we're going to do is just use a crude lower bound on how small the optimal solution value could be. Let's make a trivial assumption. Let's assume that each item has a size at most the knapsack capacity. That is, each item fits by itself inside the knapsack. Any items which fail that test obviously can be deleted in a pre-processing step. Then, the optimal solution, if nothing else, it's at least as large as the value of the max value item. So to satisfy the desired accuracy constraint, all we need to do is set m small enough so that m times n is at most the right-hand side listed here. Of course, it's sufficient to set m even smaller so that m times n is no more than an even smaller number. So in our algorithm, we just set m to be the number that equalizes m times n, the left-hand side, with our lower bound on the right-hand side, namely epsilon times v max. So notice these are all indeed parameters known to the algorithm. It of course knows how many items n there are. It knows epsilon, that's the parameter supplied to the algorithm by the client, and it's easy to compute v max, the maximum value item. So the algorithm is in a position to set m so that this equality holds, that is to set m equal to epsilon v max over n. That finally completes the description of the dynamic programming based heuristic. So we've now completed the answer to the first question that we asked. How large an m can we get away with subject to the accuracy constraint of 1 minus epsilon? We can get away with m as large as epsilon times the largest item value divided by n. And now I hope that everybody is holding their breath and crossing their fingers just a little bit, because remember, m not only governs the accuracy, it also governs the running time. The more aggressively that we can scale the numbers, the larger we can take m, the faster the algorithm. And the question now is, are we permitted to take m large enough that the resulting heuristic running time is polynomial? So the running time of the heuristic is certainly dominated by step 2, where we invoke our dynamic programming algorithm. And the running time there is n squared times the maximum item value passed to that subroutine. That is the maximum value of a scaled value, the maximum v hat I. So the big question then is, how big can these scaled item values, the v hat i's, be? So pick your favorite item I. How big can its transformed value v hat I be? Well, how do we get v hat I? We take the original value vi, we round it down, and we divide it by m. So the biggest, certainly, that v hat I could be is the original value vi divided by m. That obviously is at most the maximum original value divided by m. Now we plug in our selection for m, epsilon times v max over n. Very happily, the two vmaxes cancel, leaving us just with n over epsilon. Plugging in n over epsilon as an upper bound on every transformed value passed to the step 2 dynamic programming solution, we get an overall running time of n cubed over epsilon. The running time does degrade with epsilon. The smaller the epsilon, the bigger the running time. Of course, you would expect that for any NP-complete problem. As you take epsilon smaller and smaller, you need to take m smaller and smaller to get the accuracy guarantee. That results in less aggressive scaling of the item values. In turn, bigger transform values get passed to the dynamic programming subroutine, resulting in the bigger running time. Nevertheless, this does show that the full continuum of running time accuracy trade-offs is possible for the knapsack problem. You want arbitrarily close approximation? For this problem, you've got it. In this sequence of videos, we're going to discuss an important, if somewhat poorly understood, approach to tackling NP-complete problems, namely local search. Before I discuss the general principles of local search algorithms, I want to begin with a concrete example. That's going to be to the maximum cut problem. Some of you might remember that we studied the minimum cut problem in part 1 of the course, in particular Karger's randomized contraction algorithm. That problem was defined as seeking out the cut of the graph that minimizes the number of crossing edges. The maximum cut problem, naturally enough, we want the cut that maximizes the number of crossing edges. More precisely, we're given as input an undirected graph G, and the responsibility of the algorithm is to output a cut that is a partition of the vertices into two non-empty sets A and B that maximizes the number of edges that have exactly one endpoint in each of the two groups of the partition. In the quiz on the next slide, I'll give you an example to make sure that this definition makes sense. Before that, just a couple of quick comments. So first, sadly, unlike the minimum cut problem, which we saw in part 1 is computationally tractable, the maximum cut problem in general is computationally intractable. It's NP-complete. More precisely, the decision version of the question, where you're given a graph, you want to know whether or not there exists a cut that cuts at least a certain number of edges, that's an NP-complete problem. There's no polynomial time algorithm for it unless P equals NP. Like most NP-complete problems, there are some computationally tractable special cases. For example, the case of bipartite graphs. One definition of a bipartite graph is a graph in which there exists a cut so that every single edge is crossing it. And then obviously that would be the maximum cut of the graph. A slick way to solve this problem is in linear time is to use breadth first search. You just root the breadth first search at an arbitrary vertex of the graph. You draw your breadth first search tree. You put the even layers as one of your groups A. You take the odd layers and make it the other group B. This will have no crossing edges if and only if the graph is bipartite. To make sure the definition of the maximum cut problem makes sense, what is the maximum cut in the following 6 vertex graph? So the correct answer is C, 8. That's because the graph is bipartite. There's only 8 edges, and there is indeed a cut in which every single one of those edges crosses it. Specifically, take one group to be the vertices W and X, and take the group B to be the vertices U, V, Y, and Z. There are no edges internal to A. There are no edges internal to B. Every edge has one endpoint in each. So while the max cut problem is computationally tractable in bipartite graphs like this one, using breadth first search, it's NP-complete in general. Moreover, breadth first search turns out to be not a very good heuristic for approximating the maximum cut problem in general graphs. We're going to have to turn to other techniques. There's a number of interesting heuristics for the maximum cut problem, but I want to use the problem here to showcase the technique of local search. Local search is a general heuristic design paradigm, but I don't want to describe it in general until the following video, after we've gone through this concrete example. But at a high level, you should think of it that we're always maintaining a candidate cut, and we just want to iteratively make it better and better via small, that is local, modifications. To succinctly state the algorithm, I'm going to need a little bit of notation. So imagine that we have some undirected graph and we're trying to approximate the maximum cut. And suppose we have some current candidate cut A, B. Some of the vertices are in A, the rest are in B. Now focus on some arbitrary vertex V. V could be in A or B, I don't care. There's some incident edges to this vertex V. In the graph on the right, I've shown you a vertex V. It has degree 5 incident edges. Now, some of these edges are crossing the cut. Some of the edges are not. So I'm going to use the notation C sub V of AB to denote the number of V's incident edges that are crossing the cut, and D sub V of AB to denote the number of edges which are not crossing the cut. So in the picture that I've drawn, C sub V would be equal to 2, D sub V would be equal to 3. Here then is the local search algorithm for maximum cut. In step 1, we just begin with an arbitrary cut of the graph. So we just somehow, I don't care how, put some of the vertices in A, some of the vertices in B. Now we just iteratively try to make the cut that we're working with better until we don't see any easy way to improve it further. So what's a principled way to take a given cut and make it better? Well, let's just focus on very simple modifications. Let's suppose the only thing we're allowed to do is take a vertex from one of the two groups, say from group A, and move it to group B. For example, in the green network I've shown you on the right-hand part of this slide, if we envision taking the vertex V and moving it from A to B, we get a superior cut. Why is that true? Well, here are the two ramifications of moving V from A to B. So first of all, the two edges incident to V that used to be crossing the cut, they no longer cross the cut. When we put V over on the right-hand side, the two edges whose other endpoints are in B, those edges get sucked in internal to B. They are no longer crossing the cut. On the other hand, the good news is that the three edges incident to V with the other endpoint in A, they used to be internal to the group A, but when we bring V over to the right-hand side to the group B, now those three edges cross the cut. So we lost 2 edges from the cut, but we gained 3, so that's a net improvement of 1 more edge crossing the cut. In general, this argument shows that for any vertex, so that the number of edges incident to it that are not crossing the cut, if that's bigger than the number which are crossing the cut incident to it, then switching sides with that vertex will improve the cut, and the improvement is exactly the difference between the two quantities d sub v and c sub v. If we find ourselves with a cut such that there's no vertex switch that improves the cut, that is, if d sub v of AB is at most c sub v of AB for every single vertex v, then we stop and we just return the cut that we ended up with. We typically evaluate algorithms along two axes. So first of all, how good is their solution? So for example, is the algorithm always correct or at least approximately correct? And secondly, what resources does it require? So for example, is the running time reasonable? Now, to be honest, local search algorithms often perform poorly, at least in the worst case, along both of these criteria. This local search algorithm for the maximum cut problem is interesting in that we can say non-trivial positive things both about the solution quality and about its running time. The running time bound follows easily from an observation that we made earlier, namely that every time we do an iteration of the while loop, every time we switch a vertex from one side to the other, the number of crossing edges goes up, necessarily by at least one. So I'm going to assume that the graph is simple, that there's no parallel edges, in which case there's at most n choose 2 edges in the graph. That means that this while loop can only execute in total an n choose 2 or quadratic number of times. It's easier to implement each iteration of the while loop quickly, so that means this overall algorithm will terminate in polynomial time. Now, this local search algorithm does not solve the maximum cut problem optimally. It is not guaranteed to return the maximum cut. Indeed, that would be way too much to hope for now that we know that it runs in polynomial time. Remember, the maximum cut problem is NP-complete. However, interestingly, this is a heuristic with a good worst-case performance guarantee. Precisely, the outcome of this local search algorithm is guaranteed to be a cut in which the number of crossing edges is at least half, at least 50% of the maximum possible. In fact, something stronger is true. It's even guaranteed to be at least 50% of all of the edges of the graph, which of course is an upper bound on the maximum number of edges crossing some cut. I'll prove this performance guarantee for you on the next slide, but let me first make a couple of comments. So first of all, the analysis of this algorithm stated in the theorem is tight. The 50% cannot be improved without making additional assumptions about the input. Indeed, here's an example which itself is even a bipartite graph, so it's a tractable special case of maximum cut. But even on bipartite graphs, the local search heuristic might return to you a cut which has merely 50% of the edges of a globally optimal maximum cut. The example is drawn here in green. There's just 4 vertices and 4 edges. As I said, it is a bipartite graph, so the best cut is just to put u and w in one group and v and x in the other group. That cuts all 4 of the edges. On the other hand, one possible output of the local search algorithm is the cut where u and v are in one of the groups A and w and x are the other group B. So this cut has only 2 crossing edges, only 50% of the maximum possible, yet it is locally optimal. If you take any of the 4 vertices and you switch it to the other group, you get a cut with 3 vertices on one side and then the other vertex by itself. Since every vertex in this graph has degree 2, all of those cuts are also only going to have 2 crossing edges. The second cautionary point that I need to tell you is that you maybe shouldn't be super impressed with a performance guarantee of 50% for the maximum cut problem. Indeed, even if I just took a uniform at random cut, by which I mean for each of the n vertices, I flip independently a fair coin. If the coin comes up heads, I put that vertex in A. If the coin comes up tails, I put that vertex in B. The expected number of edges that cross a random cut chosen in this way is already 50% of the edges of the graph. Just for kicks, let me sketch a quick proof of this fact. Some of you may remember from part 1, I introduced a decomposition principle for analyzing the expected value of complicated random variables. You have a complicated random variable that you care about. What do? You express it as the sum of indicator random variables that only take on the values 0 and 1. Then you apply linearity of expectation that reduces computing the complicated expectation to a sum of simple expectations. So it turns out that decomposition principle works beautifully to prove this fact. The complicated random variable that we care about is the number of edges that cross a random cut. The constituents that are indicator 0, 1 random variables are just whether or not a given edge crosses a random cut. That is, for an edge E of this input graph G, I'm going to define the random variable x sub E to be 1 if its two endpoints wind up in different groups, and 0 if its two endpoints wind up in the same group. So what's the expected value of one of these indicator random variables x sub E? Well, as with any indicator random variable, that's just the probability that x sub E is equal to 1, the probability that this edge E is cut by a random cut. What's the chance of that? Well, let's say the endpoints of edge E are u and v. There's four possibilities. U and v could both be in A, u and v could both be in B, u could be in A and v could be in B, or u could be in B and v could be in A. Each of those four outcomes is equally likely, probability 1/4. In the first two cases, this edge is not cut by the random cut. The two endpoints are on the same side. In the other two cases, it is cut. They're on different sides. So it's a 1/2 probability that this edge is cut in a random cut. Therefore, the expected value of x sub E is 1/2. And now we're good to go just by applying linearity of expectation. So precisely what do we care about? We care about the expected number of edges that cross a random cut. Well, the number of edges crossing a cut is, just by definition, the sum of the xe's over all of the edges E. Xe is just whether or not a given edge crosses the cut. So the expected value of the random variable we care about, the number of crossing edges, that's by linearity of expectation, just the sum of the expected values of these indicator random variables, the x sub E's. Each of those has value 1/2. We're summing up 1 for each of the edges. So the total of the sum is just the number of edges divided by 2 as claimed. Thanks for indulging my little digression. Again, the point of which is that just taking a random cut gives you a performance guarantee of 50% for the maximum cut problem. But in the defense of local search, which also only gets a 50% performance guarantee, it took a while, and in fact you have to work pretty hard to get a performance guarantee better than 50% with a polynomial time algorithm for the max cut problem. The most famous such algorithm is by Gomez and Williamson. That took till 1994, and it requires a tool called semi-definite programming, something that's even more powerful than linear programming. Let's now prove that local search is guaranteed to output a cut whose number of crossing edges is at least half the total number of edges in the graph. So pick your favorite locally optimal cut AB. And here by locally optimal, I just mean something that the algorithm might return. That is, a cut for which it's impossible to swap a single vertex from one side to the other and improve the value of the cut. By virtue of being locally optimal, it must be the case that, for this cut AB, and for every single vertex V, the number of edges incident to this vertex that are crossing the cut is at least as large as the number of vertices incident to this vertex that do not cross the cut. So in the previous notation, C sub V is at least as big as D sub V. If not, swapping V would give us a better cut. So we have n of these inequalities, once for each vertex V, so we can legitimately sum up those n inequalities, combining them into 1. Now let's focus first on the right-hand side of this summed up inequality. So the sum over all of the vertices in the graph of the number of edges incident to that vertex that are crossing the cut. Now here's the main point. What is this sum on the right-hand side counting? It's counting each edge that crosses the cut AB exactly twice. Consider an edge, say u comma w, which is crossing the cut AB. It gets counted twice in its right-hand side. Once when v equals u, and once when v equals w. We can apply exactly the same reasoning to the left-hand side. What is this sum counting? It's counting each non-crossing edge exactly once. Consider an edge, again, say u comma x, whose both endpoints are on the same side. That's going to be counted once in this sum when v equals u, and then again when v equals x. Now we want to compare the number of crossing edges of this locally optimal cut to the total number of edges. So on the left-hand side, we're missing the crossing edges. So to complete that into all of the edges, let's just add double the number of crossing edges to both sides of this inequality. On the left-hand side, we get double of all of the edges, and now on the right-hand side, we have 4 times the number of crossing edges. Dividing both sides of this inequality by 4, we see we've proved the theorem. The number of edges that cross A comma B is indeed a full 50% or more of the total number of edges in the graph. It's interesting to discuss briefly how the conclusions we've reached for local search for max cut extend to a natural weighted version of maximum cut. So which facts about the unweighted special case extend to the weighted case and which facts do not? Well, it still makes perfect sense to take a local search approach to the weighted version of the maximum cut problem. Now, for each vertex and in a given cut, you just look at the total weight of the incident edges that are crossing the cut and the total weights of the incident edges which are not crossing the cut. And whenever the weight of the edges not crossing the cut is strictly bigger, that's an opportunity to improve the current cut by moving the vertex to the opposite side. One cool thing is that the performance guarantee that we just established of 50% for the output of local search, that carries over to the weighted case, and the proof remains essentially the same, and I'll leave it for you to check that in the privacy of your own home. Now, it's also true that in the weighted case, a random cut still gets 50% of the total weight of the graph, so perhaps this performance guarantee is nothing really to write home about. What breaks down is the running time analysis. Remember how this went for the unweighted case. We argued that there can be at most n choose 2 edges crossing any cut, and since every iteration of local search increases the number of crossing edges, it has to halt within a quadratic number of iterations, and that means it's easy to implement the algorithm in polynomial time. One way to think about what's special about the unweighted version of the maximum cut problem is that even though, as we've seen, the graph has an exponential number of different cuts, all of those exponentially many cuts only take on a polynomial number of different objective function values. The number of crossing edges is somewhere between 0 and n choose 2. By contrast, once the edges can just have any old weights, now you can have an exponential number of cuts with an exponential number of distinct objective function values, of distinct values for their total weight. That means just because you're strictly improving the total weight crossing the cut in each iteration, it does not imply that you're going to converge in a polynomial number of iterations. And in fact, it's a highly non-trivial exercise to prove that there are instances of weighted maximum cut in which local search takes an exponential number of iterations before converging. Now that we've seen a concrete example of local search in the specific context of the maximum cut problem, let's move toward talking about this technique more generally. So let's think abstractly about some computational problem. Let's say there's a set capital X of the candidate solutions to this problem. Maybe you want to search whether or not there exists a solution with a given property. Maybe you want to find the solution which is optimal in some sense. What are some examples? Well, in our last video, X was the cuts of some given graph G. Other examples would include the tours of an instance of traveling salesman problem, or perhaps the possible assignments to variables in some constraint satisfaction problem. A fundamental ingredient to the local search approach is the definition of a neighborhood. That is, for each candidate solution little x in the space of all possible solutions capital X, you need to define which other solutions little y are the neighbors of little x. Let's look at some concrete examples. In the maximum cut problem last video, we were implicitly defining the neighbors of a given cut to be those cuts you can obtain from the given one by moving a single vertex from one side to the other. If you're taking a local search approach to a constraint satisfaction problem, something like 2-sat or 3-sat, a common approach is to define two variable assignments to be neighbors if and only if they differ in the value of a single variable. So for the Boolean case where variables are either true or false, you're going to define two assignments to be neighbors if you can get from one to the other by flipping the value of a single variable. For the traveling salesman problem, there's a lot of sensible ways to define neighborhoods. One simple and popular approach is to define two traveling salesman tours to be neighbors if and only if they differ in the minimum possible number of edges. If you think about it for a second, you'll realize that the minimum possible number of edges that two TSP tours differ in is 2. So for example, in pink I've shown you two neighboring TSP tours. The first tour has edges from U to V and from W to X, but by contrast the second tour has the crisscrossing edges from U to X and from V to W. All of the other edges in the two tours are the same. Once you've identified the space of candidate solutions to your computational problem, and once you've settled on a neighborhood for every candidate solution, you're in a position to run local search. Local search just iteratively improves the current solution, always moving to a neighboring solution, until you can't improve things any further. I'm going to specify here a highly underdetermined version of local search to highlight the number of design decisions that you've got to make if you really want to apply local search to a problem in your own projects. We'll talk about the possible instantiations of the different design decisions in the next couple of slides. So for starters, you have to initialize the search with one of the candidate solutions, some little x. How do you pick it? Well, there's a number of approaches. We'll discuss that in more detail in a sec. Now, just like in our maximum cut local search algorithm, we take the current solution, whatever it is, x. We look for a neighboring one, y, which is superior. If we find such a y, then we move to that superior solution. If there is no superior y, we're locally optimal and we just return the current solution. Our local search algorithm for the maximum cut problem that we discussed last video is in fact an instantiation of this generic procedure, where the set capital X of all solutions is just the cuts of the given graph, and two cuts are defined to be neighbors if and only if you can get from one to the other by moving a single vertex from one group to the other. In that algorithm, as we are here, we just started from some arbitrary solution, some arbitrary cut. We repeatedly searched for a superior neighboring solution. That is, we tried to see if there was a way to move a vertex from one group to the other to get a better cut. If we found such a superior neighboring solution, we iterated from that better solution. And then when we couldn't iterate any more, when there were no better neighboring cuts, we just halted and returned the final result. You can apply this generic local search procedure to other problems in exactly the same way. As an example, think about the traveling salesman problem. Let's say we define neighborhoods like we did on the last slide, with two tors being neighbors if and only if they differ in exactly two edges, and n-2 edges are in common. What do? You start from some arbitrary traveling salesman tor, and now you iterate. You keep looking for a neighboring superior solution that is from the current tor. You consider all tors you can reach by changing exactly two edges of the current tor. You check if any of those n-2 solutions have strictly smaller cost. If any of them do, you iterate from that new superior solution. When you can't iterate anymore, when all of the neighboring solutions are at least as costly as the one you're working with, that's a locally optimal tor, and you return that as your final output. In the rest of this video, I want to continue discussing local search at a high level, talking about some of the design decisions that you've got to make, as well as some of the performance characteristics you can expect. After we finish this high-level discussion, we'll move on to some videos on another concrete example of local search, specifically to 2SAT, a specific example of a constraint satisfaction problem. Let's begin with 3 frequently asked questions about underdetermined characteristics of the generic local search procedure I just showed you. Question number 1 concerns step number 1 of the algorithm. You need to somehow come up with this arbitrary starting point x. How do you do it? To answer this question, let me crudely classify the situations in which you might be using local search into 2 categories. In the first category, you're really depending on local search to come up with a good approximate solution to an optimization problem. You really have no idea how to get close to an optimal solution other than through some local search approach. The second category of scenarios is where you have some pretty good heuristics that seem to be delivering to you pretty good solutions to your optimization problem, and you just want to use local search as a post-processing step to do even better. So let's start with the first category, where all of your eggs are in one basket. You need local search to deliver to you a pretty good solution to an optimization problem. So this is a tricky spot to find yourself in. Local search is guaranteed to deliver to you a locally optimal solution, but in many problems, locally optimal solutions can be much, much worse than what you're looking for, a globally optimal solution. In the special case of the maximum cut problem, we had a performance guarantee of 50%, which already is only a so-so guarantee, but for most optimization problems, even that kind of performance guarantee is out of the question. There are locally optimal solutions far worse than the globally optimal ones. On the other hand, you know there are some good locally optimal solutions out there. In particular, the globally optimal solution is also a locally optimal one. Now, if you just run local search once, it's not clear how to evaluate the quality of the solution that's returned to you. You run the algorithm, it hands you a solution, it has cost $79,217. Is that good or bad? Who knows? An obvious approach to doing better is to run local search many times, say thousands of times, even millions of times, and then amongst all of the local optima that the different runs of your local search algorithm returns, you pick the best one and you make that your final solution. To encourage your local search algorithm to hand back to you different local optima when you run it over and over again, you want to be making some random decisions. And an extremely common point to make a random decision is in step 1 of local search, is in choosing your initial starting point, little x. So for example, in the maximum cut problem, you'd want to start with a random cut, with each vertex equally likely to be an A or B. With the traveling salesman problem, you might want to start from a random tor, that is a random permutation of the n vertices. In a constraint satisfaction problem, you could begin by giving each variable independently a random value. If this seems kind of like throwing darts at the dartboard, that's what it is. Turns out there's a lot of stubbornly difficult problems out there for which the state of the art is really not substantially better than running independent trials of local search with different random initial positions and returning the best of the local optima that you find. Now let's suppose you're in this second, happier category of scenarios where you've got a better handle on your optimization problem. Maybe you figured out how to use greedy algorithms or maybe mathematical programming. Anyways, you have techniques that generate close to optimal solutions to some optimization problem. But why not make these nearly optimal solutions even better? How do you do that? Well, feed the output of your current suite of heuristics into a local search post-processing step. After all, local search only moves to better solutions. It can only make your pretty good solution even better. Let's move on to the second sense in which the generic local search algorithm is underdetermined. The main while loop reads, if there's a superior neighboring solution y, then reset the current solution to be y. But there may, of course, be many legitimate choices for y. For example, in the maximum cut problem, given a cut, there may be many vertices whose switch to the opposite group yields a cut with strictly more crossing edges. So when you have multiple superior neighboring solutions, which one should you choose? Well, this is a tricky question, and the existing theory does not give us a clear-cut answer. Indeed, it seems like the right answer is highly domain-dependent. Answering this question is probably going to require some serious experimentation on your part with the data that you're interested in. One general point I can make is that recall when you're using local search to generate from scratch an approximate solution to an optimization problem, you want to inject randomness into the algorithm to coax it to explore the solution space and return as many different locally optimal solutions as possible over a bunch of independent runs. You're going to remember the best of those locally optimal solutions and remember the best one at the end of the day. So this is a second opportunity, in addition to the starting point, where you can inject randomness into local search. If you have many possible improving values of y, choose one at random. Alternatively, you could try to be clever about which y that you choose. For example, if there's multiple superior neighboring y's, you could go to the best one. For example, in the maximum cut problem, if there's lots of different vertices whose switch to the other group will yield a superior cut, pick the vertex which increases the number of crossing edges by the largest amount. In the traveling salesman problem, amongst all neighboring tours with smaller cost, pick the one with the minimum overall cost. So this is a perfectly sensible rule about how to choose y. It is myopic, and you could imagine doing much more sophisticated things to decide which y to go to next. And indeed, if this is a problem you really care about, you might want to work hard to figure out what are the right heuristics for choosing y that work well in your application. A third question that you have to answer in order to have a precisely defined local search algorithm is, what are the neighborhoods? For many problems, there's significant flexibility in how to define the neighborhoods, and theory again does not give clear-cut answers about how they should be designed. Once again, this seems like a highly domain-dependent issue. If you want to use local search on a problem of interest, it's probably going to be up to you to empirically explore which neighborhood choices seem to lead to the best performance of the local search algorithm. One issue it's likely you'll have to grapple with is figuring out how big to make your neighborhoods. To illustrate this point, let's return to the maximum cut problem. So there we define the neighbors of a cut to be the other cuts you can reach by taking a single vertex and moving it to the other group. This means each cut has a linear number, O of n, neighboring cuts. But it's easy to make the neighborhood bigger if we want. For example, we could define the neighbors of a cut to be those cuts you can reach by taking 2 vertices or fewer and switching them to the opposite groups. Now each cut is going to have a quadratic number of neighbors. More generally, of course, we could allow a single local move to do k swaps of vertices between the two sides, and then the neighborhood size would be O of n to the k. So what are the pros and cons of enlarging your neighborhood sizes? Well, generally speaking, the bigger you make your neighborhoods, the more time you're going to have to invest searching for an improving solution in each step. For example, in the maximum cut problem, if we implement things in the straightforward way, if we only allow one vertex to be swapped in an iteration, then we only have to search through a linear number of options to figure out if there's an improving solution or not. On the other hand, if we allow 2 vertices to be switched in a given iteration, we have to search through a quadratic number of possibilities to verify whether or not we're currently locally optimal. So So the bigger the neighborhood, generally speaking, the longer it's going to take to check whether or not you're currently locally optimal or whether there's some better solution that you're supposed to move on to. The good news about enlarging your neighborhood size is that you're going to have only fewer local optima. And in general, some of these local optima that you're pruning are going to be bad solutions that you're happy to be rid of. If you look back at the example I gave you in the previous video that demonstrated that the simple local search for maximum cut can be off by 50%, you'll see that if we just enlarge the neighborhoods to allow two vertices to be swapped in the same iteration, then all of a sudden, on that 4-vertex example, local search would be guaranteed to produce the globally maximum cut. The bad locally optimal cuts have been pruned away. Now, even if you allow two vertices to be swapped in a given iteration, there's going to be more elaborate examples showing that local search might be off by 50%, but on many instances, allowing this larger neighborhood will give you better performance from local search. Summarizing, one high-level design decision you should be clear on in your head before you apply the local search heuristic design paradigm to a computational problem is how much do you care about solution quality versus how much do you care about the computational resources required. If you care about solution quality a lot and you're willing to either wait or you're willing to throw a lot of hardware at the problem, that suggests using bigger neighborhoods. They're slower to search, but you're likely to get a better solution at the end of the day. If you really want something quick and dirty, you want it to be fast, you don't care that much about the solution quality, that suggests using simpler, smaller neighborhoods that are fast to search, knowing that some of the local optima you might get might not be very good. Let me reiterate, these are just guidelines. These are not gospel. In all computational problems, but especially with local search, the way you proceed has to be guided by the particulars of your application. So make sure you code up a bunch of different approaches, see what works, go with that. For our final two questions, let's suppose you've resolved the initial three and you have a fully specified local search algorithm. So you've made a decision about exactly what your neighborhoods are. You've figured out the sweet spot for you between efficient searchability and the solution quality you're likely to get at the end of the day. You've made a decision about exactly how you're going to generate the initial solution. And you've made a decision about how, when you have multiple neighboring superior solutions, which one you're going to go to next. Now let's talk about what kind of performance guarantees you can expect from a local search algorithm. So let's first just talk about running time. And let's begin with the most modest question. Is it at least the case that this local search algorithm is guaranteed to converge eventually? In many of the scenarios you're likely to come across, the answer is yes. Here's what I mean. Suppose you're dealing with a computational problem where the set of possible solutions is finite, and moreover, your local search is governed by an objective function. And the way you define a superior neighboring solution is that it's one with better objective function value. This is exactly what we were doing in the maximum cut problem. There, the space was finite. It was just the set of exponentially many graph cuts, and our objective function was just the number of crossing cuts. Similarly, for the traveling salesman problem, the space is finite. It's just the roughly n factorial possible tours. And again, how do you decide which tour to go to next? You look for one that decreases the objective function value, the total cost of the tour. Whenever you have those two properties, finiteness and strict improvement in objective function, local search is guaranteed to terminate. You can't cycle because every time you iterate, you get something with a strictly better objective function value, and you can't go on forever. Eventually, you'll run out of the finitely many possible things to try. There is, of course, no reason to be impressed by the finite convergence of local search. After all, brute force search equally well terminates in finite time. So this class is all about having efficient algorithms that run quickly. So the real question you want to ask is, local search guaranteed to converge in, say, polynomial time? Here the answer is generally negative. When we studied the unweighted maximum cut problem, that was the exception that proves the rule. There we only needed a quadratic number of iterations before finding a locally optimal solution. But as we mentioned in passing, even if you just pass to the weighted version of the maximum cut problem, there already local search might need, in the worst case, an exponential of iterations before halting with a locally optimal solution. In practice, however, the situation is rather different, with local search heuristics often finding locally optimal solutions quite quickly. We do not at present have a very satisfactory theory that explains or predicts the running time of local search algorithms. If you want to read more about it, you might search for the keyword smoothed analysis. Another nice feature of local search algorithms is that even if you're in the unlucky case where your algorithm is going to take a long time before it finds a locally optimal solution, you can always just stop it early. So when you start the search, you can just say, look, if after 24 hours you haven't found for me a locally optimal solution, just tell me the best solution you've found thus far. So in addition to running time, we want to measure the performance of a local search algorithm in terms of its solution quality. So is that going to be any good? So here the answer is definitely no. And again, the maximum cut problem was the exception that proves the rule. That's a very unusual problem that you can prove at least some kind of performance guarantee about the locally optimal solutions. For most of the optimization problems in which you might be tempted to apply the local search design paradigm, there will be locally optimal solutions quite far from globally optimal ones. Moreover, this is not just a theoretical pathology. Local search algorithms in practice will sometimes generate extremely lousy locally optimal solutions. So this ties back into a point we made earlier, which is if you're using local search not as a just post-processing improving step, but actually to generate from scratch a hopefully near optimal solution to an optimization problem, you don't just want to run it once, because you don't know what you're going to get. Rather, you want to run it many times, making random decisions along the way, either from a random starting point or choosing random improving solutions to move to, so that you explore as best you can the space of all solutions. You want, over many executions of local search, to get your hands on as many different locally optimal solutions as you can. Then you can remember the best one, hopefully the best one at least, will be pretty close to a globally optimal solution. In these next 3 videos, I want to highlight for you an unusual local search algorithm. It's unusual in that it's guaranteed to solve a non-trivial and interesting problem in polynomial time. That problem is the 2-sat problem, which also furnishes an example of how local search can be applied to constraint satisfaction problems. We've now mentioned 2-sat in passing a number of times, but let me just give you a very precise definition of the computational problem here. The input is a set of n variables, x1 through xn, at a set of m clauses. Each of the variables is Boolean, that is, you're allowed to set it to either true or to false. Each of the m clauses is a disjunction, that is an or, of 2 literals. A literals is simply either a variable or the negation of that variable. Here's an example to make this clearer. The example has 4 variables and 4 clauses. The variables are x1 through x4. So the first clause is x1 or x2. So it's standard to use this v symbol to denote logical or. So what this clause means is that it's satisfied if either x1 is true or if x2 is true. The only way you can screw up satisfying this clause is by setting both x1 and x2 to false. The next clause has the form not x1 or x3. The only way you can screw up satisfying this clause is by setting x1 to be true and x3 to be false. Then we're going to have a clause x3 or x4. Again, this is satisfied unless you wind up setting x3 and x4 both to be false. And then finally we have a clause not x2 or not x4. And this is satisfied except in the case that you assign both x2 and x4 to be true. Because we're interested in whether all of the clauses can be simultaneously satisfied, one often joins the clauses using logical and simples. That's what this upside down V denotes. So that's what a 2-sat instance looks like, and then we're just interested in a decision problem. Given such an instance, we just want to know, is it or is it not possible to assign values to the n variables, true or false, so that every single one of the m clauses is satisfied. The 2-sat instance that I gave you as an example is indeed satisfiable. There's actually more than one satisfying assignment, but here's a way to produce one of them. Let's start with the first clause. To satisfy it, either x1 or x2 has to be set to true. So let's go ahead and set x1 to be true. That takes care of the first clause. Now we look at the second clause and we notice, oops, if we set x1 to be true, the only way we can satisfy the second clause is by setting x3 to be true. So let's go ahead and do that. So x1 and x3 are true. x2 and x4 we haven't assigned yet. Now, by assigning x3 to be true, we knock off not just that second clause, we also satisfy the third clause. So that leaves us with the fourth clause, and now we just got to make sure we set either x2 or x4 to be false. Let's just go ahead and set them both to be false. That satisfies all of the clauses. Much is known about the computational tractability, or as the case may be, intractability of constraint satisfaction problems. 2-sat is not exceptional in that sense. We know all kinds of things about it. It is exceptional in that it is polynomial time solvable. There are many ways of proving this fact. Alumni of Part 1 may already be familiar with one really nice way, which is to reduce the two-sat problem to computing the strongly connected components of a suitable directed graph. That reduction, in fact, shows that the two-sat problem can be solved in linear time. Another way you can establish its computational tractability is using a type of backtracking algorithm. And by backtracking here, I mean something sort of similar to what we did when we gave our faster exponential time algorithm for the vertex cover problem, for instances which have small vertex covers, small optimal solutions. Both of these proofs of computational tractability are non-trivial. I'm not going to discuss them here because instead I want to spend our time on a local search algorithm. Roughly speaking, the way the backtracking algorithm works in a two-sat instance is you start by looking at some variable, let's say variable x1, and as a tentative working hypothesis, you assign x1 the value of true. Now, through the clauses, setting x1 to be true has ramifications for what other variables have to necessarily be if you're going to have a satisfying assignment. So you go ahead and propagate those implications to the rest of the variables. If you reach a contradiction, if there's one clause demanding that x7 is set to true and a different clause demanding that x7 is set to false, you know that it didn't work out. x1 is not going to be true in any satisfying assignment, so you backtrack and you try again setting it to be false and seeing if that works out. If, on the other hand, you're able to consistently propagate all of these implications from x1 being equal to true to other variables, then you can just try to extend that satisfying assignment by walking up to a different variable and setting that tentatively to be, say, true. It's possible to organize this search so that you can correctly determine whether or not a two-sat instance has a satisfying assignment in polynomial time. Again, a non-trivial exercise. If you're interested, think through the details. We're going to instead focus on a very cool randomized local search algorithm that, again, solves two-sat instances in polynomial time. I don't want to give you the wrong idea. As we discussed earlier, generally local search heuristics are not guaranteed to run in polynomial time. As we said, that's true even in the weighted version of the maximum cut problem. This two-sat example is the rare case where we can prove it's guaranteed to converge with a correct answer quickly. You can use local search not merely to identify computationally tractable versions of satisfiability, but also to improve over naive brute force search for NP-complete versions of satisfiability. In particular, let's talk about the 3-sat problem. So 3-sat, no surprise, it's the same as 2-sat except the clauses involve 3 literals rather than 2. So while a clause in a 2-sat instance can be thought of as forbidding one of the 4 possible joint assignments of a pair of variables, a clause in a 3-sat instance can be thought of as forbidding one of the 8 possible joint values for a triple of variables. Bumping up the clause length from 2 or 3 changes the problem from computationally tractable to computationally intractable. Indeed, 3-sat is in some sense the canonical NP-complete problem. You'll often see the Cook-Levin theorem stated as 3-sat is NP-complete. But just because it's NP-complete doesn't automatically mean we can't come up with any interesting algorithms. So brute force search would just try every possible assignment to the variables. That's going to take time roughly 2 to the n. Remarkably, randomized local search lets you improve dramatically over the running time of naive brute force search. Rather than a running time of roughly 2 to the n, a very clever twist on the 2-sat algorithm that we're about to discuss, which runs in polynomial time, a twist on that for 3-sat runs in time roughly 4/3 raised to the n. Way better than 2 to the n. This is a relatively recent result, only about a decade old due to Schoening. I want to focus here on how to use randomized local search to solve 2-sat in polynomial time. The improvement over brute force search for 3-sat will have to wait till another day. This algorithm is due to Papadimitriou from a little over 20 years ago, and the very elegant pseudocode is as follows. So the algorithm has 2 loops, but the outer loop's responsibility is just to run a bunch of independent random trials. For those of you who are alumni of Part 1, let me make an analogy with Karger's randomized contraction algorithm. So for that minimum cut algorithm, we had our basic randomized algorithm, and then we ran it a bunch of times, a bunch of independent trials, hoping that one of the independent trials would find us the minimum cut. Same thing's going to be going on here. The meat of the algorithm is in the inner loop. That has some probability of finding a satisfying assignment, and then we just run that basic subroutine a bunch of times, hoping that one of the trials will find us a satisfying assignment. So conceptually, you should just focus on a fixed iteration of this outer for loop. They're all exactly the same. They just use different sets of random coins. In a given iteration of this outer loop, we're just going to be doing straightforward local search. So we have to specify what's the space of solutions. Well, those are just all of the ways of assigning the n variables to true and false, all possible assignments. We have to specify the neighboring solutions. That's just going to be the one we discussed. So two assignments will be neighboring if they differ only in the flip of a value of a single variable. We have to make a decision about where we start the local search. We're going to do it in just the obvious randomized way from a uniform at random assignment of the variables. After we've settled on a random initial assignment, we just do local search. That is, we just keep flipping variables, trying to improve the quality of the current assignment. Now, one thing that's going to be a little bit different from this algorithm relative to the generic local search algorithm we discussed in the previous video is I'm going to place an a priori bound on how many local moves we're going to do before we give up. One obvious motivation for that is if we want a polynomial time algorithm, this will ensure that the algorithm will not run for too many steps. So the magic number, which will motivate when we analyze the algorithm, is 2n squared. That's how many variable flips we're going to make before we give up and return to the next independent trial in the outer for loop. Remember, n denotes the number of variables. In each iteration of the inner for loop, we first check just to see if the current assignment is in fact satisfiable, if it satisfies all the clauses. If so, we're done. We halt and report that fact. Suppose the current assignment is not satisfying. What does that mean? That means there's one clause or maybe many clauses which are not currently satisfied. So, for example, maybe there's some clause involving the variables x3 and x7, and we unfortunately set x3 to be true, x7 to be false, and that's exactly the joint value forbidden by this clause. That is, maybe the clause is not x3 or x7. So what do we do next? Well, next we do an iteration of local search. We try and improve our assignment. How do we do that? Well, we pick an unsatisfied clause. If there are many such clauses, we pick one arbitrarily. And we try to make amends with this clause by flipping the values of one of the variables in the clause. So in our example, we're either going to flip x3 from true to false. That would satisfy the clause. Or we're going to flip x7 from false to true. That would also satisfy the clause, assuming the clause is not x3 or x7. Now, either one of these variable flips would succeed in changing this clause from unsatisfied to satisfied, and you could think of various clever heuristics about which of the two variables you decide to flip, but we're going to take the simplest way forward. We're just going to pick between the two 50-50. So again, how do we modify the assignment? We choose an arbitrary unsatisfied clause, we pick one of the two variables in that clause uniformly at random, and we flip the value of that variable. Now, what makes this algorithm so frightening to think about, and my best guess for the reason why this very elegant algorithm wasn't analyzed before 1991, is that you can do some serious damage when you flip one of these variables. I mean, yeah, the constraint you started with is going to go from unsatisfied to satisfied, but for all you know, all these other clauses are going to go from satisfied to unsatisfied. If, for example, you take the variable x3 and you flip it from true to false, well, yeah, that's great for this clause that was not x3 or 7. It becomes true, it becomes satisfied. But maybe there are a zillion other clauses where x3 appears unnegated. It's x3 or something else. And perhaps by switching x3 to go from true to false, a bunch of those have now become unsatisfied. So in no way are you always increasing the number of satisfied clauses when you do an iteration of this local search. It's a very non-standard local search algorithm in that sense. To complete the description of this algorithm, I have to tell you what happens if it never finds a satisfying assignment. Of course, if it does find such an assignment, it quits while it's ahead and just returns that satisfying assignment. But if they're all after these 2n squared times log n steps, it's never found a satisfying assignment, it does something very arrogant. It just declares that, well, if I didn't find a satisfying assignment, I think that one doesn't exist. Here's two obvious positive statements we can make about this randomized local search algorithm for 2SAT. First of all, it runs in polynomial time, and that's with probability 1, no matter how the coin flips of the algorithms play out. That's because we explicitly control the number of iterations of local search. It's big O of n squared log n, so even with the sloppiest implementation you could imagine of this algorithm, it's going to run in polynomial time. Let's turn to the issue of correctness, and let's separate 2SAT instances into those that are satisfiable, where there exists a satisfying assignment, and those that are unsatisfiable. The second obvious good property of this local search algorithm is that it's always going to be correct if you feed into it an unsatisfiable instance. Why? Well, what's the algorithm going to do on such an instance? Well, it's going to rummage around amongst the possible assignments for these 2n squared log n steps, trying out different ones. Obviously, none of them will be satisfying because there are no satisfying assignments. And at the end of the day, the algorithm will correctly conclude that the instance is in fact unsatisfiable. But the key question is, what happens on satisfiable instances? If there is somewhere out there in the exponentially big space of assignments one that satisfies all of the assignments, is this algorithm going to find one in its mere 2n squared times log n steps? Now, I have to tweak that question a little bit. This is, after all, a randomized algorithm, and there's some tiny probability that the coin flips could conspire to stymie the algorithm from finding a satisfying assignment. So what I really mean is, could it be the case that, with probability very close to 1, on every satisfiable 2-sat instance, this simple randomized local search algorithm is actually going to come up with a satisfying assignment? Understanding why Papadimitriou's randomized local search algorithm for 2-sat works requires understanding some basic properties of random walks on the non-negative integers. It's a very fun, classic topic. In this video, I'll provide the relevant background. In this video, we're going to focus on a simple randomized process. We're not going to discuss in this video how this connects to Papadimitriou's algorithm, but in the next video, we will, trust me. The setup is as follows. Perhaps you just took a super difficult exam. Maybe it was an algorithms class, for example. You stagger out of the exam room and you're just in a complete daze. You have no idea where you are or where you're going, and so you just stumble along. At each time step, you take a step to the left with 50% probability or a step to the right with 50% probability. You have no idea where you're going. We measure your position in terms of the number of steps you've taken from a dead end at the end of the street, which we call position 0. So by randomly walking left or right at each time step, your position either goes up by 1 or it goes down by 1. Each has a 50-50 chance of happening. The one exception is if you found your way to position 0. Again, that's a dead end. There's no way to go left. So with 100% probability, you stagger back to the right. You go to position 1 at the next time step. We assume that your exam room is located at this position 0 at the dead end. In other words, at time 0, you're at position 0. There's a lot of interesting questions you can ask about random walks on the non-negative integers. Here's the one we're going to be interested in. Imagine your dorm room is n steps away from the exam room. That is, your dorm room is at position n. Now, if you had your wits about you, you could go from your exam room to your dorm room in n steps. You'd just zip right down the line. But you don't have your wits about you. You're in this post-exam daze, staggering around. So, doing your random walk, on average, how many steps does it take you before you make it home to position n? To illustrate a sample trajectory, imagine that your dorm room is only 3 steps away, at spot 3. So in time 1, we know that for sure you move from position 0 to position 1. And now maybe you get lucky and you stumble a step to the right in the next time step. So you're at position 2. You're only 1 step away from home. But now, unfortunately, you stagger backward, back to position 1. Maybe now you lurch forward back to position 2 again. And this time your momentum carries you forward on home to position 3. That was a trajectory in which it took you 5 steps to get home to your dorm room at position 3. You can imagine a trajectory which is faster if you just zipped straight there. You can certainly also imagine trajectories which are slower if you stumbled back left a couple times more before making it all the way to the right to position 3. So let's state this statistic precisely and check in with your intuition about how it grows as a function of n. So for a non-negative integer n, I'm going to use capital T sub n to denote the number of steps this random walk takes before it reaches, for the first time, position n. So T sub n is a random variable in the sense that its value depends on exactly which steps you took, on the results of your random coin flips. On the other hand, once you unveil the answers to all of the random coin flips, whether you go left or right at each time step, you can compute Tn, just like we did in the sample trajectory on the last slide. So the non-trivial question I want you to think about on this quiz is, how does the expected value of t sub n grow as a function of the position n that you're waiting to reach? I'm not expecting you to devise a proof of the answer. Indeed, that's what we're going to be doing for most of the rest of this video. Just asking you to take your best guess. All right, so the correct answer is B, theta of n squared. Depending on how much facility you have with discrete probability, you may or may not have been able to do a back-of-the-envelope calculation that would suggest this should be the answer. So for example, if you take some Bernoulli random variables and do some calculations with their standard deviation, you might expect the answer to be theta of n squared. In fact, what's even cooler and what we're going to prove is it's not just theta of n squared. The expected value of the random variable t sub n is exactly n squared for every non-negative integer n. For the most part, in these courses, I have endeavored to give you proofs which on the one hand aren't too long. I know you're a busy person and I don't want to waste your time, but also on the other hand, teach you something. So I hope you'll forgive me if it's not clear what this proof teaches you. This is just going to be the slicked up proof from the book that the expected value of t sub n, the number of steps needed to reach position n on a random walk, is exactly n squared. The really nice idea behind this slick proof is to solve a more general problem. So we're going to calculate the expected number of steps, not just to get from position 0 to position n on a random walk, but more generally from every intermediate position I to the position n on a random walk. The reason this is a good idea, this gives us n plus 1 different statistics we're trying to calculate, and it's easy to relate the values of these different things we're trying to calculate. From these relationships, we'll be able to solve for all of them simultaneously. So let's have some notation to make this precise. For a non-negative integer I, by z sub I, I mean the number of random walk steps that you take if I start you at I until you reach position n for the first time. Notice by the definitions, z sub 0 is exactly the same thing as t sub n, the number of steps you need to reach n starting from 0. So are there any zi's whose expectations are easy to compute? Well, sure. If we took I equal to n, what is z sub n? That's the number of steps on average you need to get from n to n for the first time. Well, that's going to be 0. For the other values of I, we're not going to solve for the expected value of z sub I explicitly just yet. Rather, we're going to relate the expectations of different zi's to each other. To see how this works, let's start with I equals 0. That is z naught, the random variable that we really care about. Now, we don't know what the expected value of z naught is. That's what we're trying to compute. But we do know that every walk starting at 0 and ending at n begins with a step from 0 to 1, and then is followed by a walk from 1 to n. Therefore, the expected length of one of these walks is just 1, that's for that first hop to get from 0 to 1, plus the expected value of a random walk from position 1 to n. That's a quantity also known as the expected value of z sub 1. So that's kind of exciting, how we were able to avoid explicitly computing the expected value of z sub naught, instead relating it to the expectation of a different random variable, z sub 1. But if you think about it, we can play exactly the same game with the intermediate values of I as well. We can relate the expected value of z sub I to the expected values of z sub I minus 1 and z sub I plus 1. To make this fully precise, I'm going to bust out the definition of a conditional expectation. So I'm going to assume that you know what that is. If you want to review it, you can go back to part 1. We needed conditional probabilities to analyze Karger's randomized contraction algorithm, or you can just look it up on Wikipedia or whatever. If you're not feeling in the mood to recall what conditional expectation is, I actually think the computations I'm about to do are sufficiently intuitive. You'll find them eminently plausible, even without the formal justifications. So what's the expected value of z sub I, the average number of steps you need to hit n for the first time if I start you out at position I? Well, let's just condition on what happens in the first step, right? There's only two possibilities. 50% probability you go left to I minus 1. The rest of what happens is a random walk from I minus 1, and you just count the steps till you get to n for the first time. The other 50% of the time, well, you go right, and the rest of the process is just a random walk starting from I plus 1, and you count the steps until you get to n for the first time. If If you want to be totally formal about it, you would just expand the expected value of z sub I, conditioning on the first step. So you'd have the probability that you go left times the conditional expectation of z sub I, given that you go left in the first step, and a similar term for when you go right. As we discussed, we know the probability that you go left is exactly 1/2. The probability that you go right is exactly 1/2. The conditional expected value of your random walk, given that you went left first, well, that's just 1. That's the step you took to get to I minus 1, plus the expected length of a random walk, 2n from I minus 1. Similarly, if you're lucky enough to go right, then the expected random walk is just 1. That's for the step to go right, plus the expected value of the rest of the random walk, also known as the expected value of z sub I plus 1. Once the dust clears, we discover that the expected value of z sub I, the average number of steps from position I, is just 1 plus the average of the expectations of z sub I minus 1 and z sub I plus 1. If we multiply both sides of this equality by 2 and rearrange, we get that the difference between the expected values of z sub I and z sub I plus 1 is equal to 2 more than the difference between the expected values of z sub I minus 1 and z sub I. So what's a good interpretation of this equation? Well, first let's just notice that the expected value of z sub I, that number is definitely decreasing as you take I bigger and bigger. As you start closer and closer to your destination n, certainly the number of steps that you need is going down. So for that reason, both sides of this equation are going to be positive, right? The expected value of z sub I is going to be bigger than the expected value of z sub I plus 1. You don't need as many steps if you start further to the right at I plus 1. But this equation is saying more. It's saying consider a consecutive pair of conceivable starting points. Clearly you have an advantage by starting one position closer. But this equation is saying that as you slide this pair of consecutive starting points closer to the destination, the advantage gets amplified. So however much savings you got by starting one position closer at I instead of I minus 1, you get that same advantage plus 2 more if you get to start at I plus 1 relative to starting at I. So why was it useful to relate all of these various expectations to each other? Well, now that we have this big systems of constraints, we can solve simultaneously for what all of these expectations have to be, in particular for the one expectation we really care about, E of z naught. So to see how we do this, let's just write down what the differences between successive expectations have to be. So the first thing we know, and this was one of our edge cases, is that whatever the expected value of z naught is, it has to be one more than the expected value of z1. That is, the difference between these two expectations equals 1. We concluded the previous slide by noting that if you slide a pair of consecutive positions one position further toward the destination n, then the advantage you get by starting one position closer goes up by 2. So if your advantage is 1 by starting at z1 instead of z naught, then your advantage is going to be 3 by starting at z2 instead of z1. That is, the expected value of z1 minus the expected number of steps from 2 is going to be equal to 3. So we can just apply that equation over and over again. We bump up the indices by 1, and the difference between the expectations gets bumped up by 2. So at the end of the day, relative to our very first equation, we've bumped up both indices by n minus 1. So we've bumped up the right-hand side by 2n minus 2. So we have that the expected value of zn minus 1 minus the expected value of zn is equal to 2n minus 1. Massive cancellation is often the sign you're on the right track. Certainly that's what we're going to see here. So all of the expected values for z1 through zn minus 1 appear once positively, once negatively, so they're all going to drop out. And actually it gets even better than that. The expected value of z sub n, that's just 0. Remember, that would be how long a random walk takes to get from n to n, also known as 0. So if we add up all of these equations, we magically get exactly what we cared about on the left-hand side, the expected value of z naught, of a walk starting at 0, ending at n. That's also known as t sub n, the expectation we're trying to analyze. So what does the right-hand side sum to? Well, an easy way to think about it is just to group the first row with the last row, the second row with the second to last row, and so on. For example, if n is equal to 100, we're going to group 1 with 199, 3 with 197, 5 with 195, and so on. So each of these groupings is going to give us 2n, and if n is even, there's going to be n over 2 of these pairs, giving us a total of n squared. If n is odd, the story is the same. You just get n minus 1 over 2 groups of size 2n, plus the median group is going to have a value of n. Again, you get n squared. So that completes this very pretty, if somewhat inscrutable, proof that the expected number of steps you need before you reach n for the first time is exactly n squared. In the analysis of Papademetriou's algorithm, we're not actually going to use this claim about the expectation. Rather, we're going to use an easy corollary, which gives an upper bound on the probability that this exceeds its expectation by more than a factor of 2. Specifically, we're going to use the fact that the probability that a random walk needs strictly more than 2 times n squared steps to reach position n for the first time is no more than 50%. This is a special case of a simple but useful inequality known as Markov's inequality. In proof, let's denote by p the probability of interest, the probability that the random variable t sub n is strictly bigger than 2n squared. Essentially, the reason the corollary is true is that if the probability that t sub n was bigger than 2n squared was strictly bigger than 1/2, well, then the expectation would have to be bigger than n squared, but it's not. It's equal to n squared. We just computed it. So a little more formally, let's start from the expected value of t sub n. Now we know this is n squared, we just computed it, but let's also write out the definition of this expected value. So that's just a sum over the values that Tn might take on. Let's go ahead and just use all non-negative integers k from 0 to infinity, and then it's k times the probability that t sub n takes on the value k. I'm going to break this sum into 2 parts, the parts where k takes on a value that's at most 2n squared, and then the parts of the sum where k takes on a value bigger than 2n squared. So now let me just do some very crude lower bounds of this right-hand side. This first sum, well, whatever it is, it's going to be non-negative because k's are non-negative and probabilities are non-negative. In the second sum, again, I'm feeling very generous. Let's just lower bound k in the sum by 2n squared. It's always going to be bigger than that. After the dust clears, the first sum has disappeared. That's what we're just lower bounding by 0. In the second sum, we're lower bounding k by 2n squared. At that point, we can take the 2n squared outside the sum, and at that point, the sum is merely the total probability mass on which Tn takes on a value strictly bigger than 2n squared plus 1. By definition, we were calling this probability of p. This is the probability of interest, and rearranging, we do see that, in fact, p has to be at most 1/2. So that completes the claim of the corollary. It's really just a simple consequence of the hard work, which was proving that the expected value of this random walk was n squared. We'll plug this corollary into the analysis of Papademetriou's algorithm next. Now we'll see how our understanding of basic properties of random walks on the non-negative integers unlocks the analysis of Papademetriou's algorithm, showing that randomized local search yields a polynomial time algorithm for the 2-sat problem. Let me remind you the details of Papademetriou's 2-sat algorithm. Consider an instance of 2-sat. Suppose it has n Boolean variables. The algorithm has 2 for loops. The outer for loop, its only responsibility is to run log n independent random trials. In each iteration of this outer for loop, we're just going to do randomized local search. So we begin with an initial random assignment. We flip a fair coin independently for each of the n variables to determine whether it starts out true or starts out false. Then we get a budget of 2n squared local moves in an attempt to transform this initial assignment into one that's satisfying. In each of these 2n squared inner iterations, we first check if the current assignment is satisfying. Obviously, if it is, we're done. So suppose that the current assignment is not a satisfying assignment, then there's at least one, possibly many, unsatisfied clauses. Of them, we pick one, arbitrarily. It's a 2-sat instance, so this clause involves 2 variables, and if we flip the value of either of those 2 variables, we're going to make amends with this clause. It will flip from unsatisfied to satisfied. There's a tricky question of how do you pick which of the 2 variables you flip, but we take the easy way out. We just pick one of the 2 uniformly at random. If at the end of the day, after these 2n squared times log n local moves, Papademetriou's algorithm has failed to find a satisfying assignment, it somewhat arrogantly declares that therefore one must not exist. What's clear about this algorithm is that it runs in polynomial time. After all, we've explicitly bounded the number of steps it's permitted to take. Secondly, it's clear that if there is no satisfying assignment, then the algorithm will naturally fail to find one and correctly report that it's unsatisfiable. What's not at all obvious is the probability that Papademetriou's algorithm will find a satisfying assignment in instances where at least one such assignment exists. That analysis is the subject of this video. And again, what's remarkable and surprising about this theorem is that if you think about the most natural measure of progress for Papadomitru's algorithm, namely the number of clauses which are currently satisfied, that number can actually go down when you make a local step. By flipping the assignment to one variable, yeah, you fix the one clause, but you might screw up a bunch of others, leaving you with an assignment that seems worse in the sense that even fewer clauses are satisfied than before. Nonetheless, if you define the right measure of progress, you can argue by a random walk analogy that you are making progress over time, resulting eventually with a satisfying assignment. Let's see the details. Each iteration of the outer for loop represents a fresh opportunity to discover a satisfying assignment. All of these iterations of the outer for loop are identical. They just use fresh random coins. So let's just analyze for now the success probability of a particular outer iteration. We're assuming that this instance is satisfiable, so there's at least one, perhaps many, satisfying assignments. Pick one, an arbitrary one, I don't care which, call it A star. Let's denote by A sub t the assignment that Papadomitru's algorithm is considering after t iterations of the inner for loop have completed. So A sub 0, that's the random initial assignment with which we begin this iteration of the outer for loop. And then after we've done t local flips, that results in the assignment A sub t. This is, of course, a random variable. It's a function of the random choices made by Papadomitru's algorithm. Now, the great idea in this analysis is to use the right progress measure. Rather than counting the number of clauses that the current assignment satisfies, we're going to count the number of variable assignments that it got right. That is, the number of variable assignments with which it agrees with this reference satisfying assignment A star. Evidently, x sub t is an integer. It's 0 if A assigns every variable the opposite of what A star does, and it's equal to n if A and A star are exactly the same assignment. Of course, if we ever get to the point where x sub t equals n and A star is the same as AT, then AT is itself a satisfying assignment and we're good to go. The algorithm halts correctly. Now we come to the key point in the analysis. Now we're going to understand the sense in which the algorithm on average makes progress. So suppose we're currently looking at the assignment A sub t, and suppose it's not a satisfying assignment. Then there's one or more clauses that are unsatisfied. The algorithm picks one of those. Let's say it's a clause involving the variables x sub I and x sub j. So for example, if it looks at the clause not x sub 3 or x sub 7, then it's involving the variables x sub 3 and x sub 7. So here's an easy observation. Our current assignment A sub t is failing to satisfy this clause. The reference satisfying assignment A star, naturally, is satisfying this clause. Therefore, A star must give a different value to one of the two variables xi or xj than our assignment A sub t does. It is also possible, of course, that A star makes different assignments to both of the variables xi and xj. All we know is that A star satisfies the clause, whereas our assignment A sub t does not. And the amazing part is just this simple observation is enough to imply that we're going to make progress on average. Here's exactly what I mean. So Papadomitru's algorithm is going to choose either xi or xj, that choice is uniform at random, and it's going to flip the value currently assigned to that variable. Now the situation in which this is guaranteed to be good for us is where we gave the opposite assignment to both xi and xj relative to the assignment A star. If both of our value assignments to these variables was the opposite of A star, then whichever one we flip, we are going to share one more variable in agreement with A star than we did before. That is, in our previous notation, x sub t plus 1, the number of variables on which we agree next time step, will be guaranteed to be one more than it is right now. The situation is more subtle when the current assignment A sub t agrees with the reference satisfying assignment A star on exactly one of the two variables xi and xj. So for example, maybe the current assignment agrees with A star on xi, but it disagrees with the reference assignment A star on xj. Now, of course, the algorithm has no idea what A star is, this arbitrary satisfying assignment, so it has no idea which of the two variables xi or xj it should flip. It just picked one of the two at random. Now, if we get lucky and we flip the value of the variable on which A sub t and A star disagree, then this is just like case 1. The flip causes the two assignments to agree on one more variable than they did previously. As a consequence, x sub t plus 1 is going to be 1 more than x sub t. In the unlucky case, we wind up flipping the variable on which we agreed already with the reference assignment a star. Then once we flip it, we're going to disagree on yet another variable with the reference assignment a star. So in that case, x sub t plus 1 is actually going to be 1 less than x sub t. And now at this point, I hope things are starting to look a little familiar relative to our previous video about random walks on the non-negative integers. There, we again had a random variable, namely the position of the walk, and at each time step it either went up by 1 or down by 1 with 50-50 probability each. So the situation here with the x sub t's is clearly not identical to random walks on non-negative integers. So the next quiz asks you to identify the differences between the random process governing the x sub t's and your vanilla random walk on the non-negative integers as studied in the previous video. So the answer is D. If we think about two random processes, the first one is your straightforward random walk on the non-negative integers as discussed in the last video. The second random process is the evolution of these random variables, the x sub t's, the number of variables on which the current assignment in Papadomitri's algorithm agrees with a reference satisfying assignment a star. There are exactly 3 differences. One we already pointed out. In the vanilla random walk on the line, unless you're at position 0, if you're at any bigger position, it's always 50-50 left or right. In Papadomitri's algorithm, you might sometimes have a 0% probability of moving to the left, 100% chance of moving to the right. That's when the algorithm zooms in on an unsatisfied clause in which the current assignment a sub t happens to differ with the reference assignment a star on both of the two variables. Then it doesn't matter which of the variables you pick, you're guaranteed to agree with the reference assignment a star on one more variable than before. The second difference is that when we studied random walks, by definition, we always started at position 0. That would correspond to this first random variable x naught being equal to 0. However, in general, x naught will not be equal to 0. In general, it'll be strictly bigger than 0. Why is that? Well, remember, x naught is defined as the number of variables that have the same value in the reference assignment a star and the initial random assignment a naught. So the only way that x naught is going to be 0 is if you randomly chose an assignment where every variable had the opposite value as what it is in a star. And that's very unlikely to happen. Generally, you start with a random assignment, you're going to get lucky and some of the values will be correct, will be the same as in a star. So x naught will generally start out bigger than 0. Here's the third and final difference. In the random walks that we studied, the process, by definition, stopped exactly the first time you reach position n. Now, in Papadomitri's algorithm, what is true is that if you ever get to the point that x sub t equals n, then at that point the algorithm will terminate. Why? Well, if x sub t equals n, that means that in the assignment a sub t, every single variable has exactly the same value as in the reference assignment a star. Now, a star is a satisfying assignment, and Papadomitri's algorithm halts as soon as it finds a satisfying assignment. So if x sub t equals n, you found a star, and you're good to go. You stop. However, the converse is not true. Papadomitri's algorithm might halt even though the current value of x sub t is less than n. Why is that? Well, remember, x sub t measures your distance from this one satisfying assignment a star. But nobody said that was the only one. There might be other satisfying assignments out there in the world as well. And Papadomitri's algorithm might well stumble upon one of them before it finds a star. So it halts the first time it finds a satisfying assignment, and that can happen before x sub t equals n. So where does this leave us? On the one hand, there does seem to be a strong metaphor between the distance between the assignment in Papadomitri's algorithm and this reference assignment a star and the position of a random walk on the non-negative integers. On the other hand, there's kind of a lot of differences. Some of them are pretty subtle. So what you got to be wondering is, was that whole analysis last video useful? Well, what's amazing and what allows us to transfer the random walk analysis over to that of Papadomitri's algorithm is that every single one of these 3 discrepancies between the 2 random processes only helps us. It only means the algorithm is going to terminate even faster than we might have suspected from the random walk analysis. So here's another way to think about it. Imagine I force you to run Papadimitri's algorithm under an extremely unfortunate set of circumstances. So first I give you a two-stat instance with just one satisfying assignment. So there's a unique satisfying assignment A star. You're looking for a needle in a haystack. There's no way you can get lucky by halting early with a different satisfying assignment. Secondly, I force you to begin from the worst possible initial assignment, where every variable's value initially is the wrong one, is flipped from what it should be in A star. And finally, imagine I further contrive things so that whenever you pick an unsatisfied clause to do a variable flip, I force you to pick a clause where one of the variables is set the same as an A star and the other variable is set the opposite of A star. Well, for this kind of execution of Papadimitri's algorithm, the correspondence between the evolution of the random variables, the x sub t's, and a random walk on the non-negative integers is perfect. The two random processes are identical under this worst case set of circumstances. Therefore, in the worst case circumstances, the probability that Papadimitri's algorithm fails to find a satisfying assignment, that is A star, within 2n squared steps is exactly the same as the probability that a random walk beginning at 0 fails to reach position n within 2n squared steps. And we analyzed that failure probability in the previous video. We proved it's at most 1/2. That is, the success probability is at least 1/2. Now, if you look at any other circumstances other than the worst case circumstances, Papadimitri's algorithm is only more likely to succeed. So first of all, it doesn't start as far away from a satisfying assignment. Second of all, there's other satisfying assignments it might be able to find. And thirdly, sometimes it's guaranteed to make progress as opposed to having only a 50-50 chance. So the success probability under any circumstances of Papadimitri's algorithm is at least 50% in a given iteration of this outer for loop. And now we're home free. The probability that a given iteration of the outer for loop fails is at most 1/2. The probability that each of the log base 2n iterations of the outer for loop fail is then at most 1/2 raised to the log base 2 of n, also known as 1 over n. So the overall success probability of the algorithm is at least 1 minus 1 over n as claimed. In the design and analysis of algorithms, both this course and its predecessor, we've covered a lot of famous algorithms. We've covered a lot of fundamental data structures. We've covered lots of killer applications. And despite the fact that I've tried to use our time together in the optimal way, giving you the most bang for the buck, there are fundamental topics we have not had a chance to cover. In these final few videos, I want to talk a little bit about things we didn't talk about. I have a few goals. The first goal is to give you a little bit of literacy in a few more techniques, so at least you've heard of things like bipartite matching and the maximum flow problem, and you're aware that there are good algorithms for those sorts of problems. Secondly, I want to get you excited to do a little bit more study, either through further courses or on your own. And indeed, generally the topics that I'll mention in these final few videos are covered in your more comprehensive textbooks on algorithms. Finally, I hope to convey something I've mentioned in passing in the past, which is that algorithms is not an ossified field. Rather, it's a vibrant area of research. There are still lots of things about fundamental problems and models that we don't yet understand. Let's get the ball rolling with a very fun classical problem known as stable matching. We're going to think of stable matching as a graph problem, and there's going to be two sets of nodes, two sets of vertices, capital U and capital V. For historical reasons, we will call these sets the men and the women, respectively. A non-essential assumption that we'll make for simplicity is that these two sets of nodes have equal cardinality. Call that common size n. So for example, maybe n equals 3, and we can call the first set of nodes A, B, and C, and the second set of nodes D, E, and F. Now what's really important about the stable matching problem is that every node has preferences. There are things that it wants more than others. Specifically, each node in U has a ranked list of the nodes in V. Each node in V has a ranked list of the nodes in U. So in this example, maybe A, B, and C are all on the same page. They all agree that D is really the best node. It's better than E, but E is definitely better than F. That is, maybe every single node on the left-hand side has the ranked list D followed by E followed by F. By contrast, maybe there's heterogeneous preferences amongst vertices in capital V. Maybe D thinks A is better than B is better than C, while E prefers B to C to A, and finally F prefers C to A to B. So what might these nodes and these ranked lists represent? Well, imagine, for example, that one set is colleges and the other set is applicants, recent high school graduates. Each college has a ranking of the applicants based on things like test scores, grades, and the fit that student is for the college, and each student similarly has a ranking over the colleges of which ones it prefers to go to over others. As another example, you might think about medical residents, that is, people who just finished medical school looking for a residency, and the other side being hospitals. Again, hospitals are going to have a preference over which recent graduates they accept as residents. Potential residents, of course, have preferences over which hospital they get assigned to. So given this data, two sets of nodes, and these ranked lists, we're interested in computing a stable matching. So what's a stable matching? Well, first of all, it better be a perfect matching. And a perfect matching means that each node on the left, each node of U, is matched to exactly one node of V and vice versa. In addition to being a perfect matching, it should also be stable in the sense that there should be no blocking pair. What that means is that if you look at any pair of nodes, little u from capital U, little v from capital V, if little u and little v are not matched, there better be a good reason for them not being matched. Specifically, little u better strictly prefer who it is matched to, call that v prime, to this alternative v, or if that's not the case, it better be that little v strictly prefers the node it's matched to, call it u prime, compared to the alternative little u. So what's the motivation for this definition? Well, think about any perfect matching that fails this stability property. You're really asking for trouble for that kind of matching. Specifically, U, with its wandering eye, will spy V, and it prefers V over the node V prime to which it was assigned. Similarly, V is going to return that gaze. V prefers U by assumption that the stability property fails over the node U prime to which it was matched. So U and V are going to have an incentive to essentially elope and disrupt this whole assignment. Imagine, for example, that U is a student and V is a college, and you have a matching that fails the stability property. Then this pair, this student and this college, has an incentive to do a sort of backroom deal after the fact. You might want to withdraw its commitment from its assigned college V prime to try to get into V instead, and V, the college, actually wants to sort of withdraw its offer from its student U prime to give it to U instead. So that's an unstable matching, but as long as there's no blocking pair of this form, and for every pair which is not matched together, there's a good reason for it, then we deem it a stable matching. Let me tell you about an extremely elegant and justly famous algorithm for computing a stable matching, the Gale-Shapley proposal algorithm. Floyd-Shapley was one of the recipients of the 2012 Nobel Prize in Economics, in large part for this algorithm. Had David Gale still been alive, he surely would have been a co-recipient of that Nobel Prize as well. Let me explain the algorithm in an example, then I'll give you the general pseudocode. We start with the empty matching, with nobody matched with anybody else. And as long as there's some man, some node on the left-hand side, which isn't matched to some woman, we pick an arbitrary unattached man, and we let it propose to a woman of its choice. So we might start, for example, with the man C. C says, well, my favorite woman is D, so let me start by proposing to the woman D. Now, D isn't necessarily very impressed with C. Notice C is last in D's preference list. But with a lack of other proposals at the moment, the node D tentatively accepts this proposal from C. Now we proceed to the next iteration of the while loop. We look for a man that is unattached. So maybe we pick B. B now gets its shot at proposing to its favorite woman. In this case, it is also D. So now the node D has a bit of leverage. It has two competing offers from the nodes B and C, and of course it retains the offer from the preferred suitor. In this case, D prefers B to C, so the edge between C and D gets deleted and replaced with the edge between B and D. So now both of the men A and C are unattached. Perhaps in the next iteration we let the node A gets its shot. It again proposes to the node D, and again D prefers A to B, so the edge between A and D is going to replace the edge between B and D. So we now again have two unattached men, B and C. Let's say we pick C next. So C gets to propose to whatever woman it wants, and D is its favorite, but it's already been rejected by D. And in the algorithm, a man will never repropose to a woman who has previously rejected him. So next on C's list is the woman E, and so E has not had any other offers, so E tentatively accepts the proposal from C. But now, once B gets a chance, B will also propose next to E. That's B's next favorite, and it's already been rejected by D. And E prefers B to C, so we will replace the edge between C and E with the edge between B and E. And so now finally, the man C is the only one that remains unattached, and it has no choice but to propose to its final option, the node F. F actually happily accepts that because C is on the top of F's list, and that leaves us with the matching that matches A with D, B with E, and C with F. This is clearly a perfect matching. I'll let you check that it's also a stable matching. Having traced through this example, I hope the pseudocode for the general algorithm will not surprise you. So we have a main while loop, and in each iteration we pick some man who is not yet engaged to any woman. Call that man U. U then proposes to his favorite woman, the top-ranked woman, with the constraint that he will not propose a second time to any woman who's already rejected him. Each woman then behaves in the obvious way, which is to keep track of all of the suitors, all of the men that have proposed to her, and to retain as a tentative engagement only the proposal from their favorite, that is, highest ranked suitor. Notice this algorithm maintains the invariant that the current set of engagements is a matching. Not necessarily a perfect matching, but a matching. That is, at any given time, a man is engaged tentatively to at most one woman, and every woman is tentatively engaged to at most one man. The Gale-Shapley theorem states that not only does this algorithm terminate quickly, not only does it terminate quickly with a perfect matching, but in fact it terminates quickly, namely in a quadratic number of iterations at most, with a stable matching. In particular, this theorem, this algorithm, provides a constructive proof that a stable matching always exists, no matter what the preference lists of the nodes are. A highly non-obvious fact. The proof of the Gale-Shapley theorem is as elegant as the algorithm. Let me show it to you now. So first of all, why does the algorithm converge in a quadratic number of iterations? Well, no man proposes to a woman twice. Therefore, each man makes at most n proposals. There are only n men, so that's at most n squared proposals overall. Secondly, when the Gale-Shapley algorithm terminates, it does so with a perfect matching. Indeed, it's a stable matching, but let's just, for the moment, prove that it's a perfect matching. To see this, let's suppose the contrary. Let's suppose that when it halts, it does not halt with a perfect matching. That means, in particular, some man is assigned to no woman. How could that have happened? Well, it must have been that the man fell off the end of his ranked list. He proposed to every single one of the n women and was rejected by all of them. So how could this have happened? Well, notice that for a man to be rejected by a woman, it must be that the woman has some other offer from some other man that she likes better. That is, rejections happen only by a woman who is engaged to somebody else. So by virtue of this man being rejected by all n women, all N women got engaged at some point in the algorithm. Moreover, if you inspect the algorithm, you'll notice that once a woman is engaged to somebody, she will remain engaged forevermore. The only thing that changes is the woman is engaged to men that she likes better and better as the algorithm proceeds. So a man rejected by everybody implies that all women get engaged at some point in the algorithm, which means that they're all engaged at the end of the algorithm. But there's an equal number of men and women. So there's no way all women are engaged at the end and some man is not engaged. If all women are engaged, all men must be engaged as well. Finally, why is the perfect matching computed by the Gale-Shapley proposal algorithm not just perfect, but more generally stable? To see why this is true, let's prove that there's no blocking pair. That is, let's consider an arbitrary unmatched man U and woman V. Now, either the man U proposed to the woman V at some point in the proposal algorithm, or he didn't. Let's treat those two cases separately. So let's first suppose that at no point in the algorithm did the man U propose to the woman V. So what's the behavior of a man in the proposal algorithm? Well, a man simply proposes to the women on his list one at a time in turn as necessary. And the woman to whom a man winds up matched at the end of the algorithm is the last woman to whom he proposed. So if the man U never got around to proposing to the woman V, that just means he never searched that far down in his preference list. And he wound up at the conclusion of the algorithm matched with the woman he prefers to the woman V. And so that's sufficient to claim that UV is not a blocking pair. Suppose, on the other hand, U did propose to the woman V at some point in the algorithm. Why did they not wind up matched? Well, it must be because the woman V got a preferred offer, an offer from some man she prefers to the man U. Now, something we mentioned earlier is that over the course of the algorithm, a woman just winds up being engaged to men that she prefers more and more. So if at any point she winds up engaged to a man she prefers to you, then at the end of the algorithm, she will be engaged, matched with a man that she prefers to you. And again, that implies that UV is not a blocking pair. Since UV was arbitrary, this is a stable matching. That completes the proof of the Gale-Shapley theorem. One key reason why the stable matching problem admits an efficient solution is that you can, in principle, match any node to any other node on the opposite side. Sure, the nodes have preferences and might not want to be matched to certain nodes, but there's no hard constraints preventing certain pairings. When you do have such hard constraints, we wind up with the classical bipartite matching problem. So the input to the bipartite matching problem is a bipartite graph. So remember what that means. That means you can take the vertices and put them into two groups. Let's call one of them capital U, the other one capital V, and every single edge has exactly one endpoint in each of the two groups. Put differently, there exists a cut of the graph that cuts every single edge. The goal is to compute the matching. Remember, a matching is a subset of edges that are pairwise disjoint. No pair of edges can overlap at an endpoint. And to compute the matching that has the largest possible size. So, for example, in this pink graph on the right, there are various matchings consisting of 3 edges, and I'll leave it for you to check that there is no perfect matching. There's no way to have a matching of 4 edges. So bipartite matching is a totally fundamental problem. There are constraints on which objects you can pair up, and you want to pair up as many objects as possible. I'm happy to report that the maximum matching problem is solvable in polynomial time. In fact, it's polytime solvable not just in bipartite graphs, which is what I'm discussing here, but even in general non-bipartite graphs. So in non-bipartite graphs, you have to work pretty hard to solve the problem in polynomial time. The bipartite case that I'm talking about here reduces easily to another problem you should know about called the maximum flow problem. So I'll now move on to describing the maximum flow problem. I'll leave it as a good exercise for you to do why bipartite matching reduces to maximum flow. You can study maximum flow in either undirected or directed graphs. The directed graph case is in some sense the more general one. Let me state that here. So the input is a directed graph. One special vertex is called the source vertex, S, and another vertex, T, is called the sink vertex. Finally, each edge E has a capacity, U sub E, which is the maximum amount of flow or traffic that the edge can accommodate. Informally, the goal is to push as much stuff as possible from the source vertex S to the sink vertex T, respecting the capacities of the various lengths. So you should think as examples as electrical current being generated from S and flowing to T, or you could think of water being injected into the network at S, flowing through these edges representing pipes, and then being drained out at T. The point is you have conservation of flow at every vertex other than S and T. That is, the amount of stuff coming in has to equal the amount of stuff coming out, except for S, where stuff gets generated, and at T, where stuff gets drained. As a simple example, suppose in this pink network on the right, I give each edge a capacity of 1. The maximum amount of stuff you can push from S to T in this network is 2 units. The way to do that is you send 1 unit of stuff over the top path from S to V to T, and you send a second unit on the bottom path using W as an intermediate stop. So I'm happy to report that the maximum flow problem can be solved exactly in polynomial time. There are many ways of doing it, many different cool algorithms that solve the max flow problem, but the simplest ways are in effect greedy algorithms where you route flow one path at a time. One thing worth pointing out is the most obvious greedy approach to the maximum flow problem doesn't work. The most obvious thing to do is to just find a path where there's residual capacity along every edge, send flow along that path, and repeat. So the suboptimality of the naive greedy algorithm is already evident in the 4-vertex network that I've shown you on this slide. Suppose in the first iteration, to find your first path to push flow along, you wind up choosing the path that goes from S to V to W to T. So that has 3 edges on it. All of those edges have capacity 1, so you're free to push 1 unit of flow along this zigzag path. But if you do that, you've now blocked up the other paths as well, the SVT path and the SWT path. There is no way to send further flow along any of those 3 paths. So this naive greedy algorithm only computed a flow of value 1, whereas we know the max flow value is equal to 2. So instead, you have to allow a more generous notion of an augmenting path where you can send flow in reverse, in effect undoing augmentations of previous iterations. But with this more generous definition of augmenting paths, the resulting greedy algorithm is indeed guaranteed to compute a maximum flow. Moreover, if you're smart about which augmenting path you use in each iteration of your greedy algorithm, you can prove a running time bound which is polynomial. There's also a number of non-augmenting path-based polynomial time algorithms for the maximum flow problem as well. In fact, this diversity of solutions for the maximum flow problem makes it a little hard for me to give you a succinct bottom line about what running time you can get for this problem. But roughly speaking, we don't have algorithms which are near linear time, but we have plenty of algorithms which are not much worse than that. Say in the quadratic regime, think about, Bellman-Ford like running time bounds of m times n. And a lot of these algorithms do quite a bit better than quadratic in practice. And one thing that's cool is that even though this maximum flow problem is totally classical, these augmenting path algorithms were first studied in the 1950s by Ford and Fulkerson, even in the 21st century we've been seeing some really nice new developments with maximum flow, cool new algorithms based on things like either random sampling or connections to electrical networks. In some applications of flow networks, you want to think about flows as not being computed by some centralized algorithm, but rather as arising from the behavior of a number of participants. Think, for example, when you get in a car and drive from, say, home to work. Nobody's telling you which route you have to take. Rather, you choose what route you want to take from home to work based on your own preferences. For example, perhaps you take the shortest route available. Such self-interested behavior in networks has been a major research topic in the 21st century. Let me just show you one cute cocktail party ready example of that called Braess's paradox. So imagine we have a flow network, and again, you might want to think about road traffic as being a simple example. Let's focus on a case where a bunch of morning commuters are leaving a common suburb represented by a vertex S, destined for some nearby city, let's call it a vertex T, all leaving at roughly the same time, and all of them get to pick whichever routes they want through the network to get from S to T. So to better represent issues in transportation networks, let's, instead of thinking of links as having capacities, let's think of them as having delay functions. So for each edge, there's going to be a function which describes, as a function of how much traffic uses that edge, what is the resulting travel time that all of that traffic endures. So as you know from your own experiences, the more congested a road is, the longer it takes you to get across that road. So as an illustration, in this pink network on the right, let's give two of the roads the constant delay function always equal to 1. So these would be roads that have in effect an infinite number of lanes, but they're also pretty long. So no matter how much traffic is using it, it always takes you an hour to traverse one of these two roads. The other two roads, by contrast, we're going to have the travel time increase with the congestion. And just to keep things really simple, let's use the identity function so that if 100% of the traffic uses one of these roads, then it takes an hour. If 50% of the traffic uses one of these roads, all of that traffic takes a half an hour to traverse the road, and so on. So let's now look at this pink network. Remember, we have this one unit of selfish traffic, which is representing hundreds or thousands of drivers that are picking their own routes from S to T. Let's assume that drivers just want to get to T as quickly as possible. They just want to minimize their travel time. And then the question is, which flow is going to arise from this aggregate self-interested behavior? Well, the two routes are exactly the same. Each one has one road that always takes an hour, and it has and also has a second road which takes time proportional in hours to the fraction of traffic that uses it. So because of this symmetry, once things settle down into a steady state, we expect half of the traffic to be using the top path, half of the traffic to be using the bottom path. With a 50-50 split of the traffic, each of the two routes takes an hour and a half overall. Now, I mentioned something called Braess's paradox. So what's the paradox? Well, imagine that we view this hour and a half commute time as totally unacceptable. Moreover, imagine that we have a new technology. Someone just invented a teleportation device, and we want to install it in this network so that people can get to their workplace faster than before. So let's install one of these teleporters at the vertex V to allow people to travel instantaneously to the vertex W. So we'll represent that by adding to this pink network a fifth length from V to W with the constant delay function always equal to 0. So what are the ramifications of adding this teleportation device allowing you to go from V to W instantaneously? Well, suppose you were one of these drivers, stuck with your current commute time of an hour and a half. No surprise, you would want to ditch your old route to make use of this new teleporter. So you would want to switch from your old path, whether it was SVT or SWT, to the new zigzag path, SVWT. It's looking like then you'd get to work in only an hour. You'd spend half an hour on the edge SV, instantaneous teleportation, and another half an hour on the edge WT. But here's the catch. Not only are you going to switch your path to use the teleportation device, so are the thousands of other drivers. So in the new steady state, after we've augmented the network with this teleportation device, everybody's going to be using the zigzag path, SVWT. And now that everybody's doing exactly the same thing, all of the traffic uses the edge SV, driving its travel time up to an hour. Everybody's using the edge WT, driving its travel time up to an hour. So now, despite the fact we've made the network intuitively only better, in the unique new steady state, assuming everybody selfishly chooses their minimum travel time path, the commute time has actually gotten worse. It's jumped from an hour and a half for everybody to 2 hours for everybody. That is Braess's paradox. Improvements to networks where you have selfish users can make the outcome worse for everybody. Wow. So that's Braess's paradox, discovered by, you guessed it, Braess, a German mathematician back in 1968. Amaze your friends and colleagues at the next nerdy cocktail party you find yourself at. Actually, there's a physical realization of Braess's paradox you might find more useful for that purpose. Here's the idea. The idea is you're going to take as ingredients strings and springs. The strings are meant to perform the function of the constant delay functions. Strings, of course, being inelastic objects. The length of a string is independent of the amount of force you apply. Springs, on the other hand, are elastic. That is, their length is proportional to the force applied to the spring. So those play a role analogous to the linear delay functions in this network. So Braess's paradox shows that there exists a way to wire strings and springs together and then hang this contraption of strings and springs from a fixed base, say the underside of a table. You hang a weight from the bottom of these strings and springs, so that naturally stretches it out. Now, in general, when you have a contraption that's holding some weight and you start chopping, you take a pair of scissors and you cut things off from the middle of this contraption, you expect the contraption to be weaker and therefore the weight is going to sag further toward the ground. But in the same way, Braess's paradox shows that removing a supposedly helpful teleportation device from a network can actually shorten selfish commute times. That shows that cutting out taut strings from the middle of the contraption can actually get a weight to levitate further off of the ground. And this is not just hypothetical. Students in my classes have built these strings and springs contraptions and have demonstrated this levitation. If you search YouTube, I'll bet you can find some videos. Try it at home. Next, let me mention, embarrassingly briefly, linear programming. So linear programming is a problem that, on the one hand, is efficiently solvable, both in theory and in practice, and, on the other hand, is very general. It includes, as a special case, bipartite matching, maximum flow, and tons of other stuff. The general problem solved by linear programming is to optimize a linear function, maximize or minimize, it doesn't matter, optimize a linear function over a set of linear constraints. Geometrically, that corresponds to finding the best point, the optimal point, in a feasible region which is representable as the intersection of half spaces. So let me just draw a cartoon picture, which is going to be in the plane, although let me emphasize the power of linear programming is that you can efficiently solve problems that are in massively higher dimensions. Not 2 dimensions, but think millions of dimensions. So in the plane, the intersection of half planes, assuming it's bounded, is just going to be a polygon. And you can think about optimizing a linear function as just trying to push as far as possible in some direction, subject to being inside the feasible region. So for example, maybe you want to push as far to the northeast as possible, subject to being one of these blue points, somewhere in this polygon. For example, the maximum flow problem is easily encoded as a special case of linear programming. You use one dimension, that is one decision variable for each edge. The decision variable describes how much flow you route on a given edge. The linear objective function would be to maximize the sum of the flows on the edges going out of the source vertex. And then you would have linear constraints just insisting that the amount of flow coming into a vertex is the same as the amount of flow coming out of a vertex. And linear programming encodes not just maximum flow, but tons and tons of other problems as well. Despite its generality, linear programming problems can be solved efficiently both in theory and in practice. The systematic formulation and algorithmic solution of linear programs was pioneered by George Dantzig back in the 1940s. In particular, Dantzig invented what's called the simplex method, which remains to date one of the most important practical methods for solving linear programs. Have you ever heard that story about the student who walks in late to a class, sees what he thinks is homework written up on the chalkboard and solves them, not knowing that they are in fact major open research questions. Well, maybe you thought that story was apocryphal. Certainly I did for many years, but it's not. Turns out it's totally about George Danzig. In 1939, he walked into his graduate statistics class late. The two major open questions in the field were written on the chalkboard, and he solved them within a few days. That wound up being his PhD dissertation before he got interested in linear programming. Now, the algorithms used to efficiently solve linear programs, they're pretty complicated, both versions of the simplex method and so-called interior point algorithms. So it may or may not be a good use of your time learning more about how the guts of these algorithms work. But what almost surely is a good use of your time is how to be an educated client of these algorithms. That is, to get some practice formulating problems as linear programs and solving linear programs using either open source solvers or commercial linear programming solvers. Those solvers are a very powerful black box tool to have in your algorithmicist's toolbox. In fact, there are black box subroutines available to you that are strictly more powerful than linear programming. One generalization is convex programming, so linear functions are a special case of convex functions. And if you want to minimize a convex function or equivalently maximize a concave function subject to convex constraints, that again is a problem you can solve efficiently both in theory in terms of polynomial time and in practice. Maybe the problem sizes you can reach aren't quite as big as with linear programming, but they're pretty close. A different generalization is integer linear programming. So these are like linear programs, but where you add the extra constraint that certain decision variables have to take on an integer value. So something like 1/2 as a value for a decision variable would be disallowed in an integer program. Now, these in general are no longer solvable efficiently in theory. It's easy to encode NP-complete problems like, say, vertex cover as a special case of integer programming, but there is quite a bit of advanced technology out there for solving, at least in special domains, integer programs. So again, if you have an NP-complete problem and you really need to solve it, integer programming is a technique you're going to want to learn more about. What are some other important topics we haven't had time to discuss? Well, first of all, for many of the topics that we have discussed, we've only scratched the surface. There's beautiful and useful stuff beyond what we've discussed in these classes on topics ranging from data structures, for example, with hashing and with search trees, to graph algorithms, we already mentioned matchings and flows, to approximation algorithms like beta heuristics for the traveling salesman problem. A topic we've barely discussed at all is geometric algorithms, one exception being a divide and conquer algorithm for the closest pair problem that we discussed in part 1. Roughly speaking, the study of geometric algorithms has two flavors, low-dimensional problems and high-dimensional problems. So when I say low-dimensional, I mean probably 2 or 3 dimensions, so problems in the plane or problems in 3 space. A canonical computational problem here would be the convex hull problem, which means I give you a bunch of points, and then you want to know which points are on the convex hull of the point set. So here's a way to think about the convex hull problem in the plane. So take a wooden board, a flat wooden board. That represents the plane. Now pound a bunch of nails into the wooden board. Those are representing the points in the plane. Now to compute the convex hull, what you can do is you can take a rubber band, stretch it out really far so that it bounds all of the nails you pounded into the wooden board, and now let the rubber band go, and it's going to snap around the boundary nails. That's a way to compute the convex hull in 2 dimensions. And so the question is, how do you do that efficiently given just a bunch of coordinates of points? The state of the art here are divide and conquer algorithms, very much in the spirit of what we discussed for the closest pair problem back in part 1. So why would you care about computing convex hulls? Well, there's lots of reasons, but as one example, suppose you were doing some 3D graphics and you had moving objects in your scene and you wanted to know when 2 objects collide, because then you have to respond appropriately in rendering the scene. Well, to know whether 2 objects collide, you don't have to remember all of the details of the objects, you just have to keep track of their convex hulls. They collide exactly when their convex hulls intersect, and so that's one reason you might want to do that computation. A very different flavor of geometric algorithms is the high-dimensional case. And here I'm thinking of the number of dimensions as being in the thousands, say, or perhaps even quite a bit more than that. Now, why would you ever have points in thousands of dimensions? Well, imagine you were doing, say, information retrieval. Imagine you had a bunch of documents. Now, documents don't really have geometry intrinsically, but it can be useful to imbue them with geometry. How do you do that? Well, imagine you make a list of all of the words in the world that you care about. So maybe say 10,000 words that you think are interesting. And for a given document, you just count the number of occurrences of each of these 10,000 interesting words in the document. So maybe lots of them are 0. The words don't occur at all. But maybe there's some word that occurs 7 times in the document. So then you give it a 7 in that coordinate. And boom, you've now represented each document as a point in 10,000 dimensional space. One coordinate for each of the interesting words, the value of that coordinate being the frequency of that word in that document. Now you can start asking questions like, given a new document, is it similar to any of the documents you've already been storing? And geometrically, that just corresponds to asking something called a nearest neighbor query. Given a bunch of points in possibly high dimensional space, and given a new point, which of the previous points is closest, say in Euclidean distance, to the new point you were just given? That would be a canonical question you would ask in high-dimensional computational geometry. In these design and analysis of algorithms courses, we've been focusing on the most classical style of computation, where you're given up front an input, you do a computation, and you produce some output, then you take a bow, and you leave the stage. But if you think about computation in the real world, there's plenty of algorithms whose work is never finished. Algorithms that, in effect, run forever. Two applications that we've mentioned in passing in this class are the caching problem. So for example, if you're writing an algorithm to manage a cache, say, for an operating system, that algorithm's work is really never done. It's going to have to manage the cache indefinitely. Similarly, you can think about routing in a network, say an internet routing. Again, that algorithm's work is never done. There's always going to be link failures. There's always going to be new nodes. There's always going to be new data to route. So it has to keep making routing decisions indefinitely, as long as the internet exists. As you would hope, both the theory and the practice of understanding algorithms that run indefinitely, making decisions in real time, is based quite squarely on the lessons that we've learned in the classical computational paradigm here, but it is an interesting topic worthy of study in its own right. A major concern of algorithms research in the 21st century is massive data sets, meaning data sets that are way too big to fit in the main memory of a single machine. One hot topic has been so-called streaming algorithms. These are algorithms which have to, in effect, take a fire hose of data being generated at a torrential pace and boil it down using small space into just a few accurate statistics. So you might think, for example, about an algorithm running locally at a network router with data packets flying through the router at a ridiculous pace, or an algorithm which is responsible for summarizing the data generated by a bunch of telescopic observations. A final important topic for which the current theory is actually quite immature is understanding how to exploit parallelism in tackling massive data sets. For example, using the distributed systems approach exported by the MapReduce or Hadoop systems. So that brings us to the end of our journey and concludes the course. And you know, I've been teaching this material for a number of years now, but it never stops being fun. It never gets boring. The study of algorithms is an excuse to learn many of the greatest hits of computer science. Many of the most brilliant ideas in the history of the discipline make appearances in these algorithms courses. So you've learned a number of elegant and clever algorithms and concepts. You've learned a bunch of practical techniques you can apply in your own programming projects, and there's been a remarkably large intersection between these two things. I know it hasn't always been easy. The state-of-the-art in the design and analysis of algorithms and data structures is a difficult topic. The computer scientists who preceded us were brilliant, creative individuals, but you are now in a position to stand on the shoulders of those giants and apply their ideas in your own projects. If I wanted to be a little bit starry-eyed about things, I might hope that this class has left you a little bit changed, maybe a little bit more passionate or intellectually curious about computer science, maybe a little bit smarter than when we started. Until next time.